Hello, everybody. Добрый день.
Добрый день.
Добрый день. Добрый день.
О, Виктор Анатольевич, здравствуйте.
Так, хорошо. Ну, у нас еще есть время, да, на какое-то?
Александр Иванович, рад вас приветствовать.
Добрый день.
Добрый день.
Добрый день, Виктор Анатольевич. Мы рады, для нас большая честь, что вы с нами всегда.
Я счастлив быть с вами всегда. Так что...
Можно мне сделать воспроизводство? Костя, сделайте. Ну, мы еще сейчас минуту подождем, да, вот пару у нас минут. Спасибо. А мой звук нормальный идет, да? Ну, еще как начинаем. 2 минуты еще, да? На часы вперед. Костя, а почему меня не видно сейчас? Меня не видно. Видно?
Good morning.
Good morning. Ну что, наверное, пора? Ну нет, еще у меня 59 минут. Good morning, my dear colleagues. So we are nearly to start. Probably half a minute we shall wait till really 10 o'clock Moscow time and 9 o'clock Eastern Zone time, as our program is scheduled in, as it is indicated in our program. So, good morning, good afternoon to everybody. It is a great honor and pleasure for me to welcome participants and guests of the 20th Lomonosov Conference on Elementary Particle Physics that is organized by the Faculty of Physics of the Moscow State University under the patronage of the rector of the Moscow State University, academician Viktor Sadovnichiy. This is the 20th event in the series that started in 1992 when the conference got the name of Mikhail Lomonosov, the brilliant Russian encyclopedist of the epoch of the Empress Catherine II. And the Moscow State University was founded 266 years ago based on his plan and initiative. We are very thankful to Professor Nikolai Sysoev, the Dean of Faculty of Physics, for steady support of organizing committee for more than a year period since the conference preparation. And now it is a great honor for me to give floor to the Vice Rector of the Moscow State University, Professor Andrei Fedyanin, thanks to whose personal efforts the very holding of the conference this year become possible. Пожалуйста, Андрей Анатольевич.
Thank you. Good morning, ladies and gentlemen, dear colleagues. On behalf of the rector of Lomonosov Moscow State University, academician Viktor Sadovnichiy, and the dean of the Faculty of Physics, Professor Nikolai Sysoev, let me welcome all participants of this very important conference. Indeed, during more than a quarter of a century, the Lomonosov Conference has become not only an important scientific event here at Moscow State University, but has also taken a good place in the club of the most prestigious international conferences on fundamental physics. I guess it was a good decision for the conference organizers not to cancel or postpone the event to the later date, but to hold the conference at the usual time, which is in the last decade of August each odd year. At the same time, we do hope that we will be able to hold the next Lomonosov conference in full-time format. We welcome participation of senior scientists, head of the large international collaborations and institutions, as well as the young researchers from all over the world. As far as I know, representatives of more than 30 countries are participating in this Lomonosov conference. And I'm pretty much sure that even in online format, the conference will provide a nice opportunity for fruitful discussions of elementary particle physics, astrophysics, gravity, and cosmology. These fields of physics are very strongly represented here in Moscow State University, and not only at Faculty of Physics, but also at Faculty of Space Research, in the Skobeltsyn Institute of Nuclear Physics, and in the Sternberg Astronomical Institute. And many participants from Moscow University present their talks at the conference. Let me wish to all of the participants interesting presentations and discussions. Good luck to the 20th Lomonosov Conference. Thank you.
Thank you very much. I would like to recall that the conference is organized by the Moscow State University with very deep and close collaboration with the Joint Institute for Nuclear Research. And it is a pleasure for me to give floor to the scientific leader of the Joint Institute of Nuclear Research, academician Виктор Матвеев. Пожалуйста, Виктор Анатольевич.
Thank you. Спасибо. Dear academician Sadovnichiy, Professor Fedyanin, Professor Studenikин, Romanov, Rubtsov, dear colleagues, friends, good morning. С добрым утром вас всех, дорогие друзья. It's a great honor and a big pleasure to me, on behalf of the Directorate of the Joint Institute for Nuclear Research in Dubna, to welcome all of the participants of this 20th Lomonosov Conference on the elementary particle physics, which is now dedicated to the Year of Science and Technology of Russian Federation. First of all, I would like to thank the Faculty of Physics of Moscow State University, the Institute for Nuclear Research of Russian Academy of Science, and other institutes. Sorry?
What happens? No, please continue. Everything is okay, yeah?
Mm-hmm. And other institutes of Russian Academy of Sciences who have helped to organize jointly with JINR this traditional international conference. Already, as you just told, 20th in a row. Special gratitude is to Professor Alexander Studenikin for his enthusiastic and energetic contribution to organization of this very popular, very prestigious international conference in our area of science. This time, for understandable reasons, we will work in distance form, but it does not make it less interesting. Quite opposite. The most advanced science, the particle physics, is developing on a global scale in spite of all troubles, and wide international cooperation is an ultimate necessity for this progress. So we are especially grateful to those participants who are now watching us at the different continents in spite of time differences at all. Also, it's very pleasant to see the list of participants, and I would like to very much hope that you are healthy and active, and we are now all together in spite of in this video form. So let me congratulate all of you with the start of our work and wish you a considerable, well-deserved success. Thank you, dear colleagues.
Thank you very much. Since 1992, the Lomonosov conferences have been supported by the Ministry of Science and Higher Education in Russia. And it is a great honor for me to give floor to the Vice Director of the Department of State Scientific, Technical and Innovation Policy of the Ministry of Science and Higher Education of Russia, Mr. Andrei Romanov. Пожалуйста, Андрей Михайлович.
Thank you very much. Спасибо. Dear colleagues, уважаемые коллеги, друзья, on behalf of the Ministry of Science and Higher Education of the Russian Federation, I am pleased to welcome the participants and guests of the 20th Lomonosov Conference on Elementary Particle Physics, held at the main forge of scientific personnel in Russia, Lomonosov Moscow State University. We are deeply pleased to note that the conference invariably gathers leading scientist stars of the first magnitude, and the number of participants of this conference shows a significant increase, which reflects the relevance and prospects of the elementary particle physics. We are proud of our country, and we are waiting for new discoveries at the mega science installations being created in Russia now. The Neutrino based on the ion collider facility NICA in Dubna, and the cubic kilometer sized Neutrino telescope in the depths of Lake Baikal. We hope that the work of Russian scientists, together with their foreign colleagues, will open the door of a new physics, already beyond the standard model frameworks, which remains an unknown but intriguing prospects for the further technological development of mankind. I wish all collaborations of scientists, new bright achievements of the world level, and this conference many beautiful reports and successful work. Thank you for your attention.
Thank you very much. Well, there is another very important player in the organizing of this series of events. This is the Institute for Nuclear Research of the Russian Academy of Sciences. And it is a great honor for me to give the floor to the Vice Director of JINR, Professor Grigory Rubtsov. Пожалуйста, Григорий Иванович.
Thank you, Alexander Ivanovich. Great pleasure and honor for me to welcome the participants of Lomonosov Conference on Elementary Particle Physics. I am very grateful for this opportunity to the organizers, to the Alexander Ivanovich Studenikin, who has a first role in the organizing of the conference for many years. I am pleased to convey to you the words of greetings and wishes for a fruitful conference from the Director of Institute for Nuclear Research of the Russian Academy of Sciences, Maxim Libanov. This is the 20th conference in the series of the most representative and prestigious Russian conference on particle physics. The conference for many years has become a very stable platform for broad discussions on the topics of neutrino physics, dark matter, physics of elementary particles, cosmology, and physics of atomic nuclei. The program is very intense, and it includes a breakthrough experimental results in neutrino physics, particle physics, and many other topics in the scope of the conference, and talk on the brightest theoretical and phenomenological models. Due to certain circumstances, we meet online this time. And I'm delighted to see that although we can't meet at Moscow, the program of the conference is most ambitious than ever. There are many talks from the leading groups and scientists, and the program of the conference confirms the status of this the series of the conference and made a step forward. And I hope that next time we meet offline, and I think this conference will have a great success. And I wish all of you fruitful and very inspiring communications, which will facilitate the discoveries. Thank you.
Thank you very much. Well, indeed, the Lomonosov conferences started in 1992. And so this is a short prehistory. In the 80s, a series of 4 workshops for young scientists with the title Cyclotron Radiation and its Applications was organized by the Moscow State University. At the 4th workshop in 1988, the organizers decided to complete the realization of these workshops. A year later, in 1989, it was proposed by myself to renew that series of events on a new basis with much broader scientific program and to include more general issues in particle physics. And the conference was planned to be held in September 1991 in the world-famous Samarkand, Uzbekistan. At that time, that was the Soviet Union. But we know that in August 1991, the putsch happens in Soviet Union, and due to unstable and unpredictable political situation, we have to cancel this conference. However, we didn't give up the conference, and this project was continued. And the conference on elementary particle and external fields was organized by the Moscow State University in Yaroslav in April 1992. This is the Asian town about 200 kilometers to the north from Moscow. And during the preparation of the conference, I proposed that the conference should start a series of full-scale international events with a total title Lomonosov Conference on Elementary Particle Physics. That is the birth of Lomonosov conferences. And this proposal just was included in the program of the Yaroslav conference, where one finds in the future, this series of conferences will be continued under the title Lomonosov Conference on Elementary Particle Physics. And that conference in Yaroslav will bring together about 50 participants and about 30 presenters. And just looking on this exhausted young guy, you can expect that it was not the easiest task to start the conference. Since the beginning, the project of International Lomonosov Conferences on Elementary Particle Physics attracted interest both and support from the Russian national and international scientific communities. And I would like to recall here the name of Professor Giordano Gamberini Palazzi from the Sapienza University di Roma, who was a big enthusiast and helped a lot in the very beginning of the Lomonosov conferences. He was a speaker and also to promote this event among the world scientific community. And thanks to his help, the first proceedings of the Lomonosov conference of 92-93 were published by the Accademia Nazionale dei Lincei, thanks to kind decision of its president, Giorgio Salvini. Well, then the conference proceedings start being published by the World Scientific Collaboration in Singapore. We have issued a series of these colored books dedicated to proceedings of the previous conferences. All these books have in the title Particle Physics. So, and the recent conference held in last conference, 19 conference held in 2019, just published, and now the authors and the presenters of that conference should receive these volumes. So the Lomonosov conference received a reasonable support inside Russia, and the rising of scientific value of the conference has been provided by the personal participation in the events of the distinguished Russian scientists. And I would like to nominate Russian scientists who have provided a very important contribution to the organization of Lomonosov conferences and to forming the scientific programs during the past nearly 30 years. So this is academician Dmitry Shirkov and academician Andrei Slavnov. There is academician Lev Okuny. Of course, it is an honor to welcome once again Viktor Matveyev, who started supporting the conference, being the director of Institute for Nuclear Research, and now he's continuing his job for the conference from the Joint Institute for Nuclear Research. And of course, it is a great pleasure for me, an honor to indicate the contribution of today's director of Joint Institute for Nuclear Research, academician Grigory Trubnikov. And just recently, I would like to announce this, that we have reached an agreement that the proceedings of this 20th Lomonosov conference will be prepared in collaboration with the Joint Institute of Nuclear Research, and the book will be published by JINR. I would like to announce that the deadline to send in contributions to the editor is December 15, 2021. Information will be distributed among speakers very soon. So the 20th Lomonosov conference bring together many famous scientists, and also we are happy that many young researchers from 34 countries are speakers at the conference. And here is this figure or histogram that's showing the increasing number of participants, speakers during the years. Now we have 235 speakers at the conference. And this is the map of Lomonosov conferences. And in red, we indicate the countries, the speakers from which were presented in the previous editions of the Lomonosov conference. So the conference program covers a broad set of items in high energy physics, particle physics, astroparticle physics, cosmic rays, gravitation, and cosmology. And the main goals of the conference are to bring together scientists from different fields and to stimulate exchange of results and ideas, maintaining collaboration between different institutes and universities, to promote communication between young and senior scientists, and to establish relations between scientists and of different countries. A striking example of this international collaboration is provided by Dr. Alexei Lokhov. He graduated the master's degree and the postgraduate school of the Faculty of Physics of the Moscow State University. He is still the member of our Neutrino group. He is an employee of the Institute of Nuclear Research of Russian Academy of Sciences. And he has played a key role in the organizing committee of the Lomonosov conferences of previous editions. And now, staying in Germany for several years at the University of Münster, he has become a very important member of the Katrin collaboration. And we are proud that he is going to give a review talk at the Lomonosov conference of this year on behalf of the Katrin on the most fundamental problem of today's physics, that is the problem of neutrino mass. So, I would like, before to start this scientific part of the conference, I would like to announce an urgent request of the organizers to all speakers and chairpersons. So we have 235 presentations. We have 7 working days, no free day in the middle, quite short time for tea breaks and lunches. So we also have from +8 to -10 hours spread in time zones of different speakers. Therefore, I would like to ask all participants strictly follow the schedule. We recommend to reserve for discussions in the case of talks for 25 minutes, about 5 minutes, for the talks for 20 minutes, about 4 minutes for discussions, and for shorter talks from 2 to 3 minutes for discussion. So let me wish an interesting Lomonosov conference. And now in a few minutes, I think that we can start realization of the scientific program of the conference. And the first speaker is Valery Rubakov. Thank you. I think that we can wait for about 7 minutes to start sharply at 9:30 CERN time. Thank you very much.
Well, the first speaker is Viktor Matveyev. I'm Valery Rubakov. I'm chair of the first session.
So,
Okay, let's wait for 9 minutes.
Yeah, it's better. Yeah, I think it's probably too
I
late.
try to switch on my slide. So,
Okay, here, thank you.
okay.
Yeah, Alexander, could you please stop sharing the screen?
Yes,
Okay.
I will try to do it. So ask my colleague. Can you stop sharing the screen? Yeah, thank you. Have you succeeded? Now it's okay, yeah?
Now it's mine.
Perfect.
Mhm. Mhm.
Так, меня не видно сейчас, коллеги? Хорошо.
Вас не видно, а экран
Ага, есть.
не
Окей.
пойму чей.
Окей.
Все, Виктор Анатольевич, есть ваш экран.
No,
Только,
we can wait for about 5 minutes more, yeah, Valery?
да-да, ну, приготовить-то не вредно.
Yeah, of course, yeah.
Yeah, Victor,
Mhm.
you have, you probably make the full screen mode. Victor,
Да?
you could probably go to full screen mode, no?
Мгм.
Полноэкранная мода у вас должна быть.
А,
У вас
Тоже.
слева видны
А.
список слайдов.
Do you see these slides?
Yeah, we do see the slides, but we see also the left part of your screen with, yeah, that's good, excellent, very good.
So, mhm.
Yeah, that's,
May I keep it till beginning of my talk, or you
I
will?
think so, yes, I think it makes sense.
Mhm.
Сейчас, что-то у вас еще вторая видна на экране, второй слайд какой-то справа.
Виктор Анатольевич, у вас надо поменять экраны, потому что мы видим то, что вы должны видеть. А мы должны полный экран видеть и один слайд. У вас режим докладчика, там надо что сделать? Галку где-то поставить.
Что сделать?
Ну, чтобы вы видели два своих экрана, вот текущий и следующий. Потому что мы сейчас видим то, что вы должны видеть. Ваш заглавный слайд и следующий, который после этого. Это должны видеть вы. То есть вам надо каким-то образом поменять. Там, если это PowerPoint, то вам надо зайти настройка экрана и там где-то галку поставить, чтобы вы поменяли экраны, чтобы вы видели то, что мы сейчас видим все, а мы видели только ваш первый слайд на весь экран более-менее.
Ну, а это не мешает вам видеть?
Ну, в принципе,
Мы
да,
сейчас...
мы видим текст ваш, все заметки ваши видим. То есть мы можем вообще прямо вот вместе с вами читать то, что вы будете говорить. То есть надо...
А вот так вот нормально?
Вот сейчас...
Давайте так, Виктор Анатольевич.
Ну, сейчас нормально, да. Подождите,
Давайте так, Виктор Анатольевич.
да.
Вот
Почему у нас на том экране?
Нормально.
Там через Wi-Fi?
Мгм. Хорошо. Okay, so we now.
Okay, 5 minutes more.
Мгм.
We wait for 5 minutes.
Yes.
Yeah, now it's perfect, yeah.
Виктор Анатольевич, это у вас какие-то там звуки?
Нет. Окна закрою сейчас. Может быть.
Может быть. Как будто какой-то ремонт идет.
Либо зубной кабинет, Валера.
Да. Okay, so we are about to start. It's 9:30 European time, 10:30 Moscow time. I'm glad to welcome Professor Viktor Matveyev from Joint Institute for Nuclear Research, Dubna, who is going to talk about the 65th anniversary of JINR, present status and development strategy. And let me ask all speakers, as Alexander told already, to keep on schedule and leave maybe 5 minutes out of 25 for discussion. So please, Victor.
Thank you. Thank you. I really grateful to organize a committee who invited me to open this great conference with a special talk devoted to the 65th anniversary of Joint Institute for Nuclear Research, the only international intergovernmental scientific organization on the territory of Russian Federation. So I will try to speak very shortly by necessity on the present status and the development strategy of the institute. And at present, JINR unites scientists and specialists from 18 member states, which include Armenia, Azerbaijan, Belarus, Bulgaria, Cuba, Czech Republic, Georgia, Kazakhstan, Moldova, Mongolia, Poland, Romania, Russian Federation, Slovakia, Ukraine, Uzbekistan, Vietnam, and also scientists from 6 associated member states, countries, which includes Egypt, Germany, Hungary, Italy, Serbia, South Africa. So, and there are some negotiations with other countries and other big organizations for possibility to join our institute in different forms as full member states or associated member states or some other way. So in overall, JINR partnership network includes about 900 organizations and universities from 67 partner countries. So, and JINR, it is a integration form of international scientific cooperation supported by a set of large-scale research infrastructure facilities, which include, let me very shortly to name it, a complex of superconducting accelerators with high-intensity heavy ion beams called NICA, which is now under development, and also Dubna radioactive ion beams cyclotron complex, which includes world's first factory of super heavy elements with its core DC 280 cyclotron. So it also includes EBER-2 research pulsed reactor equipped with a set of super spectrometers facility, and Baikal, deep underwater neutrino telescope, which is constructed in the construction and development in cooperation with Institute for Nuclear Research of Russian Academy of Science and other partnerships. I will speak about that later on. Located on the Lake Baikal. Partially this complex in operation, partially under development. So we have multifunctional information and complex with Greek Tier 1 center, which is only among the JINR member states. So these facilities represent a very large multidisciplinary research infrastructure, realizing the deeply integrated governance model of international scientific cooperation. This infrastructure complex is partially distributed across the territory of several member states. So NICA which is a flagship of our 7-year plan, of our perspective plan. NICA is accelerator facility designed to perform a broad range of experiments on the hot and dense nuclear and baryonic matter. It will be able to operate both in collider in a fixed target modes and to provide a wide range of collision energies and particles types, as using heavy ion beams in the energy range from 4 to 11 GeV per nucleon, and proton beams with energy up to 27 GeV for heavy ion collisions and spin physics experiments with polarized proton and neutron beams. The construction of the first stage of NICA collider was completed. I will speak about these milestones. You may see maybe some milestones of NICA complex. The commissioning of NICA basic elements in accordance with schedule. It is a booster in 220 already done. Basic configuration in collider, it is years 2022, 2023. And design configuration, full design configuration of the collider in 2025. Development of experimental zones and extracted beam channels of the NICA complex. It is 2022 year, and startup of the baryonic matter nucleotron initial configuration for high intensity light ion beams extracted from nucleotron. It already was started a few years ago. So just very few slides, maybe this one, which is illustrate booster commissioning, and at the end of 2019 there was special first beam circulation testing in a booster. So, and at the end of the last year, you may see the visit of Prime Minister of Russian Federation Mikhail Mishustin, who participated in the ceremony of inauguration of this booster technology testing. This slide shows a view of collider building under construction in May of this year. Completion of all construction is scheduled for 2021, but as soon as the various blocks of buildings are ready, they will be transferred in stages to begin the installation of scientific equipment. So in June, the installation of the magnet for multi-purpose detector hall already began, and in August the collider system will be done in tunnel. No. You may see on these slides that there is international cooperation around the NICA project, and already there are formed international collaboration around the multi-purpose detector, for also in experiment baryonic matter at the nucleotron collaboration, and for spin physics collaborations now is forming. And in general, let's say in total that member states, 7 member states contributed in construction of NICA to $281 and some others $1 million, and 43 countries additionally contributed 335 and some plus for NICA. So it is really international project with including also construction and also preparation for the physics program. Now, let me say that at the end of 2019, the unique factory of super heavy elements started to functioning, and up to now, say that development of this super heavy elements factory complex continues. You may see a differential pumping system on the Dubna-Gais field recoil separators was assembled and put into operation, which is necessary for carrying out experiments at a high intensity of heavy ion beams supplied to DC 280 accelerators. So it is really necessary system which allows to work with high intensity of heavy elements. And there goes a preparation for forthcoming experiments. And in February of this year, assembly of new gas field recoil separator was completed. The separator is intended for setting up experiments on the nuclear and mass spectroscopy of super heavy elements, as well as for studying their chemical properties. It's really very important step. And also the new version of so-named cold detector is being developed for performing thermomatographic experiments in the field of super heavy elements. So, and preparations are underway for experiments on a synthesis of the first elements of eighth period of periodic table, with number 119 and 120 started, so this preparation. So a beam of chromium ions with intensity of about 3 particle microamps is obtained, which is necessary for setting up experiments on the synthesis of elements 120 in the reaction of chromium 54 plus samarium 248, which is considered one of the most promising for these new results. In November last year, the first experiments were carried out in Flerov laboratory for super heavy elements factory on the synthesis of moscovium isotopes in the reactions calcium 48 plus americium 243. In fact, those very big program was intended to prove that previous results obtained in some period of many years, and it was repeated, in fact, during 1 month, let's say, at that super heavy elements factory, which demonstrates really very strong ability of this new system. Now about neutrino astrophysics and neutrino astroparticle physics. So on March this year, a ceremonial launch of the largest in the northern hemisphere deep underwater neutrino telescope Baikal GVD, so-called, was held. And now let me to say that largest, I mean, so the north hemisphere. Now this detector has fiducial volume 0.4 cubic kilometers, and ultimate goal is achieved with proceeding with this construction 1.5 cubic kilometers. So this significant for the JINR and world science event has become one of the key elements of the current year of science and technology in Russia. Moreover, this day, the Ministry of Science and Higher Education of Russia and the Joint Institute for Nuclear Research signed a special memorandum of understanding for the development of the Baikal deep underwater neutrino telescopes in cooperation with the Institute for Nuclear Research of JINR, of Russian Academy of Science, and other partners. That's really a very important step. So you may see on these slides illustration that there is an international collaboration around this GVD gigaton volume detector neutrino telescope at Baikal Lake. So, and now it's really one among of 3 largest neutrino telescopes on the world. It's IceCube on South Pole, Antares in Mediterranean. Now it's in the North Hemisphere. It's on Baikal Lake. We have in our institute fast developing, intensively, actively developing multifunctional information and computing complex at JINR. It allows to give a great help for preparation of experimental studies at NICA and other basic facilities of JINR, and also it allows to integrate cloud environment of JINR member states. So, and great help in that connection is connected with supercomputer, which was named Computer Gavarun of JINR laboratory. And just one slide for that, we'll see how extension of this hybrid light heterogeneous platform, including the Gavarun supercomputer, is going now in this laboratory information technologies, and it will allow us to accelerate theoretical investigations in many very important, ambitious direction of activity. Also, it allows to accelerate experimental data processing, larger and more efficient computing and information tools. It has a plans for very big new development, raising the ability of this complex. So, but it deserves a special talk on that direction. So we have, by the way, very good cooperation with Moscow State University and institutes of Russian Academy of Sciences. On these slides, it was shown that according to the topical plan of JINR, about 19% of scientific projects are focused on applied research with high innovation potential. The innovation strategy of JINR consists of development of innovation cluster, special cluster, based on research infrastructure of several laboratories. A GLEP laboratory of nuclear problem, Flerov laboratory nuclear reactions, and Frank Laboratory of Neutron Physics, Laboratory of Radiobiology, Laboratory of Information Technology, etc. So, and main message is that deep international cooperation and integration to develop interdisciplinary, very large research infrastructure for basic research seems to be a very promising strategy for creating a flexible and sustainable research infrastructure, both to meet current priorities and to be ready for the new challenges. And so our member states are very interested in such a direction of development. Now, JINR participates in the European program of the United Nations, which is called Atmospheric Deposition of Heavy Metals in Europe, assessment based on analysis of most biomonitors. Within the framework of cooperation between Laboratory of Information Technologies and Frank Laboratory for Neutron Physics, a data management system was created on the JINR cloud platform. For the first time in the history of United Nations Air Program in Europe, the idea of collecting information uploaded by the direct participants of the program was implemented to assess the quality of ambient air. Very shortly, I will say, but that also such a very important direction of research activity as which allows how to deal with this COVID-19 problems. So, and a few laboratories of our institute very deeply now involved in studies of different aspects of this program. So, and gives their results for specialists in medicine and etc. So I will not speak about that in details because it will take many time, but it's really very interesting direction of activity, which is also which says that all scientific center of our kind is has a duty to contribute to this to fight with such a dangerous illnesses like COVID. Now, we, according to the decision of Committee of Plenipotentiaries of our institute, developed a special long-term program for institute, which should work at least for 2030 and maybe above of that. Beyond pure scientific part of this program, also it has also some part which goes that to deal with such ambitious plans in fundamental physics, we also have to pay attention to for the development of Institute for Joint Institute for Nuclear Research as an international organization. So we have to follow all of the best practices, best ideas in the development of such a big scientific centers to achieve more high effectiveness of that. So you may see on this slide some elements of such a part of strategic plan for future. For example, a new initiative was stated. The JINR International Innovative Research Center for Nuclear Technologies is now will be constructed, will be developed for nuclear medicine, radiobiology, material sciences for training. So we are we're developing so-called digital JINR. So it's new, very effective form of providing help for scientists. So they will pay much less of their time for, let's say, for formalities, bureaucracy, etc. So we have such really interesting part of this strategic plan for the future, not just scientific ambitious plans, but also development of styles and using the best experience of the world now. And this strategic plan in size also includes also some graphics in many years, which includes cooperation in many international also programs. And also general requirement for our strategy is that all strategic plans of our institute has to be the part of international programs, international strategic plans. There is just one of the examples. What is now assumed when we speak about International Innovation Center for Nuclear Technology Research? The main tasks of this center is development of technologies and methods in the field of nuclear radiation, medicine, radiation, material science, advanced training of specialists for JINR member states for radiation biology and medical physics. And this really already includes participation from many member states and other countries in our institute. So there are main stages determined as one of them is a new facility with DC 140 cyclotron for electronic component testing, radiation, material science, track for membranes research and production, etc. And period of realization is from this year to 2023. Also includes a new facility, radiochemical laboratory class 1 for the production of radioisotopes, set of special kind for medicine. Also 40 MeV rhodotron, so-called accelerator, and period of realization 2022-2026. User facility with elements which are shown here, and in radiation biology, so-called omics technologies and Neutrino biological studies, radiation neuroscience approaches to increase radiosensitivity, pharmaceuticals, transgen system, targeted delivery, etc., etc. And new facility for R&D in beam therapy, treatment planning, radio modificators for proton and therapy, etc. So now I go further. You know that UNESCO proclaimed the next year, 2022, as International Year of Basic Research and Sustainable Development. And JINR will be one of the organizers of this International Year of Basic Science for Sustainable Development. So an International Year of Basic Science for Sustainable Development would show the ways in which curiosity-driven research is vital to ensure good health for all, to overcome hunger, to fight climate change, to preserve terrestrial and marine biodiversity, but also to increase world peace and fight inequalities. Together, researchers from all fields will reach out to general public and to the decision makers, both public and private, to support the development of the basic science, especially in part of the world where they are still insufficiently developed. This is very important contribution of fundamental science and scientists who work in that area for general public, for the best of mankind. Let me now just conclude this my short speech, saying thank you for your attention. And also there is one part of the phrase. You see, we are very glad when we are meeting our colleagues from member states of our institute anywhere in the world. They speak about JINR here in Dubna as our common home on the banks of the great Russian river Volga. So I invite also all of you who maybe never been in Dubna, so please come to see and work with us together. So, and I wish all participants of this conference great successes on our very important way of doing fundamental physics. Thank you.
Okay, thank you very much. We have a couple of minutes, 1 minute for questions. If there is any urgent question or remark, please speak up. Okay, I don't see.
Not just scientific talk, it's around science, maybe so, because of that, there's
okay.
not so much to discuss, but just to take into.
Yes, sure. We have
also.
to, yeah. we have to digest all this information.
Thank you.
Okay, so thank you very much, Victor. And let us move on to the second speaker, Professor Wang from Beijing, who is going to talk about particles and isoparticle physics in China.
Yes, can you hear me?
Okay.
Yes, we do.
I need to, yeah, okay.
Yeah, you
I
need you
stopped
have to
my.
share your screen, right?
Can you see my screen?
Yes, yes, very good, very good.
Okay, so I'm going to report the status and some latest progress of particle physics and also astroparticle physics in China. So first of all, our Beijing Electron Positron Collider has been continuous its operation even during the pandemic. We have recorded the highest peak luminosity in last year, and also we managed to publish some 30, 40 papers in the last year. So operation has been quite smooth. Even we had quite number of difficulties during this pandemic. We have a number of publications, highlights, which actually shows that we have very high quality publications. One example is the discovery of ZC sub S 3985, and this is a strange 4 quark states. And also we observed the damped oscillation behavior in neutron form factor, and this is also quite interesting and been accepted by the nature of physics. We also measured the Hyperon up-down parameter, and this alpha is measured to be 0.75. This is actually inconsistent, more or less, with the PDG. We have also other measurements like the gamma angles. Our future plan is to upgrade this machine because we had a study of the future physics program, and which requires that we need another 40 inverse femtobars of data, corresponding to almost 15 years of data taking at the current luminosity. So we decided to increase the luminosity by a factor of 3 by squeezing the beam size, and the method is to add a new RF cavity per beam. And also we'd like to replace the superconducting quadrupole magnet near the interaction point to increase the maximum beam energy from 2.45 to 2.8 GeV. And both are a test of CPC technologies. And this upgrade plan has been approved by the Chinese Academy of Sciences, and we will operate these upgrade activities in the next 3 years, and hopefully the machine, hopefully the upgrade can be finished in the year of 2024, and by the year of 2025, we can run the machine with a new luminosity, and this figure shows the designed luminosity at the beam energy above, say, 1.9 GeV or 2 GeV, with 1.2 times 10 to 33 kind of luminosity. And we plan to operate the machine at least until 2030. PES3 is a large international collaboration. We have more than 500 members from 74 institutions in 15 countries. Another major experiment in China is the Debye react neutrino experiment. We managed to observe the measure the θ13 angle, and you can see that this best precision of the θ13 has been reached something like 3.4% of the precision. And the detector has been decommissioned. Data taking has been terminated on December last year. We also had a ceremony to broadcast these termination activities, and we managed to get 1.7 million viewers online. So this was quite good success. We are going to continue the analysis of the data collected up to December last year, and we expect to improve the precision of the sine square 2 theta 1 3 to a level less than 3%. The DIAB collaboration is again a quite large international collaboration. We have currently something like less than 200 collaborators. At peak time, we had more than 250 collaborators. And we will continue this analysis in the next 2 years. Our next step for the react neutrino experiment is the JINR experiment. And this experiment continues to use the liquid scintillator and for the neutrino mass hierarchy measurement. So you can see the baseline. This is the diabase near and the far side. And then the JINR is going to be placed at the oscillation maximum of theta 1, 2. And we could measure the neutrino mass hierarchy by this huge liquid scintillator detector. Fortunately, we managed to find a site which is 53 kilometers from the 2 reactor complex. By doing this, we managed to get maximum neutrino flux from reactors and also to build the large detector and a small mountain with an overburden of 700 meters. The physics we could do at the JINR is the following. First of all, we can measure the neutrino mass hierarchy to the level of about 4 sigma in 6 years, independent of the CP phase. And we can also measure neutrino oscillation parameters with a precision less than 1%. And by doing this, we can test the unitarity of the mixing matrix. If we have a burst supernova event, we can obtain something like 5,000 events at the 10 kpc distance. We have a hope to discover the diffused supernova neutrinos if the average energy is more than 15 MeV. We can measure the geoneutrinos with the statistics of about the factor of 10 more than any previous experiments. By having this factor of 10 more statistics, we can determine the uranium-thorium ratio of the Earth. We could also do the solar and neutrinos and also search for proton decays and many other exotic searches. The JINR detector is very large, and this, of course, is a huge challenge to us. The detector is a factor 20 larger than the CamLand, and the light yield has to be a factor 5 more than the CamLand. The Caven is almost the largest in the world, 50 meters in diameter and 7 meters high. We need to build a world's largest aquatic tank with a diameter of 35 meters. And this 20 kiloton liquid scintillator has to have a best attenuation length. And also we need to produce 20,000 20-inch PMTs with a photon detecting efficiency at a level of 30%. This is almost factor 2 higher than what achieved by the Super K experiment. So this shows you the civil construction status. This is surface building, a vertical shaft entrance, and this is the design of the underground laboratory. This is the current status. You see the water pool has been completed, and we are going to start the detector installation very soon, in a few months from now. The detector R&D and the construction is now in a reasonably good shape. We managed to overcome major technical difficulties. The right figure shows you one panel of acrylic. All the panels have been produced, and this is the steel structure to hold the acrylic sphere, and this is also almost finished. You can see this platform, acrylic tank will be installed on top of this platform, and this platform can move up and down in automatic way in the underground water pool. The liquid scintillator raw materials and mixing and purification equipment are all either produced or in the very close to the end of the production. And the liquid scintillator production itself will start very soon. The requirement is written the following, and detector installation will also be started soon. For the phototube, we developed a new type of PMTs based on micron channel plate to collect the electrons. So this is very different from the dynode PMTs. Intrinsically, it should have a higher collection efficiency and easy for mass production. Indeed, we managed to reach detection efficiency, which is a quantum efficiency multiplied by the collection efficiency. Sorry, this is C, not D. Indeed, we managed to have this result almost 10% higher, relatively 10% higher than Hamamatsu. Based on the performance, cost, the risk, etc., we decided to purchase something like 3/3 from micron channel PMTs and 1/4 from the dynode PMTs. Up to now, all PMT have been delivered, tested, and instrumented okay. So you can see the Hamamatsu PMTs, typically 28% of collection efficiency, detection efficiency, and micron channel plate PMTs have a higher efficiency in the second half. We also plan to build a near detector at the distance of something like 30 to 35 meters from reactor core. And this is a measurement to determine the spectrum from reactors with a very high precision to avoid or to understand any possible substructures in the spectrum. The way is to build a world best or the highest energy resolution detector using liquid scintillators. So we plan to build a 10 square meter of silicon PN to detect photons with detecting efficiency more than 50%. The light yield has to be more than 4,500 PE per MeV. This is almost factor 3 higher than the Juno. The detector has to be operated at the level of at the temperature less than 50 degrees, minus 50 degrees to reduce the dark noise. And this is a reduction of almost 3 orders magnitude by running at minus 50 degrees. The detector is 1 ton level Calorimeter doped liquid scintillator. And we are going to have roughly 2,000 events per day. And energy resolution is going to be 2% per square root of E. In the future, Juno will be upgraded to a double beta decay experiment. The main purpose is to reach the level of 1 milli or 2 milli EV of the effective mass. By reaching this level, you can see from this figure, you can determine the absolute neutrino mass. This is M1, and this is M1 plus M2 M plus M3. So being able to reach 1 to 2 kind of milli EV is extremely important for the mass determination of neutrinos. This is the idea. We can insert a balloon or just to put in the doped isotopes for the neutrino-less double beta decays, and by doing this, say 50 tons of xenon 136, or maybe 100 to 200 tons of tellurium, you are able to reach this kind of level of the effective mass for the neutrino-less double beta decays. So we have a study showing this. We plan to do this upgrade in around the year of 2030. JINR is a large international collaboration. We have members of something like 600 members from 77 institutions of 17 countries and regions. For the accelerator physics, we plan to work on the Higgs factory. This is actually a discussion we had since 2005. We'd like to see what kind of machines we can have after BPC. So a Higgs factory indeed is an ideal kind of a choice, because we can look for hint of new physics in the E plus minus collider, and if yes, we can build in the same internal a proton collider to do direct search. So this internal can be reused for PP, for AA, for EP colliders, all the way up to 100 TeV. So this is actually a very, say, economic way of using the tunnel. So of course, the idea has been now spread out, and we have two proposals in the world, CPC and FCC. But we have been working our design with baseline 100 kilometers, 30 megawatt per beam power, and upgradable to 50 megawatt high Lumi Z option, and also for TT bar. And the machine has to be compatible with the PP collider. So this is our baseline design, and we have been also working on the R&D of components such as the electron gun, the positron source, superconducting RF cavities, high efficiency klystrons, dipole magnets, vacuum system, electrostatic separator, and also high temperature superconducting magnets. This is a kind of R&D for the future PP collider. Just give you one example. We have been working on the superconducting RF cavities by working on different R&D say technologies. For example, to increase the Q value, we have been working on the nitrogen doping, the mid-temperature baking. We also came out with a new polishing method to replace the bulk electron polishing. And this one shows you the surface of the RF cavity before the polishing and then after the polishing. And this is a way to reduce the amount of use of acid. So it's environmental friendly, low cost, and also efficiency is quite high, easy to operate. We built a number of prototypes, for example, 1.3 gigahertz 9-cell high Q cavities for Shanghai free electron laser project, and also for CPC. So you can see the result of this 1.3 gigahertz cavity. This is a spec of the CPC, spec of SLAC SES2, and also spec of Shanghai free electron laser project, and also SES spec. We also have been working on the 1.3 gigahertz 9-cell high gradient cavity for the ISC, and you can see we have been reaching this level. Still not so perfect for IISc, but we believe that we are able to improve. We also worked on the 650 megahertz 2-cell high Q cavity for the main ring of the CPC. And also we are working on the 1-cell high Q cavity, so that you can see that this is 1-cell cavity. If we're able to reach this level, we can actually save quite a bit of the cost for the CPC main ring. We've been also working on the ion-based superconducting high TC magnets. We built the world's first ion-based superconducting solenoid, which can operate in a field of 24 Tesla. This one shows you the result. And indeed, this is very remarkable and also very promising. We have been also working on many other different type of coils and trying to get the desired performance of this kind of magnet in the very high magnetic field. So we hope that the future proton collider can be based on the ion-based superconducting magnets, which has advantages of low cost and high performance. Now let's move on to the cosmic rays. We have finished our large high-altitude air shower observatory in altitude of 4,000 meters. Construction finished, and we also observed very high gamma rays from the Milky Way, 1.4 PeV. This is the highest energy ever people observed. We also identified 12 gamma ray sources up to 1 PeV. These prove that in the Milky Way, we have many PeV kind of accelerators. These are a very good source of the cosmic rays. So having this kind of information help us to understand the origin and the acceleration mechanism of cosmic rays. So this is very important result. And we also have an experiment in space to study cosmic rays. We are a member of AMS2, and now we are working on the HERD, which has a very high acceptance using cubic crystals. And this has been selected by the Chinese Space Station mission, and we hope we can launch this detector in the year of 2027. We also have a number of satellites in space for X-rays. One is InSight HSMT, which was launched in the year of 2017, and we obtained a number of important results like EW signals, electromagnetic signals from gravitational wave events, and also we observed the signals from FRB. This one originated from magnetic star, and also observed the highest magnetic field in the universe. The new experiment is called the EXTP, and this is going to be a leading flagship observatory for black holes, neutron star, and extreme physics. This is again a very large international collaboration. So I'm going to conclude my talk by this table showing you the current experiments and also future plans. Some have been approved, like Juno LASSO, even completed, and some are still in the study and the planning. So I'm going to stop here. Thank you.
Thank you very much. We do have 3 or 4 minutes for questions. If there are any questions, please speak up. Please pose your question or remark.
Valery, this is Yuri. I have a question. Do you hear me?
Yes.
Yeah. Okay, can I speak?
Yeah, please.
Yeah. Thank you very much, Professor Wang, for very interesting talk. I have one question, maybe comment to your slide 16. Yeah, you told that oscillation will be mostly understood in 10 years, and yeah, and you switch to double bit decay. I think in 10 years will 2 very important programs, long baseline experiments in Japan and in the US will start. So, and primary goal, of course, search for CP violation. And I think in 2 years will be beginning of another journey in oscillation measurements. What do you think about that?
Yes, I fully agree with you. This kind of 10 years from now is a rough kind of statement. So I think Dune and Hyper-K were still operational during that time, but I think the mass hierarchy and the CP were mostly understood. So we certainly can improve the precision, but I think the problem itself is more or less there. So there'll be no major discoveries. That's what I meant.
Okay, thank you.
All right, thank you. Other questions, please? Okay, I don't see any. Thank you very much for very interesting talk. And let's go to the next.
Я кончилась делать.
Sorry? Okay, anyway, let's go to the next speaker, Professor Vallée, who is going to talk about the prospects at CERN on physics beyond colliders.
Yeah, good morning. Do you hear me?
Yeah.
And do you see my slide? So thank you. And I will just stop the video to have a better bandwidth. Good morning, everybody, and thank you to as the organizers to give me the opportunity to report on physics beyond colliders. So the study was recently new momentum after the strategy update, and I will briefly discuss the lines of the new mandate that we got from the management. Spend most of my time on the projects, of course, as they are now and how they look like, and a few words on the updated organization. As you know, the study was launched initially to prepare the European strategy update as regards projects at CERN with the particle physics outside LHC, non-LHC particle physics, and we provided a number of reports to the strategy. So the strategy was quite positive for that kind of physics. And the management at CERN decided to keep the study alive after the strategy, to follow the projects and include also new projects for the future. And the mandate was updated. The PBC mandate was updated to take into account the strategy recommendations. And in particular, what we will try to do now is to increase synergies with neighboring fields, to strengthen the collaboration of CERN with national laboratories, which have, as you know, projects in particle physics. Of course, they are participating to LHC, but also have own projects on their site. And also increases communication between theorists and experimentalists by providing a central forum of exchanges. As regard the projects, I will first discuss the new facilities which have been discussed and which are now in the game. Discuss experiments QCD and BSM oriented mainly on the current CERN complex, and also the new experimental and theoretical directions which recently appeared. And all this is based on a PBC workshop that we held in March, where you see the details on everything I will show. So the new facilities. So as you know, CERN traditionally had a few non-accelerator experiments, and one highlight was a CAST experiment looking at axions from the CERN, from the sun, sorry. And there is now a longer-term second generation, next generation project, YAXO, which was studied in PBC, and its precursor, baby YAXO, is now approved and in construction at DESY. And CERN played a strong role in the design, especially on the magnet of baby YAXO. And baby YAXO has already a unique physics reach in the parameter space, and YAXO, of course, will have a higher reach. Another project which is rather decoupled from the CERN complex is a proton storage ring for measurement of the proton EDM. And the PBC study showed that a prototype ring was necessary before the final ring to tackle the many systematic issues. And the COSI facility at Jülich was supported by the strategy as a possible site for developing the project. So we hope that this will get momentum at Jülich, and of course CERN will stay involved in the design. Of course, most of the PBC projects studied are foreseen for the CERN complex, accelerator complex. And as you see on this slide, it's already a very crowded complex. So the workhorse for non-LHC physics is SPS, and especially the north area on Prévesin. But there are now new trends also to do fundamental physics on the lower energy injectors, especially on the antiproton decelerator and also on Isolde and Enthoff. So the flagship facility that was studied for PBC was beam dam facility, which is foreseen to be implemented on Prévesin in the north area. And unfortunately, the European strategy was quite positive on the physics goals of this facility, but could not recommend construction now, mainly because of financial reasons. So the R&D goes on, and we focus on matters which are also of general interest for other extracted beam at CERN, and also focusing on cost optimization and possibly looking at alternative siting, which could allow cost saving. There is also the possibility to implement a new electron beam facility based on the awake technology, which is being developed at CERN. The idea is to accelerate electrons using a wake field produced by proton bunches in plasma cells. So the proof of principle was validated during run 2, and there is now a program to consolidate the technology during run 3, and this could serve the purpose of an electron beam damp experiment in the CNGS decay tunnel after LS3. The two new topics which came in recently are studies of tagged neutrino beams, either electron neutrino beams monitored by tagging the kaon decays. This is an ENUBET project, which is already part of the neutrino platform at CERN. And more recently, the idea of a tagged muon neutrino beam based on tagging individual pion decays using fast radiation-hard silicon trackers developed for HLLHC. And these new type of beams could be the basis of either of short baseline beams facilities implemented at CERN to make precision measurements, which are necessary for the current long baseline projects, but also could be of use for the next generation long baseline projects. Finally, a facility which started to be studied in PBC, the Gamma Factory, where the idea is to gain orders of magnitude on gamma ray beams compared to existing facilities. And the idea is to convert a laser beam into a gamma ray beam using the strong boost of partially stripped ions stored in the LHC. So an important milestone was reached already by PBC by storing such ions in the LHC. And there is now a proof of principle experiment which is being prepared at the SPS. And such a facility could have many physics applications. And there was already a first workshop held to study those. So let me now move to the experiments mainly based on the current CERN complex, starting with QCD experiments. So the CERN complex has two specific strengths for structure functions and the study of the QCD phase transitions. LHC fixed target, which is part of the mandate of the PBC, allows measurement at high statistics, at high X and high Q square for structure functions. And for the QCD phase transition, together with SPS measurement, you can explore a domain which is intermediate between the collision mode of LHC with ions, as studied by Alice, and the reach of lower energy facilities. The current flagship program for heavy ion physics at SPS is NA61, which is a TPC spectrometer. It was recently upgraded to study open charm during run 3. This is something which was not done at SPS in the historical experiments of the 90s. And they now plan for the longer term a finer grain two-dimensional scan, energy ion size scan, to study the onset of fireball. And there is also now the idea to revive the Na60 concept, which was a dimuon spectrometer, to measure the caloric curve of the fourth order QCD transition. And the toroid design is now ongoing with PDC support. And we have now identified a location at CERN where it could be done. This was a difficulty in the initial PBC study. I cannot forget NEO project because this is really related to hot topic recently. As you know, the new G-2 FNAL measurement confirmed the experimental measurement at BNL of 20 years ago. And now the focus is more on the theoretical prediction, where the prediction based on lattice QCD seems to have a discrepancy with the one based on E plus E minus data. So MUONI would provide a third method, alternative method, to measure the dominant error on the theoretical predictions, which is hadronic vacuum polarization. And by measuring it in the T channel with mu-E elastic scattering. So this is very challenging experimentally, but the PBC study has not yet found a showstopper. And there is currently a pilot runs planned next year with still the aim to do a full data taking before LS3, or maybe later, we will see. This is now in the hands of SPSC. For structure functions, the flagship QCD facility at CERN is COMPASS, and it has now a long-term program named AMBER, and which could be based either on existing beams for structure function measurement, for example, with pi plus Drelian, which was not measured with very high statistics in the past, and but could also use new beams like RF separated high intensity kaon beams to, for example, revisit the kaon spectroscopy and bringing to the level of precision similar to pion spectroscopy. And so these are programs which are partly accepted for the short term, but in discussion for the longer term. And one domain for QCD which is developing strongly currently is LHC fixed target, which was pioneered by LHCb with a SMOC system during run 2. And LHCb has now installed a storage cell, SMOC2, which promises a large increase in luminosity during run 3. And there are longer term options studying within PBC, consisting in possible polarized storage cell in LHCb, which this is a LHC spin study, possible installation of a Y target in ALICE, and possible also double crystal setup, which would allow measurement of short-lived baryons, electric and magnetic moments. Especially having ALICE in the game would allow to benefit from a different acceptance and also maybe have even dedicated runs during proton running. Let me now turn to BSM-oriented experiments. So currently, as you know, there is now being no new high mass state discovered at the LHC. There is now more growing interest into mass ranges away from the TeV scale explored directly by LHC. And as you know, precision experiments indirectly are sensitive to much higher mass states than directly accessible at LHC. Beam damp experiments at the SPS explore one few 10 GeV range in mass, and the non-accelerator experiment explore the very low mass and very low coupling strength domain. So they are really complementary to LHC. So currently at CERN, the flagship BSM program at SPS is NA62, which is well on track to complete its measurement of this ultra-rare K plus decay during run 3. And for after LS3, there are two options are under discussion: higher intensity charge K on beam, or a K0 beam, previously called Clever project. Since K0 similar decays are complementary to charge decays for both CKM matrix and BSM researches, because they are sensitive to, in a different way, to parameters of BSM models. And the two options are now considered as an integrated project. And the choice and phasing between the two will depend on many things. First, the results of the current measurement on K+, and the future of B anomalies and how they relate within models to K+ and K0 decays. And also for K0 decays, there is a competition of Koto in Japan. Of course, what will be done at CERN will depend on the results of Koto, which may be a long-term program too. So NA62 plans also to take some data during run 3 in beam damp mode by closing the collimator upstream of the detector. And this would give new sensitivity to hidden sector. There is recently a new idea to complement NA62 by installing a small, rather low-cost detector called Shadows, some kind of mini ship detector, slightly off axis to increase the acceptance at high mass to hidden particles. So this is now under study. Of course, the flagship beam damp experiment is SHIP, associated to the beam damp facility. So SHIP would be a state-of-the-art dual spectrometer, sensitive to both scattering of hidden particles and decay of hidden particles. I hear somebody speaking. No? Okay. So there was a comprehensive design study done within PBC, but due to the delay of the PDF, there is further study now done to update the design of SHIP with emphasis of the critical system, muon shielding and decay vessel, and also cost reduction. There is also at CERN an electron beam damp running, by the way, where there are many Russian colleagues working on. It was initiated by Russian colleagues. And initially, it was a cheap setup implemented on the H4 test beam, electron test beam. And it's currently leading the field, especially in the missing energy mode. And there are currently upgrades being done to run at higher intensity after LS2. And similar searches are in preparation with muon and hadron beams, which would be a similar setup, but independent setup. One domain which is really developing now are dedicated detectors on the LHC to look for long-lived particles. And this is now part also of the PBC mandate. And this domain was pioneered by Phaser, which benefited much from the PBC support, and which is now installed for run 3. So it is a small detector, 400 meters from the Atlas collision point in the in the beam axis. And there are also 2 other detectors planned to be installed, accepted to be installed during run 3. One for milli-charged particles and the CMS collision and point, and one for forward neutrinos on the Atlas point. And for the longer term, there is recently the idea to implement a forward physics facility, which would be a dedicated cavern, again on axis of a collision point, probably the Atlas point, which would provide enough room to implement bigger detector than the currently implemented ones. So this is under study and could be implemented for after LS3 during the high Lumi LHC era. There are also big detectors off axis, which are under study either on surface, Matusla, or close to the collision points, Codex B on LHCb or on Atlas point in the pit. And there are demonstrators and simulators are being done currently within PPC. To finish, a few words on the new experimental and theoretical directions. There are a few facilities which are not considered in the PBC study, previous PBC study, but we are now entering the game. One is the antimatter factory, the antiproton decelerator, where many quantum technologies are at work for precision measurements, and new ideas are recently being introduced, and so there is really a potential for new precision measurements there of interest for particle physics that we are now following. Similar things are happening at Isolde and NTOF, and with, by the way, similar technologies. There is also possibility to increase the energy of Isolde, which could have some interest for fundamental physics. And there is a strong boost now, as you know, on quantum sensors for non-accelerator experiments. Within PBC, here are a few examples we are studying. We are studying, for example, the ion atom interferometer, which is foreseen to be sensitive to gravitational waves and ultralight dark matter. There is a study to implement the second stage at CERN in the LHC shaft. There is also a rather ambitious idea to detect the cosmic neutrino background with the Ptolemy from tritium decays. This is a Ptolemy project. And this is a study which is already ongoing for some time of an updated magneto-optical setup to measure vacuum magnetic beer refrigerants. Finally, a few words on theory. So one highlight of PBC was the definition of a set of simple benchmark models of hidden sector to allow comparison of projects using same assumptions. And now there is the idea to extend such models to all domains dealing with feebly interacting particles, to allow to cover the whole field in a coherent way. And there was a first workshop held recently with a report that you can look at. And these studies are now followed by the so-called FIPS Physics Center, which is now embedded in PBC as a portal of the PBC project to the external world as regard feebly interacting particles. And you see here all the kind of experimental projects and also theoreticians which are included in this study. So my last slide to show the updated organization, which takes into account the evolution of the project since the first phase of the study. And you see here on the physics domain, the Fifth Physics Center entering. There is some resources secured at CERN in the CERN medium-term plan for the next years for PBC support. And last but not least, new ideas may be submitted anytime to the PBC coordinators. So there It's very simple. If you have ideas for new experiments, just submit your ideas to us, and you have a few instructions on our website, which, by the way, describes all these new organizations and give details on the new projects. So thank you for your attention.
Thank you. Again, we have little time for questions or remarks, please. Well, if not, let me ask one question. Which reasonably large facility is going to be the first in the list you gave us?
You mean for the facilities?
For the new facility, yeah.
Yeah. Let us. I think it's difficult to say. Clearly, the BIMDAM facility, we will have to see where, if there is maybe a way to do it in the cheapest way. On the other hand, as you see, the other projects make progress and may fill the gap between the current projects, like, for example, NE62 BIMDAMP and the reach of SHIP. And especially if Shadows, for example, is implemented, it will start to fill the gap. So clearly, the motivation of the proton BIMDAM facility may decrease with the progress of other projects. So it's difficult to predict the future of this facility. The proton EDM ring, this is something which is really for the long-term future, and it is difficult to know whether it can be competitive with other methods, especially the progress of neutron EDM measurements, which, as you know, are the probes, typically the same thing as the proton EDM. So it's difficult to see if it will be competitive. YAXO clearly is being built already, so this is a new facility at DESY. So if you come back to CERN, Awake, to transform Awake as a real facility competitive with other beams is also a question which we are looking at as an electron beam at CERN. Clearly, maybe the best potential is for new neutrino beams to implement a short baseline at CERN, for example, based on NUBET, a short baseline tagged new beams using the current detectors of the neutrino platform, you know, these small liquid argon detectors, which will be available. This is something which may be achievable soon. The other thing which may be really feasible is a forward physics facility. This underground cavern, which should not be too costly, could be a really good way to maximize the reach of high Lumi LHC. So I think this one also has a chance, according to me, to be implemented on the timescale of LS3 or close after LS3. So, of course, this is my personal view. It's difficult to predict the future.
Okay, thank you. Okay, I don't see any. Yeah, there is some. Yeah, there is a question. But that was a question to previous speaker, I think.
On
so
the chat, yeah.
In the chat. So we maybe not take this question because this question was for the previous speaker. Maybe this can be answered privately. This was a question to Professor Wong. Okay, if there are no other questions, let's move on to the last speaker of this first session by Professor Bozovic, who is going to talk about Higgs physics with huge linear colliders. Please. Professor Bozovic, are you with us?
Yeah, sorry, I just forgot to unmute my microphone.
Okay, very good. Go ahead.
I'm going to share my screen now. I hope that you can see it.
Not yet.
Not yet, okay. Share. Okay, just a tiny moment.
Yes, yeah, we now see your
Tiny
screen.
moment, we will go here. And I am about to minimize this, stop my video for the sake of connection, and to go into the full screen mode, which should be hopefully happening now. So, is everything fine?
We see your screen, but not full screen mode.
You don't see a full screen mode?
Not yet.
New share. Okay. Is it better now?
Yeah, very good, very good.
Okay, okay. So let me say it is my honor to speak after distinguished colleagues before me, and also to be again at the Lomonosov conference, though in spirit, not in physical presence, which I hope it will improve in the future. I'm going to talk about future linear E plus E minus colliders as options for realization of the Higgs factories. Despite I think it is very well established fact, I would like to remind you, why do we need Higgs factories? Linear colliders are valuable, and I would say ready to go option for their realization, because decades of detector concepts, vigorous R&D on both technology and physics are behind these projects. And despite the fact that linear colliders offer more than Higgs physics, I'm going to constrain myself to Higgs physics cases. Here I stole a piece of a discussion from inspiring talk of one of my favorite theorists, Nima Arkani-Hamed, trying to remind us why actually Higgs factories are needed. Higgs discovery from 2012 ended era of reductionism and symmetries in particle physics, opening several important questions that we are lacking a full understanding of, like how can we accommodate the Higgs vacuum in the energy density of the universe, or why the Higgs is not enormously massive or even Planckian. Nima formulated that in a well-known cosmological constant and hierarchy problem, asking even more liberal question, why is there a macroscopic universe at all? The current situation here is that basically we're facing only limits in the absence of new physics discovery at LHC. From the point of LHC resolution, if we would like to probe, let's say, Higgs compositeness, the Higgs could be as elementary as pi. So at the moment, we cannot answer even how point-like is it. Not to mention the Higgs self-coupling, determining the shape of the Higgs potential that can be significantly enhanced in BSM models, in example, electroweak barrier genesis. Even high luminosity LHC will be capable to probe it with only 50% uncertainties. As Nima is again pointing out it here, being a harbinger of the profound new principles at work in a quantum vacuum, Higgs boson should be studied more closely. And naturally, Higgs factories are recognized as the highest priority future initiatives by the European Strategy Update for Particle Physics, are offering millions of Higgs bosons over their time span, with several projects of the market. Some are linear, like ILC and CLICK, some are circular, CPC and FCC. All electron-positron colliders comes in a package with general benefits like the reconstructible events from the known initial state and also almost QCD-free environment. But what is a genuine advantage of a linear collider is accessibility of the higher center of mass energies, and that really brings added value to potential physics searches. It is clear that it will be around for statistical precision. The starting point is already 100 times the lab luminosities. Circular colliders are in favor when it comes to luminosity, but as I said, linear machines offer genuine advantage of accessing the high center of mass scale. But naturally, when we have this display of future projects, it comes to the question, which one is going to be built? Apart from the physics program itself, which is more or less quite similar at all these machines, I think that other important aspects will be considered, like the extensibility of the physics span to accommodate new options. Clear advantage again of circular colliders is a PP option, but also linear colliders could offer gamma-gamma collisions or accommodate new accelerator technologies. Then it is the issue of technological feasibility and cost, and I would say, unfortunately, the politics, because the final decision will be, I'm afraid, of this nature. So talking about linear colliders, ILC and CLIC, they both come as a mature technological options that have been developed for decades in the case of ILC. So they're ready to take projects. That comes as a stage upgradable machines, as you can see on the top right, offering various heat production mechanisms accessible over the large energy span. From one of the speakers of the conference, my dear colleague Aidan Robson, I took a nice example how less precise determination, actually 2 orders of magnitude less precise determination at higher energy leads to the same precision of observable at lower energy. So the higher energy scale, apart from accessibility beyond the standard model physics, offers really very strong benefits. The similar is with polarization. Luminosity can be almost double, at particular in higher energy due to the chiral nature of the WW fusion as the dominant heat production mechanisms at high energy. Also, beam polarization provides new sensitive observables to new physics and helps characterization and discrimination between various BSM models. On the down right, it is an example of the polarization impact at ILC when combined with high luminosity LHC. Again, linear colliders comes with a few technical benefits, like these systems are triggerless, basically you're not suffering from pile-up, you can afford power pulsing for the readout, and so on. ILC is the oldest project of the market, being developed independently in Europe, America, and Japan in 2004 by adoption of after the ICFA recommendation of the so-called cold technology developed at the Tesla project in Europe. It turned into a global project ILC, foreseen to operate from 2500 GeV to 1 TeV center of mass energy, with further options to run precision electroweak physics at a Z-pole and WW threshold. It offered a beam polarization up to 80% for electrons, 30% for positrons, and throughout this talk you will hopefully see numerous benefits of polarized beam and also accessibility of the high energy scale. The total footprint at the first stage is 24.5 kilometers, and the site has already been chosen in Japan, in Kitakami, where again there are years of geological and other surveys in this direction. What is interesting about ILC, it is that it is the project that has the largest ever accelerator prototype operating now as the European free electron laser, with demonstrated full industrialization of the RF cavity production. Now we are in the phase of the international development team being formed, converging hopefully toward preparatory lab in Japan, where first collisions are expected in a similar manner as at CLIC around 2035 if there would be a positive political decision. I would just like, leaning a bit on what Claude said just before me, that ILC comes with, apart from the Collider program, with rich program of auxiliary experiments following the LHC example already mentioned, Phaserev and Millikan experiments at LHC, where dark sector can be probed through parasitic, fixed target, and beam dump experiments. There will be, of the so-called ILCX program, a workshop in the autumn and NKK, and I also cordially invite you to participate if you are interested. Two detector concepts have been developed for for ILC. This is ILD and SID. ILD I would say the mother of all detectors, because every emerging project on the market would start from the ILD, modifying it according to its experimental condition. So it is optimized from energy from the electroweak scale up to the maximal 1 TeV for ILC based on the silicon gas. Tracking both detector concepts rely on particle flow calorimetry, which is basically the major paradigm to enable jet energy resolution, which is approximately 2 times better than ATLAS, and which is essential also for realization of the Higgs physics program. CLIC is yet another very interesting project at CERN of a linear collider, unique in its feature to be only linear collider to go above 1 TeV. Differently from ILC, which is a cold machine, this is based on the normal conductive technology where the high current drive beam is used for power transfer to the main beam, where accelerating gradients of 100 megavolts per meter can be achieved. This is demonstrated, as you can see on the top, in the CTF3 CLIC test facility, now operating at CERN as CLEAR. CLIC that was initially derived from CLIC ILD, but now being more compact with a higher 4 Tesla field with all silicon tracking. Again, it is particle flow paradigm in action. What is a bit different than from ILC, being capable to go in higher center of mass energy. The experimental environment is contaminated with Beamstrahlung photons converted to hadrons. However, they could be nicely suppressed with time stamping, as it is illustrated here. Both ILC and CLIC are mature and well-documented projects. For instance, for your information, I can direct you to full yellow reports from 2018, summarize the vigorous R&D effort over decade at CLIC. But there are 2 speakers at this conference, again, my dear colleagues, journalists from ILC and Aidan Robson for CLIC, who will talk about these particular projects at, I'm certain, much higher level and with more interesting details. The physics program of linear colliders are not definitely constrained to Higgs physics. I'm going to talk about, there is the T physics from top quark mass measurements, electroweak physics, then CP properties and BSM constraints preferred at either low on high or high center of mass energies. And again, BSM physics searches that are, as you're going to see also throughout this talk, preferred by the high center of mass energies. Higgs physics has a few key or major measurements. One are Higgs couplings. They are probably the most studied at linear colliders and documenting in corresponding papers at E+ E- machines. They can be measured in a model-independent way, which is a unique feature in comparison to Hadron machine. Or in the LHC style, model-dependent Kappa framework, or within the EFT approach, which is again almost model-independent and of the realization of any particular new physics model. Then Higgs self-coupling, very important measurement, as well as other measurements in the Higgs sector that could serve as a probe to dark and BSM in general. Also the CPV, possibly realized in the Higgs sector, or all preferred at the higher center of mass energies. When we are talking about the linear machines, and you see that 100 TeV can be reached with proton collider, I would like just to point out with this example, which is a bit off the Higgs focus, that actually the linear colliders, especially at high energies, are superior in probing the physics scale far beyond their kinematic limits. And here you can see example both for ILC and CLIC, where 100 TeV scale can be reached in probing for fermion contact interactions. But as I said, I'm going to focus myself on Higgs physics. There is plethora of processes from Higgs-Strahlung, WW fusion, double Higgs production at high energies. It is interesting that only the first Higgs-Strahlung phase could lead to a significant improvement of the high luminosity LHC measurement when it comes to the Higgs coupling. enabling, as I said, model-independent measurement of the total cross-section for Higgs Z, and the Higgs to invisible, which is again sensitive to beyond the standard model contribution, can be determined by the recoil mass method. WW fusion rising with the rising cross-section at the higher center of mass energy offers superior statistics to probe even rare Higgs decays, while the double Higgs production enables Higgs self-coupling measurements, again, at high energy center of mass energies. So we have here high energy accessible at linear colliders, possibility to have polarized beam, possibility to combine between various channels and polarizations, and all these factors enables linear colliders to access rare processes like the photon decays realized via loop exchange or second generation fermion coupling. High energy advantages are listed here, and I'm giving you a nice example of a study of Higgs to 2 muons decay from ILC, where really the demonstration of combination and polarization is clearly illustrated. So somewhat inferior statistical precision of inferior channels when combined between different polarization and different energies leads to a 17% of statistical uncertainty to probe Higgs to mu decays. This is an example of a pseudo experiment and the pool distribution used to derive this precision. General advantages of E plus E minus colliders when it comes to Higgs physics are the absolute measurements of the Higgs cross-section and branching ratios, as I already pointed out, where the high energy benefits are also clear, in particular when it comes to BSM and the Higgs self-couplings. Higgs self-couplings are the most studied measurements, and here is example for click on the left in the model-independent approach, where the most sensitive to BSM Higgs to electroweak couplings could be measured below 1 precision. Similar example, but from the EFT fit is here for ILC. And you may be wondering what can circular colliders say about this, but more or less precision is comparable. And again, here the synergy with high luminosity LHC measurement is demonstrated. This is, of course, true for linear colliders as well. This is an example from CLIC, improving ultimately high luminosity LHC results in combination far beyond the percent precision, so at the per mil level. And the example here is given for ILC in combination with high luminosity LHC. What I would like to point out that already the lowest phase here illustrated for ILC 250 leads to a large improvement with respect to the high luminosity LHC accuracies. So as I said already in the first phase. One of the really critical measurements in the Higgs sector is the Higgs self-coupling, and high energy collider reaching TeV or more is really superior in determination of Higgs self-couplings. This is illustrated here. CLIC can reach a combined precision of 9%, benefiting from double Higgs production mechanisms, which are, as illustrated on the bottom left, the most sensitive to Higgs self-couplings, while this plot from ILC really illustrates why the higher center of mass energy is important. And again, this is true in case for ILC as well, where by adding 18 Vesato barns at 1 TeV ILC, these are the only experiments to bring down Higgs self-coupling measurement to the 10%. Again, I stole some plots from Aiden, but this is again true also for ILC, not for CLIC, that basically possibility to use various processes, double Higgs production, but also ZHH, due to their different behavior to contribution to the Higgs self-couplings from beyond the standard model physics helps in resolving ambiguity for interference. So if we are going to measure the shape of the Higgs potential, we indeed do need high energy linear colliders. BSM physics can manifest itself in the Higgs sector in several ways. For instance, contribution from higher order from higher order operators that can be addressed in the EFT approach, and this is the example from CLIC. Of course, the smaller the value here, higher the new physics scale to be probed. And here, in an example of from ILC, you can see the scale that can be probed is again of the new physics is again much further from the kinematic limit of the machine itself. How to interpret the EFT results? These are the model listed that basically cannot be probed at LHC and high luminosity LHC. And this top right figure is already telling us that only 250 GeV ILCV2 inverse attobars enables determination of most of the models above the 5 sigma. Again, synergy in action. If we add high luminosity LHC projected sensitivity, basically there won't be a model that could be confirmed or disfavored by in combination of these experiments. Then one possibility for BSM is extension of the Higgs sector. Higgs could be extended, and these extensions come in the majority of BSM models, either in the form of a lighter scalar that is lighter than the standard model Higgs, or if the standard model Higgs is lightest, other states are nearly mass degenerated, so future colliders should be capable for probing this. This is an example of a single light scalar production associated with Z at ILD, while in the case that heavy singlets, that the singlet states, scalar states are heavy, the click is really superior at high energies in measuring the standard model Higgs mixing angle with such a heavy single state. So extended Higgs sector, both light and heavy, could be probed with high energy linear colliders. Then one may ask a question, is dark matter somehow connected with Higgs and the standard model particles? The answer is yes. The possible connection could go through a set of specific operators called portals, and such particles should be, let's say, visible through the Higgs invisible with measurement, or anomalies in the Higgs invisible with measurements. This is a nice example from Higgs strong at 250 GeV ILC, where basically nothing is recoiling against the Z boson, enabling the measurement in the full ILC running with precision below 0.5%. Also, one of the possible manifestation of the BSM is a very intriguing possibility that CP violation is actually taking place in this Higgs sector, where the light Higgs could be a quantum superposition of the pure scalar and pseudoscalar states, can be measured both in fermionic vertices that are receiving contribution on the 3 level to the Lagrangian, and thus they are more sensitive. All these projections that you can see in the table here are from Higgs to tau-tau channel. Again, ILC has superior precision of measurement up to 4%. This is a nice example of a pull experiment from one of the ILC samples, where again, combination between various polarization and various channels leads to this ultimate precision. Then my colleague Daniel Jeans will talk also in this conference more about this measurement. I would also like to point out that although with smaller sensitivity, Higgs to vector boson vertices can be probed, and such an ongoing analysis is in HZZ vertex at 1 TeV ILC. Let me come to my summary. I really have to go through all these points because I think they are important. All future projects bring significant added value to the projected high luminosity LHC sensitivities in the Higgs sector. And with the features they are bringing in, like the high energy scale and polarization, they are enabling discrimination of the BSM models that are inaccessible at high luminosity LHC. Already in the lowest phase, they are far more sensitive than high luminosity LHC when it comes to the Higgs couplings, but higher center of mass, which are, in my opinion, a genuine advantage of linear colliders, are bringing deeper understanding to the Higgs potential shape, to Higgs self-couplings, and also through BSM realizations that could impact the Higgs physics. And other very important message to take is that these are ready-to-wear projects with proven technologies and years of studies, and basically they both will rely on a political decision to provide first collisions in 2035. Thank you very much for attending.
Thank you very much, Professor Bozovic. We are a little bit beyond the schedule, but still, if there is an urgent question, please ask your question.
No.
Okay, I don't see any, so thank you very much for interesting overview.
Yeah.
And we have now short break until 11:25 European time.
Valeria, thank you very much for the nice presentation of the first plenary session. And I would like to suggest to start 12:30, just 5 minutes later than in time schedule. Yeah, to have a little bit 5 minutes more for this break. Yeah, but thank you very much again to everybody and to the chairman. So, and we shall start the next session at 11:30, and Joaquina will be the chairperson. Well, thank you very much.
Okay, thank you.
Okay, so Alexander, I think that we can start the new session.
Thank you. Yeah, we can start, please.
Okay, so we proceed with this morning's session. So the next talk is from Jose Valle from IFIC, CSIC University of Venezia. The title of the talk is Neutrinos as a New Physics Pathfinder. So please.
Hello, everybody. First, I wish to thank the organizers for their kind invitation. My task here is to illustrate the key role neutrinos can play in helping us make the next step forward in particle physics. And I start from the discovery of oscillations in solar and atmospheric neutrino experiments. And these were followed by reactor and accelerator-based experiments, which have not only confirmed the oscillation phenomenon, but also improved the parameter determination. So much so that today we have a pretty reasonable determination of the lepton-mixing parameters, the leptonic analog of the CKM matrix characterizing the quark-wake interactions, except for 3 points. First of all, we still lack a robust determination of the atmospheric octant, the angle theta to 3. We certainly lack a good measurement of CP violation. And finally, we have an ambiguity concerning the ordering of the neutrino spectrum. And in fact, these form the target of the next round of experiments. And we will have a dedicated talk tomorrow. So I will not go into these, but instead I jump directly to theoretical interpretation, starting from the 3B maximal ansatz. You have maximal atmospheric mixing, 3 maximal solar mixing, no reactor mixing, hence no CP violation. Although TBM is no longer viable, it provides a good starting point for systematic generalizations one can make exploiting symmetries, so as to produce 2-parameter patterns which are not only viable, but also predictive. For example, this one, you see here the prediction in green, how it overlaps the generic oscillation region over a very narrow range on delta CP. And as I said, this is just one out of a broad class of possible examples. I now turn to bilarge lepton mixing. This pattern was suggested exploiting the fact that the largest quark mixing, namely Kabibu, is similar to the smallest, namely lepton mixing, namely reactor. This way, the lepton mixing matrix is power series expanded in lambda. So if you know lambda, you know them all. And indeed, you see here the solar neutrino prediction, very tight prediction. And likewise, in blue, you see the atmospheric neutrino prediction. Again, this is one example out of a class. This brings me to neutrinoless double beta decay, a very important process because it is associated to the Majorana nature of neutrinos. And it allows us to access parameters which we cannot within oscillation experiments. One is the third neutrino mass parameter. Oscillations depend on only 2 mass splittings. This involves the third mass, and also it involves the 2 Majorana phases, which are inaccessible in oscillation experiments. Notice here that I'm expressing M beta beta in our original parameterization, the symmetrical parameterization of lepton mixing of 1980, which is much better when it comes than the PDG choice, when it comes to describing neutrinoless double beta. The most favorable situation would be when the three neutrinos are nearly degenerate. In this case, I can express M beta beta in terms of this dimensionless parameter eta, so that when eta is 1, neutrinos are strictly degenerate. That's the vertical line. In real life, one must depart from the idealized limit, either going left into normal ordering or right into the inverted ordering branch. We have the brown horizontal band from Kamlan-Zen. That is just the limit that follows from neutrinoless double beta decay search. And recently we analyzed the cosmological data and showed that they rule out this vertical band shown here. So altogether, cosmology severely disfavors quasi-degenerate neutrinos. Another interesting possibility is when we have one of the neutrinos massless. In this case, there can be no destructive interference amongst the light neutrinos, and one has a lower bound even in the case of normal ordering. Unfortunately, though, this lies below the foreseen sensitivity of the next round of experiments indicated by these dashed black lines, so that we move back again into the orange band corresponding to inverted ordering, but which in contrast to the generic situation up there is much more restrictive, and it is fully covered by the expected sensitivity of experiments, so that one can entertain the possibility of underpinning the value of the Majorana phase. What if all neutrinos are massive, though? In this case, we have no guaranteed lower bound. Yeah? As you can see here in these green references, it often happens that in the presence of family symmetries, more often than not, there are lower bounds for neutrinoless double beta decay. And I give an example down here from a very recent JHAP paper illustrating how, in fact, the preferred value lies within experimental sensitivities. Of course, an eventual discovery of neutrinoless double beta decay would signify a major achievement in particle physics. First, it would imply the discovery of lepton number no conservation, but also by use of the black box theorem, it would imply that at least one of the neutrinos is a Majorana particle. And this will be a double discovery, which would really be very, very, very important. The importance of this theorem, I should stress, also applies to the context of high-energy collider experiments. This brings me to the issue of the origin of neutrino mass. It was noted by Weinberg that to the standard model, one can add a unique operator with dimension 5, shown here, so that, violating lepton number by 2 units, so that when the Higgs doublet goes into its vector expectation value, one generates a Majorana mass for neutrinos. The art of neutrino model building is precisely the art of UV completing this argument. Perhaps the most popular UV completion is the seesaw mechanism, from my point of view, because it opens up the possibility of a dynamical understanding of small neutrino mass, following from minimization of the Higgs potential. And in fact, the extra expectation values associated to neutrinos may hold the key to the stability of the electroweak vacuum. So this may touch the very heart of the electroweak theory. Within the seesaw picture, then the masses of the left-handed active neutrinos, their smallness can be understood as a result of the exchange of heavy right-handed neutrinos, type 1 seesaw, or heavy triplet scalars, type 2 seesaw. It is anecdotal here that in our original formulation in science, we called type 1 seesaw the triplet seesaw, because we are fascinated by the simplicity of the triplet seesaw, and also that was our baby. However, we did provide the most general analysis of type 1 seesaw ever in the literature up to today. And to understand that, I show here in yellow the statement that the yellow seesaws were based on left-right symmetry. So their type 1 seesaw must have the number of right neutrinos match the number of left neutrinos by gauge symmetry. In contrast, our standard model-based seesaw, type 1 seesaw, allows for any number of singlet neutrinos. For example, you can have a missing partner seesaw in which out of the 3 left-handed neutrinos, which we know exist, we could add only 2 right-handed neutrinos, 2 singlet neutrinos. This means that one neutrino misses its partner and it remains massless, and this leads to the bound on double beta decay. On the other hand, this seesaw is all we need to explain solar and atmospheric oscillations. So to date, this is still the simplest viable type 1 seesaw model. We also discussed the 3-1 possibility of having only one singlet neutrino, one right-handed. Again, you have the double beta bound, but in this case, you have only one 3-level mass from the seesaw mechanism. So solar neutrinos have no mass splitting. They are completely degenerate. That degeneracy can be lifted by some other mechanism. And it is especially interesting the case of a radiative mechanism, because in that case, one would have an understanding of the hierarchy between the solar and the atmospheric splitting in terms of a loop factor. And that is precisely what is done by the recently discussed Scotto seesaw, which is a combination of the seesaw paradigm for neutrino mass with the wind dark matter paradigm. Conversely, also in our old paper, we noticed the possibility of having more singlet than doublet neutrinos. And there is a especially interesting example of that when the number of doublets is twice the number, the number of singlets is twice the number of doublets. So you add 2 singlets sequentially. This model, in the limit of left-hand number conservation, has strictly massless neutrinos, as in the standard model. However, and this is extremely important conceptually, its charge current weak interaction matrix, the lepton mixing matrix, violates flavor and violates CP symmetry, despite the masslessness and degeneracy of the light neutrinos. This is interesting conceptually and practically, because it means that, for example, mu2 gamma as a process is not suppressed by the small neutrino masses. It can be associated to physics complementary to that of the neutrino mass. From the point of view of neutrino masses, this limit is the template upon which one builds low-scale seesaw, either inverse or linear seesaw. The idea is that you have a blob violating lepton number, and that gets transferred in the form of Majorana mass for the left active neutrinos as a result of the exchange of quasi-Dirac heavy neutrinos, whose mass, however, can be accessible at the LHC. So this is the whole idea of the inverse. And the important point is that small neutrino masses are symmetry protected, and they are protected by Toft's argument. In the limits, in the symmetry limit, neutrinos get massless. In fact, the protection can be a double one if this blob itself emerges as a calculable one in terms of yet another layer of physics, such as dark matter physics. And here we have again a novel way of reconciling the seesaw paradigm with the WIMP dark matter paradigm, and the resulting theory may be called dark inverse seesaw. Seesawing is not a feature present only for Majorana neutrinos. You can also seesaw on a Dirac. This is Dirac type 1, and these are Dirac type 2 diagrams. The main point again is symmetry protection for the mass, and also in this case, symmetry protection for a Diracness of neutrinos. In particular, the protecting symmetry for Diracness, which in some models is also a protecting symmetry for dark matter stability, could be, for example, the Pechet-Quinn symmetry, as recently discussed in this physics letters paper. Now I turn to the flavor problem, a corner of particle physics where the standard model fails miserably, as it lacks an organizing principle in terms of which to understand family replication and fermion mass and mixing parameters. And at this point, one must stop and recognize the legacy of oscillation. Oscillations demonstrated not only that leptons mix, but also that they do so rather differently from the way quarks mix in the weak interaction. And this constitutes one aspect of the flavor problem, which cries out for a theoretical explanation. The other side of the flavor problem, which also calls for theory explanation, is this odd pattern of charged fermion masses. Nobody has a solution to the flavor problem. However, as a consequence of the legacy of oscillation, there has been a tremendous effort in seeking for models of flavor that could perhaps shed light on the structure of the mixing. And even though all these models are interesting, none of them is interesting enough that one may say, well, this is it. This is the model of flavor. No. However, one finds that all of them converge into a very simple and elegant and successful unification, bottom-down unification formula involving all the families that I showed. So we believe that this golden mass relation forms part of the ultimate solution to the flavor problem. But the problem itself is so complex that perhaps one should seek for its solution outside the confines of four-dimensional field. This is an example of warp dimension, which has been suggested as a solution to the gauge hierarchy problem. It can be upgraded into a solution to the fermion mass hierarchy problem, although that would be a tremendously difficult mathematical problem. Masses will be geometrical. However, the other side of the flavor problem is the mixing. And to the mixing, we can apply our old phenomenology trick of predicting the mixing from family symmetry. Family symmetry can be imposed in warped flavor dynamics. And these predictions here are nothing but the three maximal prediction, which already existed before. They are now obtained from this family symmetry. And going to double beta decay, we have very tight prediction. In fact, this model, its parameter space for normal and inverted ordering indicated in blue and red can be fully covered by the next round of experiment. And this is the corresponding oscillation prediction coming from three maxima. This, for the case of warp extra dimension, one also has a flat extra dimension, for example, orbifold, which are flat except for the singular points. A six-dimensional orbifold compactified on the torus has the unique opportunity of dictating what is the family symmetry in four dimension. That symmetry is in four. That symmetry leads to the golden formula. That symmetry predicts the sign of CP violation. And that symmetry predicts neutrinoless double beta decay. So this brings me to my conclusion. Oscillations brought neutrino to the spotlight. We have a vibrant program to measure CP octet ordering and perform unitarity and NSI tests. Searches for double beta decay proceed, and we have a new window into neutrino properties and new physics provided by the historical discovery of coherent electron neutrino nuclear scattering. All my theoretical comments, I have already made them within the talk, so you are free to ask me if you have any questions. Thank you for your attention.
Thank you, Joseph, for this nice talk. And now we have 1-2 minutes for questions. So it seems that there are no questions, so we can move ahead to the next contribution from Joseph Formaggio, Massachusetts Institute of Technology. The talk is a direct measurement of neutrino mass. So please, okay, you can start.
Evening, good afternoon, and good morning to everyone. It's my pleasure to give you a brief overview of direct neutrino mass experiments. As we heard from the previous talk, oscillations have had a huge impact on our understanding of the standard model. And one of the main outcomes of almost 4 decades of experimental observation of oscillations is that we now know that neutrinos have mass, and there are predictions that come from that observation that we're now exploring. And one of the key factors is that although oscillations tell us that neutrinos have mass, they cannot reveal the neutrino mass scale, and this is still an unknown within the standard model. And so one question you could ask is, how do we access the neutrino mass scale? And there are a number of indirect ways in which we can provide that information. Although oscillations themselves don't provide information about the scale, they definitely reduce the parameter space that we have to explore. We no longer have to deal with 3 eigenvalues that we need to solve for. But the fact that they all oscillate means that if you're able to measure one aspect of the scale, say, for example, electron beta decay, then all of them are connected. And as we heard from Vali's talk just a few minutes ago, essentially everything boils down to everything boils down to having a single mass scale that's unknown, and an ordering that is yet to be determined. I'm trying to advance my slides, and it's not working at the moment. There we go. Okay. The second way where we have access to the neutrino mass scale is by looking at the Majorana mass of neutrinos, and this is explored by looking at neutrino double beta decay. This is an ambitious effort worldwide in order to see this process, because not only does it reveal information about the mass scale, but it also reveals that the neutrinos are Majorana particles, and therefore a lepton number is not conserved. The next generation of experiments will certainly surpass the inverted scale of neutrino masses. However, even if we observe this process, whether in the next generation or the next generation of experiments, there's no guarantee that that information will reveal the mass scale. And that's because other mechanisms aside from the neutrino mass could provide that, that signature. And there's a lot of ambiguity as well in interpreting the lifetime of neutrino double beta decay to the mass scale itself. So although this is certainly worthwhile in its own right, it's not a direct way in order to measure neutrino masses. Cosmology provides another lever arm in trying to understand neutrino masses. And this can be done by looking at the remnants of the Big Bang through the cosmic microwave background, the distribution of clusters of galaxies, the Lyman alpha forest. And in fact, there's been some very interesting limits that have been set by the most recent experiments that place the neutrino mass scale all the way down to below 0.2 eV on the sum of the neutrino masses. And what's really exciting is the next generation of experiments hope to probe all the way down to about 50 milli eV or even lower. However, this comes as a result of a very large model of the cosmic microwave background and the cosmological evolution. And therefore, there is a number of degeneracies and parameters that one needs to fit in order to extract the neutrino mass. So although these are certainly the forerunners in terms of sensitivity for these experiments, and certainly over the next decade, it would need to be followed up by a more direct measurement if we're to ascertain that this is definitely a signature for neutrino masses as opposed to misunderstanding of cosmology or new physics. So that leaves direct methods as a base, and by direct methods, I mean kinematic methods of determining the neutrino mass, essentially determining whether the dispersion relation holds for neutrinos. And the first suggestion of this was made in the 1930s by Perrin, and followed up independently by Enrico Fermi in his paper in 1934, where he lays out weak decay. And already he sketches out the basis of direct measurements in this paper, where he draws the endpoint spectrum of beta decay. And he infers that if we are able to observe the shape of this endpoint, the neutrino mass affects the phase space near the endpoint, and the shape itself should tell us about the neutrino mass itself. In fact, he already determined, based on the data back in 1934, that it must be much lighter than the electron mass. Nowadays, we look at the either the beta decay of, say, tritium, three-body decay, where we observe the electron, or we look at electron capture, where the electron is captured within the atomic shell and releases energy in the decay process. Both of these have a neutrino sensitivity to neutrino mass near the endpoint, and it's because the rate of decay near the endpoint is proportional to both the neutrino momentum and the neutrino energy. So a slight variation, i.e. the presence of neutrino masses, is essentially sensitive to all mass eigenstates, in an incoherent sum. And as long as your detector is not superly fine resolved in order to tell the mass splittings, we usually absorb this into a single parameter, which you call M beta, which is the incoherent sum of the neutrino masses. So to observe this, we first have to pick a source, and the best leverage is done by looking at the lowest endpoints possible. That's where you have the highest phase space for seeing these events. That leaves basically tritium, holmium, rhenium, and more recently, it's been shown that indium and cesium-135 have very low endpoints as well. If you look at the details of each of these 5 possibilities, the indium and cesium certainly look interesting, but their branching ratios and decay rates are incredibly small. So you need a very large amount of material in order to make a dent on seeing even having enough sufficient statistics in order to observe events near the endpoint. And effectively, that leaves 2 players for determining neutrino masses, and that is tritium and holmium. And in fact, those are the efforts for today's leading experiments. So once you've picked a source, then you have to pick a technique. And there are essentially 3 techniques at play in this decade. One having to do with calorimetry, one on electromagnetic calibration, and then one that is frequency-based. I'll start with the calorimetric one for starters. And this is basically the idea that if you have an implanted either beta decay or electron capture isotope, in this case, I'll pick holmium-163, then when it decays, you deposit all of the energy onto your absorber. And usually this absorber is cryogenic, sitting at temperatures below 100 millikelvin or less. So these are very small detectors that operate at cryogenic temperatures. And if you attach them to a highly sensitive thermal detector, then you can convert that energy into a thermal pulse that you then measure in your detector. And that allows you to extract the energy deposited with very high accuracy. Early experiments that were done with rhenium were done with semiconductors and superconductors. This had the additional advantage of having the capacitance, which is your lever arm for your temperature, scaling like the cube of the bath temperature. More recently, calorimetry experiments have used gold with holmium implanted in them. And although the temperature scaling is not as good as semi and superconductors, these are much easier to handle and certainly have enough energy resolution. And if you look at the endpoint of the electron capture, although you're dominated by the resonance lines, if you concentrate near the endpoint, you get the same phase space factor as you do for beta decay and has sensitivity to neutrino mass. The current incarnations of this experiment can be found in the Holmes experiment, which is based off of Italy, and the ECHO experiment that is mainly focused in Germany. These both use holmium-163 and implanted in gold in order to extract their experiment. They differ in how the holmium is created and how the temperature readout is made. In the Holmes case, they use transition edge sensors in order to measure these energy depositions, whereas ECHO uses MMCs in order to achieve a similar resolution. So for these experiments to work, you need a very high energy resolution, both of which have been demonstrated with both technologies. So you get exquisite energy resolution and timing from these microcalorimeters. So a lot of progress has been made in the past few years in order to realize this. Also, because you're dealing with small detectors with limited activity, you have to multiplex all these experiments. So we're talking about hundreds of small detectors being read out at once, both which collaborations are pushing on. And the first generation of these experiments will have results soon with an aim at the EV scale. In fact, we'll hear from Loredana Gastaldo on Friday that she'll tell us about the update for these microcalorimeter experiments. So expect to hear more from her in the next day. So the second technique that we'll explore is using electrostatic and magnetic filtering. This is the basis of the Catron experiment. The principle is that you want to have high efficiency for collecting your electrons from isotropic decay. And to do that, you immerse your target, in this case, it's tritium, inside a magnetic field that causes the emerging electrons, which are low energy, to be pointed toward your detector, thus having a high efficiency for detecting those electrons. And then you drop the field adiabatically to very low, sort of from Tesla to Gauss, and you apply an electric potential, and that allows your system to act like a high-pass filter, only allowing electrons of a certain energy to pass through. And then if you scan the system, that allows you to explore the spectrum. And essentially, this is an integrating spectrometer. This principle is the basis of the Mackey filter technique that's used by this approach. Certainly, it's the one that's used by Catron right now, and its predecessors being the Mainz and Troyes experiments, both of which their previous limits over 3 years of data taking gave us our current direct mass limit of about 2 eV. The Catron experiment is now taking data. It's a colossal 70-meter experiment with a high throughput source of tritium gas and a very large spectrometer that does this event selection. The first results from the data campaign in 2019 were released, and you can see the very high agreement between the beta decay model and the data. Those error bars are multiplied by a factor of 50. This gave us a limit in just a few days, about a month of data taking, to a mass limit of less than 1 eV. Just about 1 eV. And then more recently, we released our second batch of data, again with very good agreement with the model. And as you'll hear on Friday, the update on the mass limit has improved to less than 1 eV at 0.8. So you'll hear about this development also on Friday's talk. In the outlook, right now, Catron definitely is collecting more and more data. We're just at the beginning of this process. We're trying to reduce backgrounds and assess systematics with its final target sensitivity of about 200 millielectron volts. So as Vali said in his talk earlier, we'll be able to rule out the quasi-degenerate scheme very quickly. And certainly if we see a mass level, a mass of this limit, we should be able to make a claim. Finally, a third technique that's in play is using a microwave detection for measuring the beta decay spectrum. This is the technique used by the Project 8 experiment. It uses cyclotron radiation in order to detect and measure the electron's energy. The basic principle is that if you have an electron that's come from a beta decay in a high magnetic field, it undergoes cyclotron radiation motion and then releases microwave photons as a result of that radiation. So you can convert those microwave photons into a kinetic measurement of the electron, since the energy of those electrons and the frequency that they emit their cyclotron radiation is inversely proportional. At 1 Tesla, this is about 28 gigahertz or so in terms of the frequencies that we're interested in, and it releases about a femtowatt of power. This technique was demonstrated about 6 years ago the idea is that if you look at the power versus frequency, and if you have an and just to orient you, frequency going up is energy going down. And you see a sudden onset of power if an electron appears in your system. That's the presence of an electron, and the start frequency tells you the start energy of your electron. You can also observe the radiative loss as the electron loses energy from cyclotron radiation, and even single scatters of electrons in the hydrogen. After its demonstration using a calibration source known as Krypton 83, we moved on to a vessel that can contain a small amount of tritium. This is a picture of the Project 8 vessel that has a waveguide that collects the microwave photons, and there is a tritium gas cell inside that provides the decay electrons. And if we can orient our detector so that it has very high energy resolution. What you see on the top is the resolution of the krypton line, and that resolution is about 2 electron volts. Then we move to a much a configuration that has lower resolution but higher acceptance, and allowed us to collect our first tritium spectrum, which you see on the bottom. One of the key features of this spectrum, even though the statistics are low, is that we see no background past the endpoint of the spectrum. And in fact, this technique tends to have very low backgrounds associated with it, which is a good plus. The Project 8 experiment is moving to a much larger detector. So they're moving into what they call phase 3. So going from cubic millimeter detectors to centimeter and meter cubic volumes. So this is the plan for the next generation of this technique. And efforts are underway to develop an antenna array in order to image electrons in position as well as energy. For a future experiment, however, experiments like Hadron and Project 8 will come into a wall, and that comes from the fact that both of these experiments don't use tritium per se, but use molecular tritium. And molecular tritium has a complex final state distribution that's due to the rotational and vibrational states of the molecule. And although calculations provide a very good model of what those states look like, they inherently add a broadening that's difficult to overcome. And so an ultimate experiment should really move from a molecular source into an atomic source. And this is really needed if we're going to access the inverted hierarchy scale and go beyond the degeneracy scale that we currently are aiming for. And you can see immediately the advantage of going to an atomic source. On the bottom, I show the distribution of the final states for the endpoint of molecular tritium. You can see the broadening of states and roughly half of an EV of broadening. On the other hand, a purely atomic experiment is basically limited only by the thermal broadening of the gas. And so it's far more favorable and accurate if you can do an atomic experiment. This displays itself on the sensitivity. If you look at the limits for an ideal experiment as a function of volume, molecular sensitivities peter out around where Hadron has its limit of about 0.2 EV. But an atomic experiment is not limited in such a way and could reach down to the inverted scale. And indeed, this is one of the focal points of the final phase of the Project 8 experiment, what we call phase 4. Assuming that we understand our systematics, we hope to push down to the degeneracy scale at about 40 milli EV by taking advantage of this CREST technique in a large volume with atomic tritium, and R&D is on effort to that. If you combine that with other with our current limits now, so current experiments definitely have broken the EV scale. And as you'll hear also on the details on Friday, that our current limit is well below 1 EV and pushing down to the 100 milli EV scale. And in the future, we'll have experiments from Katrin, Echo, and Holmes hope to push all the way down to remove the inverted scale, and to hope that a future atomic experiment could even push down to the inverted scale for these kinds of experiments. So this is actually a pretty good decade to access direct neutrino mass experiments. There are a number of exciting measurements that are underway from both Katrin, Echo, Holmes, and Project 8. And so we hope to illuminate the neutrino mass scale much further as we go forward. Okay, thank you for your attention, and I'm happy to take any questions.
Thank you, Joseph. Thank you for this very nice talk. We have now time for a couple of questions. I have a curiosity more than a question. You mentioned the past effort on rhenium, which now apparently is an abandoned isotope. Can you remind why technically rhenium has been abandoned?
So one of the issues that was observed is that, so in the crystals that were used, these are, sitting at cryogenic temperatures, so you're very sensitive to the phonons that are created. As the electron was produced in the system, it would interact with the environment. So I believe it was the MyBeta experiment, but I think both MyBeta and Manu observed this effect, where if you plot the spectrum, you would essentially, and you took out the beta decay shape, you would see essentially a wiggle in energy that had to do with the environmental and interaction of the electron with the crystal. And so this is, although qualitatively you can predict this effect, it's very hard to have such an environmentally based on your crystal geometry systematic in your setup. And so since all of these really depend on understanding the shape near the endpoint, this was seen as a serious systematic that couldn't be overcome. And the second, of course, is that rhenium is one of the most expensive metals on Earth. So a large crystal experiment would be quite expensive. I think that with the combination of the holmium advances kind of moved the community from concentrating on rhenium to concentrating on holmium. And I'm sure Loredana Gastaldo can, who was really, the pioneer, one of the pioneers of this effort, can provide her own perspective on this. But that's my interpretation of why the community moved from rhenium to holmium, and I hope I said that right.
Thank you, Joseph. By the way, we have in the chat a question from Loredana. She writes, thank you for the very nice overview on direct neutrino mass measurement. I would like to ask if you would consider Ptolemy also an experiment which could provide information on the effective neutrino mass.
Yes, so Ptolemy is a very ambitious experiment. They want to resolve grams of tritium in order to look for neutrino capture using embedding tritium on a substrate. I believe they are using carbon as a substrate, although I'm not 100% sure. Any experiment that aims for that should also have sensitivity to the neutrino mass. So if their technique can be demonstrated and shown to have the accuracy that they envision, then they would certainly be players in this in this field. And so a demonstration of the technique to show they can achieve resolution and this loading of atomic tritium could be very interesting for neutrino mass, future neutrino mass experiments. And I know they have an effort ongoing to try to explore the different challenges of that kind of experiment.
Okay, thank you, Joseph. I think that now we can close here your talk and move to the next talk. So the next speaker is Michael Klasen from University of Münster. The talk is about absolute neutrino mass as the missing link to the dark sector. So please, Michael.
Yes, thank you. Can you hear me and see my slides?
Both. Please
Great.
go ahead.
Okay. So, Dobry den from the University of Münster, ladies and gentlemen. I would first like to thank the organizers also for inviting me to speak at this prestigious conference. And the title of my talk, as you just heard, is Absolute Neutrino Mass as the Missing Link to the Dark Sector. In other words, I will address the question what the impressive progress on the upper limit and the future measurement of the absolute neutrino mass scale with Hadron or subsequent experiments that we just heard about will teach us about the mass and properties of the mysterious dark matter in our universe. Our work has been published as a rapid communication in Physical Review D and has been obtained in collaboration with a master student and 2 PhD students within our local research training group, whose hallmark is the close collaboration of theorists and experimentalists. And this is exemplified in the participation of Caroline Wodenbeck, who is a member of the Hadron collaboration. So to introduce the topic, let me remind you that today we have impressive evidence for the existence of dark matter from many different length scales, which requires even alternative theories like those with modified gravitational interactions to include a dark matter particle component. To start with, on the galactic level, rotational spectra of stars and hydrogen gas, like the one of the Triangulum galaxy M33, which you see here in the top left corner, remain flat out to large distances, while the gravitational attraction of the visible interior mass is insufficient to balance the centrifugal force. On the level of galaxy clusters, we have the famous picture of the bullet cluster on the top right, demonstrating the separation of hot interacting gas emitting X-rays and observed with the Chandra X-ray telescope from the collisionless dark matter observed with gravitational lensing. Third, on the bottom left, numerical simulations of the large-scale structure of the universe and comparisons of those simulations with observations show that small structures form first, indicating that dark matter must be cold and not hot. And finally, the measurements of the power spectrum of the full sky cosmic microwave background with the WMAP and Planck satellites provide us with a precise value for the dark matter relic density in the universe, which is 0.120. So we clearly have this evidence for dark matter from many different length scales. And we know dark matter exists. And from the Planck measurement, we also know that the density of baryonic matter is only 0.022, so that dark matter is about 5 times more abundant than ordinary matter. And because of the gravitational effects and the fact that we don't see it, we know that dark matter must be at least, and perhaps, if we're unlucky, only gravitationally, but not electromagnetically interacting. From structure formation, we learn that it should be cold, with some indications from the so-called missing satellite problem, i.e. the fact that we do not observe the expected number of dwarf galaxies that might have a warm component. We also do not observe many machos, massive compact halo objects, and there are limits on the contribution from primordial black holes to the dark matter, which show that they should be below 10%. So the wide-held view is that dark matter must be a new heavy elementary particle. Possibly, of course, there could be a whole dark sector. And a prime candidate has been for a long time the weakly interacting massive particle, or WIMP, due to the miracle, so-called miracle, that when you take a particle of weak scale mass and interaction strength, you automatically obtain the correct relic density. On the other hand, the standard model contains WIMPs. Neutrinos are only weakly interacting, and we know from the oscillation experiments that at least 2 neutrinos have non-zero mass, although they are very small. But these standard model neutrinos are very light, so they are neither cold dark matter, nor can they contribute more than a small fraction of about 1% to the cold dark matter relic density. We have also seen that there is a lot of information already on the neutrino masses and mixing angles, the solar mixing angle and the atmospheric mixing angle being much larger than the reactor angle, which, however, is not zero. And we also have 2 mass differences squared, with one larger than the other. We also have a measurement of first value on the CP violating phase. But what we do not know yet is the hierarchy of the neutrinos, although there are some indications by T2K and NOVA that normal ordering might be preferred with respect to inverse ordering. So I give these values here. About the absolute neutrino mass scale, we don't have a measurement yet, but from the oscillation results, we know that there is a minimum on the sum of the neutrino masses of about 0.06 electron volts. We have already heard about the quasi-degenerate regime, when the neutrinos are above 0.2 electron volts. The differences don't matter that much anymore. We've seen that this 0.2 electron volt is also the Catrin sensitivity goal. The published upper limit that we used in our work was the one from this 2019 PRL of 1.1 electron volts. We now have a better limit even from Catrin of 0.8 electron volts. And if you believe the lambda cold dark matter cosmological model, you can obtain also from the Planck measurement this upper limit on the neutrino masses of 0.12 on the sum of the neutrino masses. Now, the question is, how are these neutrino masses generated? And in Jose Valle's talk, we already briefly heard about the possible and intriguing connection that the mass generation might be linked to dark matter. And this is the idea of the so-called scotogenic models, where scotogenic means that the masses are created from dark matter. They are a particular type of radiative seesaw models, so not tree level, but at least 1 or more loop level, where the mass is then generated and then naturally suppressed by loop factors, which brings down the C-score scale from 10 to the 9 GeV or so to TeV, and therefore into the observable range also of the LHC, for example. And the idea in the scotogenic models is that at least one of the particles in the loop is a dark matter candidate. Now, the one loop realizations of this dimension 5 Weinberg operator have been classified for the dark matter models in this paper by Restrepo from 2013. We have these 4 different topologies, which where the neutrino at the bottom is always connected to the standard model Higgs field at the top. And in the loop, we have different particles. There are triangular topologies and box topologies. And so these are the full list of possible one loop realizations. And of course, there are simpler ones and more complicated ones. And the restriction here in these models is that we add up to 4 new fields at most, that we assign stabilizing symmetry which is typically a discrete Z2 symmetry, so that there is no tree-level seesaw mechanism and that dark matter becomes stable. They're usually taken to be singlets of QCD in order to avoid the generation of bound states, which would have a lot of strong interactions. And in terms of the weak quantum numbers, they can be singlets, doublets, or triplets. And the hypercharge is assigned such that there is at least one neutral candidate, which is the dark matter candidate. Now, the simplest of these models is the famous scotogenic model introduced by Ernest Marr 15 years ago. It is the simplest in terms of particle content. It is also of this triangular topology, which is the simplest of the topologies. And if we denote the standard model lepton doublets with the letter L, we only have to introduce two types of particles, which are both odd under this Z2 symmetry. The first is a complex Higgs doublet denoted by eta, which is inert because it's Z2 odd, and it does not acquire a vacuum expectation value in order to preserve the Z2 symmetry. And the second type of new particle is a sterile neutrino, a fermion singlet, where you need at least two generations to create two non-zero neutrino masses, and a lot of the literature has focused on this. But here we are interested in the absolute neutrino mass scale, so we of course want 3 generations to create 3 non-zero neutrino masses. And in our work, we consider the lightest neutral fermion to be the dark matter candidate, and we will see later why we do this. It could also be the lightest scalar, and this has been studied in many other different works. So, which is then, the phenomenology is then similar to the inert doublet model phenomenology. The Lagrangian of this scotogenic model, apart from kinetic terms, contains a Majorana mass term for the sterile neutrinos, which couple through Yukawa couplings only, and they couple to the standard model leptons and the inert doublet. These Yukawa couplings will be 3x3 matrices. And of course, there is also a limit from perturbativity on these Yukawa couplings, which we take to be 4 pi. And there is also a scalar potential for this 2 Higgs doublet part. We denote the standard model Higgs doublet by the letter phi, and of course, it obtains a vacuum expectation value in order to break the electroweak symmetry. And the most general form of this potential is then given here. It has a mass term and a self-coupling for the standard model Higgs field as usual. But it also has a mass term and a number of couplings for this second Higgs doublet. In order to preserve the vacuum stability, one has to impose a number of other constraints on these couplings. And similarly to the Yukawa coupling, one imposes a perturbativity bound on these scalar self-interactions. So there's quite a number of parameters in this model, which makes the parameter space numerically time-consuming to study. Some of them can, however, be fixed, or some are more important than others. In particular, the standard model, scalar mass parameter and self-coupling are fixed by the well-known value of the vacuum expectation value and the Higgs mass measured by Atlas and CMS. So this fixes m phi and lambda 1. And there's another parameter which does not play a relevant role. This is the lambda 2 parameter. Since there is no vacuum expectation value for eta, this lambda 2 only introduces conversions within the scalar sector and does not really affect the phenomenology. If we now translate the parameters of the model into physical masses, we have 3 scalars, the charge scalar and 2 components of the neutral scalar, the real and imaginary part, which depend on the eta mass parameter and the lambda 3 or lambda 3, 4, and 5 couplings proportional to the Higgs wave due to the interactions of eta and phi. And it turns out that the mass differences, if you look here at the difference between the two scalar components, depends only on lambda 5. And now if you look closely at the Lagrangian, you observe that the limit of lambda 5 being exactly 0 introduces a new symmetry of the model. It would imply lepton number conservation. You could assign lepton number to the new scalars and sterile neutrinos. And it would also imply that the neutrino masses are exactly 0. So in fact, because of this new symmetry, it is natural for lambda 5 and this mass difference to be small. And in line with previous work by Vicente and Laguna, we scan over this range indicated here. So this model is actually not that complicated, but it contains a number of parameters that have to be taken into account and constrained by our experimental knowledge from different corners. And this is, of course, the challenge to take into account constraints from different experiments. So we start with the lab limit by Opal on charged particle masses, which focus, of course, on supersymmetric particles, but which generalize also to non-supersymmetric particles and showed that they must be heavier, these new particles, either scalar or fermionic, than about 100 GeV. And in this case, if this, an eta parameter is larger than the VEF, in much of the parameter space, then of course it dominates over the other parameters, in particular the couplings lambda 3 and 4. And the scalar masses, neutral and charged ones, will not be that different. We use then the same mass range also for the sterile neutrinos. However, of course, with the additional constraint that we want the dark matter to be fermionic, and the lightest neutrino, sterile neutrino, should be lighter than the lightest neutral scalar. The whole idea of the scotogenic models is, of course, to generate neutrino masses, and therefore one has to take into account the neutrino mass differences in mixing angles from the oscillation experiments and a reactor experiment. And the neutrino mass matrix can be then expressed by a loop factor, since we generate the neutrino masses at one loop that contains the masses of the new particles in the loop. And it is bilinear in the Yukawa couplings Y. And then one diagonalizes, as usual, this neutrino mass matrix with the PMNS matrix. And once you do this, you can actually invert the mass relation in the famous Casas-Ibarra formalism and express the Yukawa couplings conversely as a function of the neutrino masses, mixing angles, the masses in the loop function of the new particles, and 3 arbitrary rotation angles in the case of 3 non-zero neutrino masses. So you actually do not have to scan over the Yukawa couplings, but they are rather constrained by the neutrino mass differences and mixing angles. What you have to scan over is the 3 rotation angles. The next set of constraints comes from charged lepton flavor violation. Jose Rale has already mentioned also the importance of these constraints for neutrino physics. And the most important ones are given here, in particular the mu to E gamma constraint from the MEG experiment, but also mu to 3e and mu e conversion by the syndrome experiments. And we give here the current limits and also the prospects for the upcoming experiments, where in fact mu 3e has a big jump with respect to syndrome. So these are also loop processes, similar to, for example, to the B to S gamma in the quark sector, mediated by penguin-like diagrams. And in this one loop, in this charged lepton processes, we find again the new particles. Here now the charged scalar, but also the light or the neutral fermions, and they are also again proportional to the Yukawa couplings. And they depend on these parameters to form factors of box diagrams. And one can numerically compute these numbers, for example, with Spheno. The next set, or next number rather, that we have to take into account is the relic density. So here we assume that only one particle is responsible for all dark matter in the universe. We have the standard freeze-out scenario for our WIMPs. And the fermions, the sterile neutrinos, have only the possibility to annihilate to standard model leptons because they are actually sterile, they don't have gauge interactions. And so these annihilation processes are also proportional to the Yukawa couplings. And so this will play an important role, the fact that both lepton flavor violation and the relic density are very sensitive to these Yukawa couplings. I've already mentioned the measured value by the Planck correlation, and from our work on supersymmetric dark matter within DMNLO, we know that there is also a theoretical uncertainty that has to be taken into account, similar to Higgs physics, where you also have this caveat, which we take to be 0.02. And here we calculate the relic density with one of the packages that are publicly available, like micrometers. Yeah, direct detection could be possible, but in fact, for sterile neutrinos, it occurs only at one loop, and therefore the rates are currently beyond experimental reach and do not have to be taken into account. So to get to the results, I think I have to speed up a little bit. We
Hello? Alexander, can you still hear Michael?
Yeah, I hear you. What is the problem? The problem... Костя, как мне включиться?
Michael, I cannot hear Michael anymore.
So I am. So I think that's the problem with the speaker. Yeah. There's because I just hear you and I see you. Yeah.
Yeah. So we have a problem with the speaker, unfortunately.
Yeah, I suppose yes. Костя, как мне включиться, чтобы мне тоже видно было? Костя, помогите мне, Костя, пожалуйста. Костя.
Включить, чтобы видео было включено.
Ну, сейчас, почему мне... Нет, хорошо. Убраться из полного экрана как? Костя, почему у меня этого нет? So, what to do? Probably we shall continue with another speaker and then probably give time.
Okay.
Yeah, I think it's the most reasonable thing. Yeah.
Okay.
Yeah. Thank you.
Okay. So we go ahead with the next speaker while hoping to solve the issue with Michael. So the next speaker is Rostislav Dvorky, and we will talk about the neutrino telescope in Lake Baikal, recent status and future perspective. The speaker is from JINR and Comenius University. So please share the screen and start your presentation.
Okay, thank you very much. So now just Chairman, I need to know whether you can see my full screen. Is it okay? Can you hear me and see my screen?
Both you can start.
Perfect. Okay. Okay, thank you very much. So firstly, I would like to thank the organizers for letting me do this presentation on behalf of the Baikal-GVD collaboration. That was, as the experiment of our Neutrino telescope was already mentioned by Viktor Anatolovich Matveyev. And just to emphasize that the collaboration is really international. So I would like to just highlight also the participation of the JINR, which allowed actually Slovak scientists as me just to join this very nice and brilliant experiment. So recently, our collaboration consists of roughly approximately 10 institutions from 5 countries, 70 members. And what I would like to stress and notice that actually this collaboration, you should be thinking of that as a grower. That means that we are still growing and enlarging our collaboration. Once I would like to just stress and emphasize what are the main objectives that were already mentioned by the not only Baikal-GVD telescope, but also by the neutrino telescopes in general. So that means simply investigating the neutrino sources like galactic and extragalactic neutrino sources in very high energies. For that particular reason, neutrinos are perfect messengers. As usually we say, that do not possess electric charge and therefore they are not bounded by magnetic fields. They interact very weakly, so they bring us the information immediately from the source till our detector. And speaking from the detector, what we are using is simply just the Baikal water. Speaking of Lake Baikal, which is quite general term, I would like to just focus your attention to the southwestern basin of Lake Baikal. Here, where is my pointer? It's 3.6 kilometers from the shore. So this is our location of the Neutrino telescope. The reason that was actually pick up this place is very wise, and that you need to travel only 3.6 kilometers away from the shore, as you can see on this ecologic picture, and you will reach the flat bottom lake, which is perfect for our ideal geometry of the detector, as it can be enlarged. Each module of the telescope can be enlarged at the same depth. Then the telescope is connected to the shore station, which you can see on this picture, which is simply the heart of our neutrino telescope, and it's simply acquired data that are collected by the neutrino detector. The biggest advantage, I would say so, from this place is also that we have solid ice cover for the 2 months of the year, usually February and April, where we can provide our maintenance work, enlarging the detector, and do some other technical operations on it. And the other advantage of this place is that there are really unique Baikal water properties. That means the absorption length is about 22 to 24 meters, and the scattering length about 30 to 50 meters. And there is a really low optical background, which varies from 15 to 60 kilohertz. I will speak about it on the next slide a little bit in more detail. Indeed, what we can really see how the Baikal water is clear. And when I say see, that means that what we can observe is the noise also of the lake. This is the slide, and particularly I'm working on in Baikal experiment, is that you can see that really the background on it reaches something like from 15 to 50 kilohertz, but sometimes there are intermittent periods where we can see something like a luminescent layer moving downwards through the telescope. So this is the disadvantage also once you have the detector in open water of the lake or sea. And when I say that what we can really see, that I mean it literally, because the basic detection unit of the whole neutrino telescope is nothing else but optical module, which is photomultiplier Hamamatsu in diameter of 10 inches, fixed in water-resistant pressure glass sphere. And with this glass sphere is called in our experiment optical module. It houses a mount, it houses except the photomultiplier and it's some other electronics, something like controllers and high voltage converters. And also inside of each optical module, there are also some detection units that are measuring humidity, the controlling of high voltage, and the temperature, which is inside, also the air pressure. Each optical module also contains calibration LEDs, which I will speak about a little bit later. Typical dark current of our optical modules is ranging from 8 to 12 kilohertz. So that is the typical dark current. Quantum efficiency is about 30 to 35%. So the main detection unit is nowadays mostly assembled and prepared in Dubna. So this is just a sketch how the preparation for the next winter expedition is going on. So you can see these spherical halves of the optical modules which are being prepared, then glued with, we are gluing with these photomultipliers and packing them. And lo and behold, in the end, you have one optical module as a key ingredient of our neutrino detector. The new facility in Dubna allows us to produce and test up to 12 optical modules per day. So this is quite a high production rate that we are actually trying to keep on. Another detection unit, which we call Baikal GVD section of optical modules, is simply nothing else but just a sequence of 12 optical modules with vertical spacing of 15 meters. All these optical modules are looking downwards, so that's the prime aim, is just the detection of the light going from downwards to upwards going particles. The 12 optical modules are attached to something that we call section control module, which is another housing optic, is another spherical glass that is housing actually only electronics. That's the dark sphere you can see here. It contains ADC channels and FADC converters, which are actually receiving the signals from optical modules, is responsible for the trigger and the data transmission from data from the 12 optical modules to the center of our detector. Beside optical modules and the central module, which houses electronics, we also do have acoustics module attached to the sections, which I will speak a little bit later. Now, thinking of that section as a subunit of our detector, what we do have is we just attach 3 such sections, and this unit is then called a string. 8 strings attach in such an arrangement that you have the one central one and 7 peripheral one, which produces something like a regular heptagon, is the fully independent unit of the Baikal GVD experiment, and that is called the Baikal GVD cluster. The cluster center, which is electronical module, not only one, actually 4 of them, then just simply takes the responsibility for the data acquisition. As you can see on the picture on the right side, is attached with the cable directly with the shore station. That means that you just take the data and by electro-optical fibers, you transfer the data to the shore station where the data acquisition takes place. So the cluster of our detector is responsible for the data acquisition once the trigger was generated on an arbitrary section of a cluster. That means that we have 24 sections on a cluster. Just the first one that will create the trigger, data from all 24 sections are stored and later on analyzed. So that means, speaking of data, what do we have is automatic data processing system. At the shore station, what we really do is that we acquire 40 gigabytes per cluster per day. These data are sent and stored at the shore station. Then they are transferred to Dubna, which we are also very thankful to Laboratory of Information Technologies that helps us with the computer facilities. Data are stored and sent to JINR servers over the internet from Irkutsk to Dubna. And recently, we do have fully automatic data processing and also alert production systems. What do we store are the raw waveforms that allow us later on for possible reprocessing of the data, pulse extraction, for the time synchronization, very important for detecting our events. We use White Rabbit synchronization of these independent clusters. And eventually what we have built is data quality monitoring system that runs 24/7. That means that we may control and see the health status of our experiment indeed continuously. As I mentioned previously, what do we actually need are also calibration devices. So on each section, there are 2 LEDs in each optical modules that flash light of 470 nanometers for a time about 5 nanoseconds. Once a week, we do something like we call calibration runs. That means that we try to observe neutrinos and the light from the neutrinos. But from time to time, what we need to do is to check the status of our telescope. And for these purposes, we use the calibration devices as these LEDs that are mounted in each optical module. Then what we do use are the LED beacons matrices that are attached at some strings of the cluster. And then we have installed, and we do use 2 powerful laser stations on each string. There are several strings already installed, which actually blink the light, and you can illuminate several clusters by this light. And it will, the flash of light is something, duration of it is something like about 1 nanosecond. Here is the picture of it, of the laser that is merged and installed in Lake Baikal. So I would like to also stress about the acoustic positioning system that is attached to the strings of our detector. Once we are in open water of Lake Baikal, you cannot prevent anything what to do if there are some torrent currents in water, then the whole detector will be slightly tilted. And that's the life. We need to take this into account. And for that purpose, there is an acoustic positioning system that actually measures each deviation of each string on a cluster. It uses simply just the acoustic waves that are, that you have one acoustic model is a source, the other one that produces beep. Then the other beacons are actually listening to this beep. And from the time delay, you simply deduce what's the position on, and the tilt of that string. This fact is really known that our gyrometer is not perfectly ideal. And here you can see as the string deviates on each beacon, you can see the X and Y deviation as a function of time during the measurement in July 1st and July 5th of the year 2019. So eventually what then we do are that we take these data from the acoustic positioning system and do the interpolation on the position of each optical module installed on a string. With the error something like less than 20 centimeters. Diameter of that optical module is roughly 28 centimeters. So that's the error that we have there. Baikal GVD, as I said, you should be thinking of the experiment as a grower. That means that it's still under construction and keeps growing. Each winter expedition, each year, we keep going on works and technical works that we install another cluster. Recently, this year, status of 2021 is that we have 8 clusters installed. 3 laser stations. Those lasers are exactly those calibration devices which we flash the light to the other optical modules. And there are also 2 experimental strings which I will briefly mention by the conclusion of my talk, and just to explain you what are these for. The plan, as you can see in this table, is that we will be moving on till the phase number 1 will be finished with 14 clusters in the year 2024. Recently, what I need to stress is that the effective volume in the cascade mode is 0.4 cubic kilometers. Unlike, for instance, the ice cube experiment in Antarctica, which is at a level of 1 cubic kilometer. So I will now briefly present you some selected results from our experiments. These I will divide into something like 3 subcategories. The muon detection mode, which will concern about atmospheric neutrinos. then the multi-messenger studies, and then the cascade detection modes, most particularly high energy cascades. So muons. Muons are good also for the calibration of our detector, and the muon neutrinos that we are using, actually the atmospheric neutrinos, serve as a perfect tool for calibrating our detector. The present status is that the technique for neutrino event selecting and recostering is recently under development. So what is developed is the quality function based on impulses, on the time of the detected impulses of each particular optical modules, and the information on the charges deposited on particular events there. Data that I will be showing are taken from April 1st to June 30 of the year 2019. This period was picked up, as I showed you on the previous slides, because this is what we call quiet period of the lake, when the luminescent layer that is the biggest, that provides background noise, is still on the top of the lake, not reaching our detector. So that is the reason why we pick up this period. And then, as you might see, what we used for the neutrino selection cuts, that we apply actually zenith angle larger than 120 degrees. That means that we can really, in this picture, can be seen that we can distinguish between atmospheric neutrinos and atmospheric muons. That these are just for the Monte Carlo data comparison. I will show you with the data on the next slide. Illustration of such events is presented on the right side, as you can see, where the color of the spheres represents actually the time. Being the red one are the earliest impulses, the bluish one or the violet one are the latest one. And what you can see is simply just the reconstructed track here on the two events. Also here there are some events here. So then what we can do with this analysis, that we applied something about 10 million reconstructed events from the year 2019, which I would like to emphasize that these are for the 5 clusters, and this equivalent for the single cluster equivalent lifetime of something like 320 days, which is approximately 1 year. Monte Carlo expectation should be about 44 events. What we observe are 44 events. So this is really fair agreement with the Monte Carlo prediction, though I still need to emphasize for the atmospheric neutrinos. The median energy is about 500 GeV of these events, and the angular resolution is about 1 degree or even better. So I would like to move to the next point, and those are multi-messenger studies. So except Michael GVD, there are 2 other experiments in the world as the neutrino famous telescopes, the one NTERES or KEAM-3net and the IceCube experiment. So since September 2020, we are processing the alerts with a delay of something like a few hours. These nearest plans are actually just that this high energy alerts should be processing with less than a few of minutes. Then, so since the end of the December 2018, the NTERES alerts that the colleagues from the European experiments are sending us, we have been processed. We processed already 45 alerts, and in 3 events, there are some possible coincidences that were found in a cascade mode within the circle, within the direction of 5 degrees, and the time delay ±1 day. So far for the IceCube alerts of the American experiment installed in Antarctica. So Baikal GVD followed the 20 full alerts. No coincidence has been found, but we derived upper limits at the level of the neutrino flux in the energy range of 1 TeV to 10 PeVs. So the cascade detection with the Baikal GVD, here I will present several slides on the results given on the cascade mode. So just simply to understand that what we will be operating are the 7 Baikal GVD clusters. That's the configuration from the year 2020-21. So this is on the left picture. You can see that the energy resolution in this mode is about 10 to 30%. And the mismatch angle is about something like a few degrees between the neutrino direction and the reconstructed cascade event that we might see. As far as the experiment aims for the detection of astrophysical events, that means high energy events, one may put something like artificial limit for 100 TeV and even above. So with the 7 GVD clusters, what we can then really expect is something like to have 3 to 4 events per year. So that is the situation of the year 2020. Recently, the situation is even better. As I said, we have now fully operating 8 Michael GVD clusters. So for the Monte Carlo and data comparison, the data are taken from the previous year, which means lifetime something like 2,000–3,000 days in terms of a single cluster. What has been selected are 72 events that have energy higher than 14 TeV and the number of hit optical modules larger than 19, which the number of hit optical modules we use as one of the criterion for the event selection. Then what you might do is that you will just simply increase the energy threshold, and then only 10 events will pass the criterion that they have energy higher than 100 TeV. This 100 TeV is something like a psychological border that you are really detecting really astrophysical neutrinos. You need to be sure that you're not detecting atmospheric neutrinos in that sense. On the right figure, what you might see is also the Zenith distribution of these events. And what we have now is one event that I will be speaking on later on that reaches the energy of a PeV scale. And the other one that is upward going neutrino, which I will mention also later on. So I would like to just now show you also.
Vasilslav, how many slides you still have? Sorry.
A few of them. So I understood. Thank you, Giacomo. That
you should hurry up.
Hurry up. Oh, okay. Thank you for notifying me. Okay, so I will just briefly go to something like astrophysical consequences that we have observed of these particular 10 events that we have observed. This is still preliminary work as the detector was completed with 7 clusters last year, but there is still ongoing analysis. I will just briefly mention that a PeV interesting event that this is just an illustration of it, that it is actually the highest energy we have registered in our detector so far, which is very good for us. And then I would like to also just to show that there are some possible astrophysical sources nearby this estimated direction of this event. And what I would like to emphasize also that there are 2 events that actually might overlap in the direction in the sky map, which you should be looking close to the galactic equatorial. And simply based on the I would like to also say that this is the interesting event because it is upward going event. You might say 91 TeV is not that much, but it is upward going event, which is the first clear cascade event from the interaction, most likely either from electron or tau neutrino at the level something like 100 TeV. So I would then actually, we are in cooperation with colleagues of astrophysics. Events that we did detect are close to something that is very interesting when the radio blazars increase their activity, but this is still preliminary work. I would like to show you only this picture and the other one, that when the blazar increases its activity, we observe also neutrino events, not only in that direction, but also in the vicinity of the time of that activity. So this is very interesting, but still preliminary results. I would like to just to give the acknowledgements to our colleagues who are not members of the collaboration, but they are responsible for the astrophysical studies. And I would like to just simply conclude that the Baikal GVD is recently just the biggest neutrino telescope in the Northern Hemisphere, with something like the effective volume of 0.4 cubic kilometer and still growing. Please keep in mind that Baikal GVD is under construction and growing and enlarging experiment. So there are also some future plans that we would like to move on with the data analysis and some other tasks of these alerts that I was speaking of. And this is just simply schematically the picture that what we have are 8 Baikal GVD clusters already installed. We would like to finish with 14 of them as the stage 1, and eventually we would like to keep going on and enlarging the telescope up to the cubic kilometer scale, or maybe even higher, if we will stay in health due to this COVID situation. And I would like to thank you for your attention. Thank you.
Thank you, Radislav, and congratulations for this potential detection of astrophysical neutrinos from Baikal. Unfortunately, I think that we have no time for question, maybe one urgent question, if there is one question.
I have a question.
Yeah, okay, please, Maxime.
Can Baikal Neutrino Telescope measure the flare content of cosmic neutrinos? What I mean, other neutrino telescope, for example, IceCube, can tell, or at least put some limits on how many electron neutrinos, mu neutrinos, and tau neutrinos come to the Earth from the sky.
Yes.
Can Baikal Neutrino Telescope do it?
Yes. The answer is simply yes, because we can distinguish clearly between the electron tau and muon neutrino signature. As far as the muon one is the track signature, while the cascade ones, I didn't perhaps mention it in more detail, gives you something like the flash of light, which is limited in space. Mostly we consider cascades as the point light source. So the answer is yes.
What is the ratio you predict?
Oh, the ratio that we have in our previous analysis is like we see the decoherence ratio of 1 to 1 to 1 for the electron, with tau being like the cascade mode 2 and the muon.
All right.
But still we need, for the astrophysical, we need to wait for larger statistics. Just please wait for a few more years, because really now what we have in the year 2019, really big jump in the increasement of the effective volume. So we will have more and more events per year. So the statistics will increase.
All right, thank you.
Yep.
Thank you, Radislav. Now, Alexander, I think that Michael is still connected, so he can complete his talk.
I think yes, yeah. Thank you.
So please, Michael, you can start from the, yes, you are at this slide, yes.
Okay, thank you. Can you hear me?
Yes, we can hear you.
So I'm sorry for the connection that broke. So I was told that I dropped out at this slide, and I will continue here. So we have to take into account experimental constraints on our parameter space. I discussed the lab limit on charged particles and the neutrino mass differences. The third type is lepton flavor violation, which was also mentioned by Jose Valle. And the important channels are given here, mu to E gamma with the MEC limit, 2 limits from syndrome, and the future perspectives. In particular on the mu to 3e, there will be a big improvement. And these diagrams are similar to the neutrino mass generation at one loop. They depend on the charged scalar mass, in this case, the singlet fermions, and again on the Yukawa couplings. And this is a very important point, because we will see how the different constraints from different experiments constrain the Yukawa couplings in different ways. We calculate these numbers with Pheno. The next important number that we have to take into account is the relic density, where we assume dark matter to be composed fully of our lightest fermion. It is heavy, so we have a standard freeze-out mechanism, and the relic density is generated by annihilation of these sterile neutrinos into standard metal leptons. Again, these processes are bilinear in the Yukawa couplings. Finally, there could be limits from direct detection. However, for singlet scale fermions, this process would only occur at one loop, and the rates are currently beyond experimental reach. So let's get to the numerical results. We have seen that the parameter space is relatively large, but some are constrained, some are more important than others. We have 4 masses, 3 scalar couplings, 3 Casas-Ibarra rotation angles, and we are of course mostly interested in the impact of a measurement of the lightest neutrino mass, or the absolute neutrino mass scale, which we vary between 10⁻³ and 2 electron volts, and we did actually analyses for both normal ordering and inverted ordering. And we have also seen that we have some constraints on the neutrino mass scale, but no measurement yet. The first result I want to show is here on the ratios of Yukawa coupling eigenvalues. Here, the second over the first one. And we see that this variation is large for small neutrino masses, but small for large neutrino masses. And the gray points include only the neutrino oscillation constraints. When we impose lepton flavor violation, which impose upper limits on the Yukawa couplings, also the ratio becomes reduced. And if we impose the relic density constraints, we get the green points. And since we need sizable Yukawa couplings, it imposes a lower limit. And in the end, in the overlap, we actually are forced to almost align with, so the Yukawa couplings have to be very similar in size. And this is both true for normal and inverted ordering. The second result I want to show is actually the most important one. If we look again at the diagram generating the neutrino masses, and you remember the quite complicated formula that deduced from it, from the loop factor, it actually simplifies considerably in the limit of this smallness of this Yukawa coupling, of this coupling lambda 5, self-coupling lambda 5, which is natural because of the additional symmetry. And in this limit, the neutrino mass matrix becomes directly proportional to lambda 5, and not only bilinear in the Yukawa couplings. And since we now have these constraints on the Yukawa couplings, we can actually make this dependence on lambda 5 explicit. And this is shown in this, what we think, very nice plot here, where you can see that the value of lambda 5 is in fact proportional to the lightest neutrino mass. And you can see how the lepton flavor violation constraints and the relic density constraints act in different ways, so that in the end, the viable points lie exactly on this line in the degenerate regime and become independent. This value of lambda 5 becomes independent of the absolute neutrino mass for small neutrino masses. And the yellow line here is the Hadron limit, the old published one, now it's 0.8, and the dashed line is the sensitivity limit. We can fit these red points at 90% confidence level, and we get these results here proportional to the neutrino mass above 0.05 electron volts and constant below. So the central result here is that this coupling that connects the dark sector with the standard model Higgs boson can be predicted once the absolute neutrino mass scale is known. Once we know that this ratio of neutrino mass over lambda 5 is fixed, we can also look at this bilinear dependence on the Yukawas. Here you see y1 as a function of the dark matter mass, and you can see that it has this square root dependence as expected. And in fact, the points don't spread out very much in the remaining parameter space. Even the ratio of the scalar mass over the fermion mass is relatively fixed to 1.5. We can fit this again. We get then the square root behavior of 0.08 at the bottom. So the second or the third result rather is that if we know the dark matter mass, we can then also predict the coupling of this dark matter to the standard model leptons, which is a strong prediction and makes the model testable. And now in terms of future experiments, one can also consider the upgrades of the lepton flavor violation experiments and future measurements by Hadron. And we can see that in this parameter space here, the measurements are complementary. So when we go from the current limits, which are the full lines, to the future limits, which are the dashed lines, you can see that the complete parameter space for fermionic dark matter in the scotogenic model can actually be tested. So this brings me to the summary, where first I would like to repeat the conclusions. We've seen that it is an intriguing possibility to connect the dark matter to the neutrino mass generation because it brings down the seesaw scale to TeV and makes it testable, or even at the LHC. We've seen that the fermionic dark matter space is severely constrained, and we could make this dependence explicit so that a measurement of the neutrino mass scale would directly predict the coupling of the dark sector with the standard model Higgs. And together with future measurements of lepton flavor relation, the complete parameter space can be tested. The reason is that in this diagram, which generates the neutrino masses, there is strong correlations between different observations, and the diagram is similar to the penguin diagram mediating lepton flavor relation. And when you cut on this fermion line here, it's also similar to the dark matter annihilation processes, which induces these strong correlations between the different constraints. As a caveat, I have to say that, of course, these correlations are not there. If you cut the diagram horizontally on the scalar lines, then these correlations are absent. And also scalar doublets, which have gauge interactions, can annihilate into weak gauge bosons, making the parameter space of the relic density larger. However, I would like to point out a very recent paper, which we have written in collaboration with our IceCube colleagues, also with experimentalists, showing that for this scalar dark matter, which is similar to the inert doublet model dark matter, inelastic scattering is important. It's important in particular in the sun, and neutrinos from the sun can be observed with IceCube and put stronger constraints also on the scalar dark matter than, for example, direct detection on Earth. Co-annihilation processes between scalar and fermion are also possible, have been studied elsewhere. And as an outlook, I would like to say that I focused mostly on Mars' original scotogenic model, but our conclusions generalize to some other of these topologies and diagrams, in particular in models. In particular, if you have a fermion triplet instead of a singlet, the topology doesn't change. If we have singlet and doublet scalars, the topology doesn't change. So the correlations are similar, but when the lepton flavor relation processes have weaker constraints because of mixing, for example, in the singlet doublet scalar sector, one has to consider also collider constraints. Thank you for your attention.
Thank you, Michael. And thank you for this interesting talk about the possible connection between neutrino and dark matter. Maybe we have time for one question. No question. So thank you again, Michael. And I think that we can close here the session.
Yeah, thank you very much. And I would like to propose that we start at 40 minutes, not 35, but 40 minutes. 40 minutes. Yeah.
Okay. Thank you, Alexander.
Yeah, thank you very much. Thank you.
Thank you, everybody.
И видео включаю. Вы не можете включить видео, поскольку я оставил... Ну, слушайте, вы меня прям это... Включите мне видео, если можно. Thank you. А как мне себя-то увидеть, Костя? А, я вижу себя, да. Я вижу, да.
Сейчас у нас еще пленарная.
А, пленарная, да?
Hi, just to say I'm here. Hi.
Hello. So, Francesca, I think that you can start the session.
Perfect. Thank you. Okay, so welcome everyone to this afternoon session. So we have 4 more exciting talks now. The first one is from Antonella Castellina. She's going to talk about the quest for the sources of ultra high energy cosmic rays, results and perspectives. So on to you, Antonella.
Yes, thank you very much. So maybe I can share my screen. I hope. Do you see my screen?
Yes, I can see it.
Let me check if I can. Yes. Is it okay?
Yeah, it's fine with me, yeah.
Okay, good. So, good morning, everybody. And before starting, let me thank the organizers for this invitation to talk about the quest for the sources of ultra-energy cosmic rays. I will talk about them from an experimental point of view, showing the results and the perspectives of this field of research. So let me start, if I can. What's happening? Yes. Okay, let me start by showing you some nice pictures of candidates of ultra-energy cosmic rays. There is something wrong with this presentation. Okay. Which may be of many different kinds, of course. We have gamma ray burst, active galactic nuclei, starburst galaxies, and more. But the most important thing that we have immediately to consider is that to be a viable source of ultra-energy cosmic rays, the possible sources have to comply with the severe constraints. The first one you can see in the left part of this slide is the Hillas criterion, very well known, which tells you that in a source with the magnetic field B and the size R, a particle can be accelerated if it is confined enough time and if it doesn't lose too much energy inside. So in this plane of magnetic field versus size, you see these lines that show you the conditions to accelerate different nuclei to energies around 10 to the 18 electron volts, and only the sources that are above these lines are viable ones. But of course, this is not the only constraint, because there is a second one, a very important one, the so-called Blandford constraint, which tells you that the sources have to be luminous enough. So to accelerate, for example, a proton at 10 to the 18.5, a source has to have at least some few 10 to the 44 per second. And we also can obtain from the measured flux of ultra-energy cosmic rays their emissivity, the emissivity of the sources, and their number density, or limits on their number density. So in this second plot, you see that in the case, for example, of stationary sources, you must have sources that have not too much number density, because they have to be luminous enough to stay above this horizontal orange line, but they can't be not too dense, because we didn't see multiplets coming from these sources. So we are left with sources that have to stay in this region of density and in this region of luminosity. And it seems that there is a contradiction. Not many candidates are there. Of course, this depends on the conditions under which you calculate these limits, and you can relax, for example, what you think of the galactic and extragalactic magnetic fields, and also consider that this kind of sources appear in different classes, so they can also populate here. But this is to make the point that viable sources are not so many, and they have very strong constraints. Now, I have always problems with this. I don't understand what. Now, the sources produce the particles, and they are injected in the universe. And of course, they have to propagate through the radiation fields that they encounter towards their path towards the Earth. And this implies that they can lose energy, and in particular into interactions with the cosmic microwave background. This means that there exists the so-called ZK cutoff, that is an attenuation of the flux. And you see here that the fraction of cosmic particles that can reach you from a distance d at different energies is not so big. And the horizon, the fraction of 50% of the particles that can reach you, is limited to 1 or 200 megaparsecs in case of the most numerous nuclei that you can have. This is also a very good news, because it means that the contributions of distant sources is naturally eliminated, and you are left with the search for sources that are nearby. And this allows you to look for anisotropies. Now, what are the experiments that look for these sources in this energy realm? We have two experiments. The first one is the Piedogé Observatory. It is located in Argentina. It's a very big one, 3,000 square kilometers surface detectors, water Cherenkov tanks, surrounded by 24 fluorescence detectors measuring the ultraviolet light that the showers produce. In Utah, in the Northern Hemisphere, we have the telescope array, much smaller, 700 square kilometers, also hybrid concept. The surface detector is made by scintillators, and there are fluorescence telescopes around. These two detectors together cover the full sky. This is a very important point to look for sources. They even have a small region in declination between about -15 to 40 degrees in declination, in which they have a common sky to view. And this is very important to check the results of the two experiments. What do we detect is shown here in the case of Auger, which is the biggest and most precise, so I will use it in the following, but I will show the comparison with the results of telescope array all along the talk. What do we measure? We measure the longitudinal profile of the showers, that is the energy deposited in the atmosphere, from which we get the energy, and observables related to composition. The lateral distribution with the surface detector, that is the signals at the different distances from the shower core, and in each point the time structure of the particles that reach our detector. And in a small part for the moment, we also have radio detectors which measure the radio emission of showers. Note that for the fluorescence detector, the duty cycle is only 15%, while in the other two cases, we have 100% duty cycle at hand. This is the most recent energy spectrum of the ultra-energy cosmic rays published by Auger last year. We have a combination of different sets of data with a very, very large exposure. And note that this spectrum is known with a very high precision. Our calibration that is done with hybrid events reaches the whole range up to 10 to the 20 electron volts. So everything is well known everywhere. To make things more visible, if I can, because this stops all the time. Oh, yes, I show you here better the features, the low energy angle, the secondly, the angle, the suppression, and the new one that we call the in-step, which is around 10 to the 19 electron volts. Note that the suppression is very well defined, and we could have even a flux recovery here. Although for this, we will need for more statistics. Now, as promised, I show you the comparison of our spectrum with that of telescope array. You see the comparison here. If you take into account the systematic uncertainty that we have on energy, 14% in Auger, 21% for telescope array, and you rescale, you see in the whole sky that you have a very, very good agreement in this region. And there is quite large disagreement in the highest energy part, which is not visible if you do the same comparison in the common declination band, because within the uncertainties, this is reasonably in agreement. This discrepancies is now a matter of study. There is no declination dependence of the Auger spectrum in the southern hemisphere, except for the dipolar anisotropy. But on the other hand, the difference is seen in telescope array at 4.3 sigma level. So, and it's not explained, according to our colleagues, by any systematic effects. So they claim that this could be an astrophysical effect, and this is now under study. Let me go quickly to the mass composition. That is the other important information that we have. We can measure it through the maximum development of the longitudinal profile with the fluorescence detectors, because this is directly proportional to the mean logarithmic mass. We can measure it through muons because with the surface detectors, because muons are produced in higher number when the primary is heavy. We can also measure it with radio because the two-dimensional footprint of the shower in radio at ground is related to the height of the depth of the maximum development. Note that the maximum contribution to the systematics in the mass composition measurements is due to the uncertainties in the hadronic interaction models that we need to convert our observables to the mass, to the nuclear mass of the primary. This is the current result on composition from Auger. This is the elongation rate of X max versus energy. You see that the composition is absolutely not constant. It goes lighter towards 10 to the 18.3 electron volts, and then it turns heavier again, intermediate and heavier. And this result is confirmed independently by the first measurements that we made with an engineering array of radio antennas by measuring the radio emission, although this is at the moment, of course, low statistics, but the agreement is very good. Now, the comparison of compositions between Auger and telescope array has always been a source of large confusion in the community. This is a non-trivial comparison because the two experiments use different methods and to determine this, to derive this information. For example, in telescope array, they don't have enough statistics to unbias their result from the detector response, while in Auger we can do this. To overcome this problem, we provided our friends of telescope array with our measured composition mix of nuclei, and they fed it to their simulation and put them in their detector. And this is what you see here. The red points are the points indicating the composition in X max that TA would have seen if the composition would be the Auger one, compared to what they measure in blue. So you see that in this energy range, the two compositions agree very well, in composition, and telescope array cannot at the moment distinguish between proton composition or mixed, like Auger is pointing at, composition. Note that telling that you are compatible with protons, as the telescope array says, does not mean that you are not compatible with something else, as this shows. This has been also done in other cases or in the same way, and confirms this result. Now the comparison has to be increased to higher energy. The working group in common with the two in collaborations is active again, so we hope to extend this result further. Now to go to the ultra energy sky, this is of course a very important information to look for the sources. The arrival directions of our cosmic rays can be studied looking at large scale as anisotropies. This can be done in the low energy range, where because the rigidity of these particles is not high enough and the deviations due to the magnetic fields are strong, while in the highest energy part we can look to intermediate or even small scale anisotropies. As for the large-scale anisotropy, the most important result was the discovery at the level of observation of dipolar anisotropy by Auger, which is now at 6.6 sigma significance. This anisotropy is pointing clearly outside the galaxy and is increasing with energy. This is a very important point because it means that we now know by experiment that the ultra energy cosmic rays above 10^18 electron volts are extragalactic. Also, this behavior here is reproducible only in models if you take into account an evolving composition in mass. This result has been confirmed by full sky search performed by Auger and telescope array together. The result is confirmed, and of course the uncertainties in this case are smaller, and they can be made even smaller in the future. If you go to now the highest energy part, what we do is to compare the arrival direction of our particles to different catalogs of astrophysical objects, basically catalogs related to radio galaxies and blazars, or catalogs related to star formation region star formation sources regions. You see here in top that if you look at this bright part of the sky where Centaurus A is, you have a deviation from isotropy that is at the level of 3.9 sigma, more or less. While if you look, as you see here in the model flux map, at starburst galaxies, the correlation is much stronger. You see here the test statistics that we obtain from this analysis, which is increasing with years, as you expect from a real event, from a real effect. And you see that if you we are now in a downward fluctuations, unfortunately, at the level of 4 sigma for starburst galaxies. But if you extrapolate with a line this trend, you can conclude that in 5 or 6 years from now, in phase 2 of the experiment, we will be able to reach discovery level 5 sigma observation. Also in this case, Auger and telescope array performed a full sky search together. This is again the coverage of the sky, and the scales of the two experiments have been rescaled in order to have the same flux in the common region. And you see that the result is confirmed for all galaxies and for starburst galaxies, for which we have more than 4.2 sigma post-trial significance. Now, this is a crowded slide in which I tried to summarize what we did learn from data up to now. Here you see the evolution of the composition fractions. Red are protons, yellow are helium nuclei, then we have nitrogen, and so on and so forth. The composition is clearly mixed and getting heavier. We still don't know if it goes like e to the atomic number, like in Peter's cycle, or if it's due exclusively to spallation, going then like e to the nuclear mass. We don't have data here, and this is the goal of the next upgrades of the experiment, to solve this problem. We have a very well established suppression here, which tell that the sources must be nearby, as I told you before, and we have limits on the local density of the sources, around 10 to the -6 to 10 to the -4 per megaparsec cube. In this region, the region of the ankle, we can exclude by means of other analysis, which I don't have time to describe, that the composition is pure or light. It's clearly mixed here. And also you see that we don't have iron in this region. So the transition from galactic to extragalactic cosmic rays should happen below the ankle, which can also be seen if you compare the limits on the dipolar anisotropy amplitude to models in which protons or iron are of galactic origin. This is not possible. So in this region, we expect to have the end of the galactic component in heavy nuclei and the onset of a protonic component, which is extragalactic in this energy range. We can make a combined fit of the energy spectrum and composition, like we did in Auger, for example, and show, for example, that the step here is due to the contribution basically of helium and nitrogen. And then we have the results of anisotropy that I showed you before. This was done, this combined fit, by using the idea of homogeneous sources. We have the interplay of two extragalactic populations, one in blue, high energy, one in red, low energy, and then the tail of the galactic component. And this kind of analysis put many serious problems because of the fact that here the spectrum is very hard at the sources, and for this component the spectrum is very soft. But of course there are also other ways to interpret these results. For example, you can think of different sources, or you can consider that you have maybe one single extragalactic component, but you consider also the interactions within the source and in its immediate environment, which would produce heavy nuclei which are of high energy and produce this part of the spectrum that we observe, and neutrons from the interactions inside the source that are lower in energy and then decay into protons, producing this lower energy component, again extragalactic. So there are a lot of models and works in this respect. There are also ways to go on in this kind of searches, which we, for example, explored in Auger. For example, we looked for composition-sensitive anisotropy by dividing the plane, the galaxy, into the galactic plane, looking at events coming from these directions, and to events coming from the direction off plane. And what we find is a difference in the mass composition. Heavier nuclei seems to concentrate in directions corresponding to the on plane, while light nuclei seem to become to reach us from off plane. And this is again some effect that grows in time. This cannot for sure be due to the galactic magnetic field, because there are other effects that can cause this, but it's a very interesting outlook that we want to explore. Another very nice thing that we did recently was to explore, for the moment in simulations, what happens if you include the arrival directions in the spectrum plus composition combined fit. And here you start with some simple models and try to fit all these three variables. And what you see, if you can see in this table, is that if you use only the spectrum and the composition, you have not much difference between, for example, starburst galaxy models or AGN models for sources. But if you use in the likelihood also the arrival direction, you see that the power of your separation becomes very, very strong. So we aim at applying this kind of combined fit, of a full combined fit, to all the data in the very near future. I don't know how much time I have, but I would like to finally...
Just for minutes, but in total, yeah, so
So I want just to tell you that the main outlook for the search for sources is given by the upgrades of the two experiments that are exploring this range. Auger prime is the upgrade of Auger, TA times 4 is the upgrade of telescope array. The philosophy of these two upgrades is different. In our case, in Auger, we choose to keep the area that we have, which is huge, but increase the composition sensitivity in the suppression region. And putting scintillators, radio antennas, and underground neon detectors. In telescope array, they chose, on the contrary, to increase the coverage, reaching the 3,000 square kilometers of Auger by including these two areas, instrumenting these two areas with 500 more stations and more fluorescence detectors. In our case, for example, in about 5 years of operation of the upgrade, we will be able, if we use all the variables that we will have at our hand, we will be able to reach 5 sigma significance in the possibility to define if in the suppression region there is at least a fraction of protons about 10 or 15%, which would open the door to particle astronomy. And for horizontal showers, we will have the radio antennas that will allow us to increase our exposure. So this brings me to my end. We are now here, more or less, with our two upgrades. We hope that we both will go on for another 5 or 6 years, and then we will leave ground with more certainties and results to new approach to the next step, which will be characterized by a very large complementarity approaches, because we will have space with POEMA, we will have ground with the giant cosmic ray observatory, which is now being discussed in the community, and also giant radio arrays like GRAND. So I thank you very much for your attention.
Thank you very much for this very nice talk. Let's move on and see whether there are any questions. So please just ask questions in case you have them, and no need to raise your hand. Can I just ask for the upgrades? You put a time frame of 2025 to 30th. Is that going to be operational just in 2025, or do you have also the construction period and then you have the...
Both upgrades are now in the deployment phase. We, in Auger, we already provided the first data with the part of the upgrade that is already operating, and we think we will complete the upgrade in 1 year from now. So during the deployment, of course, we will put into operation the part that is already ready to measure, and we are already starting to take data. And for telescope array, I know for sure that they are in deployment phase 2. I don't know if they plan to provide already upgraded results in the very near future, but I think we will have another talk about telescope array in this conference, so we will have more information from them.
Thank you very much. Okay, I can't see any questions there. So thank you very much again for this very nice talk, Antonella. And let's move on then to the next speaker, Javier Verdugo.
Hello, how are you? Can you hear me?
Yes, I can hear and see you.
Can you see the slides?
Not yet.
Yes, let me.
Okay, maybe starting now. Yeah,
Okay,
they are not
see it
in
now?
full screen. Yeah. Okay, now it's perfect. Thank you.
Okay. So first, I would like to thank the organization for inviting me to give this talk on behalf of the EMS collaboration. I will try to go through the latest results of the EMS during my talk. AMS is a magnetic spectrometer specifically designed for identification of charged particles with charge up to charge 28, and to measure their energy at the TeV region with high precision. The core of the detector is a permanent magnet that is hosting 7 silicon trackers that measure the bending of the trajectory of the particles in the detector. 2 outer layers at the top and the bottom of the detector increase the level arm of the measurement for high rigidity, for high energy. Above and below the core of the detector, we have a time of flight system that delivers the main trigger of the AMS, and also measure the velocity and the charge of the particle. Below the lower top, a ring imaging Cherenkov provides a high precision measurement of the velocity at the permit level, and allows to measure isotopic composition up to 10 GeV per nucleon. Also, the reading imaging Cherenkov makes an independent measurement of the charge of the particle. And at the top, at the bottom of the detector, we have the two key detectors to identify electrons and positrons from the huge background of protons in the measurement of the electrons and positrons. The electromagnetic calorimeter also provides the measurement of the electromagnetic shower at the TeV with a few percent. The key points of the detector is that it's able to make redundant measurements of the charge and the energy of the particles, therefore allowing to have independent calibration of the two detectors and to retrieve the efficiencies and the whole correction that we need to make the measurement of the flux of the cosmic rays. AMS was launched in May 16, 2011 from the Kennedy Space Center, and a few days later, 3 days later, the detector was already installed in the International Space Station and starting taking data that has been continuing till now. In fact, this year we have our 10th anniversary of operation in AMS. We could then celebrate properly due to the pandemic, but I hope that next year we will be able to make a good and nice meeting with people. During these 10 years, AMS had collected more than 180 billion cosmic rays. This is a capture that I made from our control system at CERN. And AMS is the first and only instrument providing simultaneous measurement of particles, antiparticles, chemical composition up to iron in an extended energy range and over a solar cycle. The AMS measurements resulted in 20 papers in physical review letters since 2013. That was the first publication that we made. And 12 of them were already tagged as editor suggestion by the editors. This year, we made a compilation of the results from the first 7 years in physics report. So in my presentation, I will concentrate on these updates that we made in the last measurements, as well as the measurements that we made and published in the last 2 years. This is the update of the measurement of the proton flux that we made in 2015. This is included in the physics report of this year. The flux is measured as function of the kinetic energy in order to compare with other experiments. And the flux is based on the measurement of 1 billion protons. Also, we have updated the measurement of the antiproton flux in cosmic rays. In this case, the increasing the statistics allow us to increase the energy range of the measurement. We reach 525 gigavolts, and the measurements compared with other experiments. In the insert, you can see the comparison at low rigidity because the plot is in linear scale. As well as with the antiproton flux, we measure the antiproton to proton flux ratio that is shown in the figure. It's curious that from around 50-60 GeV, the antiproton to proton flux ratio behaves as a constant. And in the insert, actually, you can see the evolution of the measurement compared with other experiments, Pamela and Bess. Antiprotons are commonly thought to be in the cosmic rays due to the collisions of other cosmic rays with interstellar medium. So there are mainly secondaries. So it's very important to make a comparison both the flux ratio and the flux of the antiprotons and the antiproton to proton flux ratio with models that provide with this decomposition that we expect from collisions. So in this slide, I saw the comparison of the data with 5 of the most recent models of secondary production for both in the top antiproton flux and at the bottom for antiproton to proton flux ratio. As you can see, still there is some kind of tension at the higher rigidity, and also the accuracy of the models, even if there has been a big improvement during the last few years, is still uncertain. So the accuracy of theoretical predictions can be improved with the latest AMS results on fluxes of cosmic rays, primary, secondary cosmic rays, and the ratios. In AMS, we have been measuring the flux of nuclei from helium to oxygen for light nuclei, and for heavy nuclei from fluorine to silicon in the first step, and also iron. The part of the from silicon to iron, due to the low flux, we are still waiting for have more statistics. Cosmic rays are usually seen as two components: primary elements, helium, carbon, oxygen as a light nuclei, or neon, magnesium, silicon as heavier, or iron, are produced during the lifetime of the stars, and they are accelerated by the explosion of the star supernova. During the traveling of the primary cosmic rays interaction with interstellar medium, they are produced secondary cosmic rays, lithium, beryllium, boron, fluorine, and the subiron nuclei. And the relation between these two elements provides an important information about the propagation of the cosmic rays in the galaxy. In fact, the ratio of the secondary over primary provides a direct input parameter for the propagation. So the precise measurement of primary and secondary rigidity dependence provide key information in the source process as well as the propagation. Here I show you comparison of the measured flux from AMS from helium to silicon plus iron in red with other measurements for other experiments. The precision is quite relevant, especially for secondary cosmic rays, lithium, beryllium, boron, or for heavier elements like fluorine, silicon, where the previous measurement had not enough statistics and they did not range too much energy. So let me go to some details of the measurements that we did for the nuclei. Here I present the latest AMS measurement of light nuclei in cosmic rays. The plot shows the flux as function of the rigidity for primary cosmic rays, helium, carbon, and oxygen, and for secondary cosmic rays, lithium, beryllium, boron, in the light nuclei. The primary cosmic rays, they have all of them, the three of them, they have identical rigidity dependence. And the secondary, they have also identical rigidity dependence. For the primary is about 60 GeV, for the secondary is about 30 GeV. And about 200 GeV, both primary and secondary, deviates for an Siegel power law. So by looking the secondary to primary flux ratio, we see that they do not follow a Siegel power law. We made the ratio of lithium over oxygen, beryllium over oxygen, boron over oxygen. We see that already they don't follow a single power law. And the secondary is hardened more than primaries. This, in some sense, gives some hint that this deviation from single power law of the fluxes is due to a propagation effect. Here I include in the plot not only the light nuclei, helium, boron, oxygen, also include the heavier elements, neon, magnesium, silicon as primary, and fluorine as secondary. In this case, also the primary neon, magnesium, and silicon, all three of them, they show identical rigidity dependence, about 86 GeV. And fluorine has identical rigidity dependence as of the light nuclei at high rigidity. But the rigidity dependence of the heavier nuclei is distinctively different from the light nuclei. If we make the ratio of the primary over primary, for instance, silicon over oxygen, we see that already there is a break And we see that already this deviation is at around 5 sigma level. Also, we see that the fluor over boron for low rigidity, for rigidities below 200 GeV has also different rigidity dependence. Traditionally, the light secondary to primary ratio is used to describe the propagation properties of all cosmic rays. In the plot, I show the ratio of fluorine over silicon, the ratio of secondary over primary for heavier nuclei in red, compared with the boron over oxygen, that is the ratio that we see in the light nuclei. We see that already that for heavier nuclei, we see it also there's a working power law, so they don't follow a single power law. But we observe that already the behavior versus rigidity of both ratios is different. In fact, we make the ratio of the ratios, secondary over primary, we see that above 10 GeV, the ratio can be described by second power law, deviating from zero with an effect 7 sigma. So it looks like the propagation properties of heavy cosmic rays are different from those of light cosmic rays. The last result that we published this year was the measurement of the iron nuclei in cosmic ray. We see that already the iron also deviates from a single power law above 200 GeV, but unexpectedly, one will assume that being iron the heaviest and more abundant nuclei in the cosmic rays, the rigidity dependence should be more similar to silicon, for instance. But we see that already the rigidity dependence is similar to the light nuclei, to helium, carbon, and oxygen. So this is an unexpected result. We also, very recently, last month, we have published the measurement of the flux of nitrogen, sodium, and aluminum nuclei in cosmic rays. These nuclei have the characteristics that are a composition of both primary and secondary. They are produced both in during the start, and also they are producing as secondaries during with interaction with the stellar medium. So the rigidity dependence is therefore quite different from both primary and secondary. Due to the high precision that we have in the measurements of the primaries and secondary cosmic rays, we can already express the flux that we measure in nitrogen, sodium, and aluminum as a sum of primary and secondary fluxes obtained by ourselves. And we see that already, for instance, here you can see for nitrogen that the nitrogen flux can be decoupled as a primary component that is increasing with rigidity and a secondary component. The same we can see from sodium and for aluminum. In fact, the abundance ratios at the source of the nitrogen with respect to oxygen or sodium and aluminum with respect to silicon have been determined without the need of, to consider the galactic propagation of cosmic rays with this measurement. As I said, EMS is able to measure isotopes up to 10 GeV per nucleon. Here I present the fluxes measured by for deuterium, the lithium isotopes, beryllium isotopes. I don't have too much time to go through. 2 years ago, we measured the isotopes for helium, helium-3 and helium-4. As you can see already, the measurement extends the energy range with respect to previous measurements. And also we made the measurement with respect to rigidity, not with respect to the kinetic energy per nucleon, in order to see already the behavior of the secondary over primary to be compared with the other nuclei. We see that the signal power law that we can fit about 4 gigavolts is consistent with Economov theory. Below 4 gigavolts, the solar modulation effect makes the flux changing a lot, and it's not constant. We are on the way to provide measurements of the lithium-6 over lithium-7 isotopes, as well as beryllium-10 over beryllium-9. So let me now go to the last part of my presentation that is more related to low energy cosmic rays and solar physics. Cosmic rays from the interstellar medium are screened by heliosphere, and this is particularly visible at low energies if we compare the spectrum measured at Voyager outside the heliosphere with measurements made at the Earth, AMS. We can see that already the effect is a shift in the energy that we measure. So in order to uncover already the flux measurement in the interstellar region, we have to already understand the solar modulation effects. In addition, the temporal evolution of the interplanetary space environment cause disturbances in the cosmic ray flux that correlate with solar activity. So therefore, the measurements of the time evolution of cosmic ray fluxes of different particles over an extended period of time is a very valuable input, and there is a field of physics in which AMS can make contributions. Cosmic ray variation correlates with solar activity at different time scales. The most significant is the long-term scale variation of 11-year solar cycle, during which the number of sunspots change from a minimum to a maximum and then back to a minimum. AMS started taking data in 2011, and the period of observation covers almost one complete solar cycle and includes the period in which the sun magnetic field polarity reversed between November 2012 to March 2014. Previously, AMS reported the time evolution of the monthly Bartle rotation, proton, helium, electrons, and positrons measured during the first 7 years of data taking. We have extended the analysis and the measurement to the time evolution of light nuclei, helium, carbon, and oxygen, and we have extended the time observation for these 8.5 years. So these results will be presented by my colleague Valerio Formato from Italy next Tuesday in this conference. I will just like to mention a few words about the measurements that we made on the daily proton and the helium fluxes. So we went from the Bartle rotation period, 27 days, to measure the fluxes in a daily basis. The data collected was from May 2011 to October 2019, it's 8.5 years, a total of 114 Bartle rotations. And you can see in the plot the evolution of the flux versus time, versus the years from 2011 to 2019, at different rigidity range. This is for in the left for the protons, the daily proton flux, and on the right for the daily helium flux. The data sample includes 5.5 billion protons, and the measurement has been made in the rigidity range between 1 and 100 GeV for protons, and for helium is 0.76 billion heliums, and the rigidity range from 1.71 to 100 gigavolts. Both fluxes, as you can see, both exhibit variation on different time scales from days to years, and the relative amplitude of these variations, as you can see in the plot, decrease with increasing rigidity. The first more clear variation that we see is the long-term variation related to the 11 years solar cycle. Here I plot the time evolution of the daily proton flux for the lowest rigidity bin, that from 1 to 1.16 gigavolts, together with the sunspot number. As you can see already, there is a clear correlation with both. We have studied also periodicities. In fact, this is the topic of our last publication that we have already submitted to PRL, is the study of periodicities in the daily proton flux. This is more evident in the part of the solar minimum, and you can see in the plot for different rigidity bins from 1 to 115 till 12 GeV, the evolution, the flux, the daily flux evolution, a function of time for year 2016. The vertical lines delimit Bartle's rotation. You can see very clearly, we can see very clearly the 27 periodicity correlated with the synodic rotation of the sun. And in fact, we can, in some cases, we can see for some of the Bartle rotations, doubles and double peaks or 3 peaks in one Bartle rotation. So in order to identify when periodic structure has significance, we have performed an analysis of wavelength time frequency, and the results of the analysis for the year 2006 is shown in the plot for 3 different rigidity bins, low rigidity, medium rigidity at 10 GeV. And the power of the wavelet is normalized by the variance of the flux in the corresponding time interval to show the strength of the periodicities and to be able to compare the strength at different rigidity ranges. The horizontal white lines marking 9, 13.5, and 27 days periodicities. And as you can see, the periodicities are clearly visible, but also they are changing both with time and also with rigidity, with energy. In particular, for the cases of 13.5 and 9 days, the strength, the power is much higher at higher rigidities than at lower rigidities. In the plot of the right is shown the evolution of the normalized power as function of the rigidity for the first half of the year. We divided the analysis into parts, first half and second half, and these are the results for the first half of the year. And at the bottom is for the second half of the year. As you can see, the 13.5 period appears in the second half and in the first half in both, and the strength, the normalized power is increasing with rigidity. The rigidity ranges from 1 to 20 and from 20 to 100. While for the 9 days period, does not appear in the second half of the year, appears only in the first half of the year, and also has a similar behavior, increase with rigidity and then decrease while rigidity is increasing. So let me just say that in the same way that we made the measurement of the daily proton and helium, we have performed the measurement of the daily electron and positron fluxes. It's important to have simultaneous measurement of particles and antiparticles over a complete Sokal cycle that represents a unique input to study charge science dependence on the heliospheric effect. So on the left, you can see the evolution of the flux as function of time in a similar circular plot as for the proton and helium for different rigidity beams. In the right plot, I present it's not presented the daily, it's a 3-day granularity, while the measurement is made on a daily basis, also as function of the rigidity. So this brings me to my conclusion that in 10 years on the International Space Station, AMS has recorded more than 180 billion cosmic rays, and AMS is providing simultaneous measurement of particles, antiparticles, chemical composition up to iron in an extended energy range and over a solar cycle. So the new features measured by AMS on high and also on low energy cosmic rays are new phenomena. So AMS will continue to collect and analyze data for the lifetime of the space station that, to my knowledge, is foreseen 2028. So thank you very much for your attention.
Thank you. Thank you very much for this great talk. All right. So are there any comments, questions?
May I ask you a question? Studnikin is speaking.
Please.
Yeah, please. And I would like to ask you, is there any reasonable explanation for positron excess?
Positron excess? No. As you know, we are looking at the different schemes. Certainly, the cosmic ray collision does not fulfill the measurements that we have already. So we have a huge space of about 40 GeV. And the two candidates, the more favored candidate from the astrophysics point of view is to have pulsars. And there are many pulsar models that can fit our data. But as I must say that the pulsar models, there are many parameters that you can tune whatever you want. And I mean, there are nice models, but it's not possible to exclude right now the pulsar contribution. Another possibility is dark matter. That is our favor, but perhaps it's not the right one. So the other tool that we have to look at it is to measure the anisotropy. In some sense, pulsars, we expect to have some kind of directionality of the positron excess. And while for dark matter, we don't expect such a thing. With the measurements that we have up to now of the isotropy, the excess is compatible with the isotropy. So we don't see any deviation from isotropy. So the conclusion from our side is that we would like to continue taking data we have to extend the energy range of the measurement for the positrons. Right now is 1 TeV. We would like to go to 1.5, 2 TeV. And also to improve with increasing the statistics, the measurement of the anisotrope, to see whether we can reach some kind of a level of total anisotropy or not. For pulsar models, we have some kind of predictions of anisotropy of the order of 0.5%. So right now we don't reach that statistical level.
Well, thank you very much.
Thank you. Okay, we are at the end of our time. So thank you very much again for this great presentation. And let's move on to the next speaker, Kate Schallberg. She is going to discuss the present future of a coherent elastic and neutrino nucleon scattering. Kate, hi.
Hey, let me find my screen to share. So first, thank you to the organizers. It's really a pleasure to participate in this conference. I'm sorry it's not in person, but I'm glad to be here anyway. So I'm going to give you an overview of coherent elastic neutrino nuclear scattering. And this is a process which we pronounce sevens these days, where you have a neutrino that hits a nucleus, exchanges a Z boson, and the nucleus recoils as an intact entity. And the condition for coherence can be stated a little bit more quantitatively as the momentum transfer times the size of the nuclear target. If that is a small number, then you have a coherent condition, which results in a total cross-section that scales as a single constituent cross-section times the square of the number of constituents. And this is what you get when the target nucleons are in phase with each other at low momentum transfer. And the cross-section is really very large by neutrino standards. Neutrinos, of course, are famously weakly interacting. Here's a plot of a cross-section as a function of neutrino energy. And this red line is inverse beta decay of antineutrinos on protons, which is a famously relatively large cross-section used for a lot of experiments. This green is a regular charge current process of electron neutrinos on iodine. That's one where there's actually a measurement. And the blue line here is the sevens cross-section on cesium or iodine, which are similar size. And you can see there's a couple of orders of magnitude difference. It's really quite large. And that's due to the squaring as the number of neutrons in the nucleus. And this cross-section, even though it's large, it's very difficult to observe. It was several decades between the time it was first proposed to the time it was first measured. And the reason was that the recoil energies are really extremely tiny. It's like trying to hit a bowling ball with a ping pong ball. Here's kinematic terms where the maximum recoil energy is. Just putting in some numbers for a medium-sized nucleus and a 30 MeV neutrino, this maximum recoil energy is only about 25 keV, which is orders of magnitudes slower than the threshold for a detector like, for example, super K. So this is the difficulty. You might ask, why should we bother? And there's many answers to this question. I could spend several talks on it. There's a reason. I'm going to pick out a couple of these, not go through the whole list. It's a signal for signatures of new physics. That's because the nucleus looks point-like to the neutrino, and so you can ignore a lot of nuclear physics uncertainties compared with high-energy neutrino interactions. It's also interesting for nuclear physics. I'm not going to talk about that. It's a background for new physics. I'm going to say a little bit about that. It's also a signal for astrophysics. I'll say also a little bit about that. The last thing I'm not going to say much about, it's because of the relatively large cross-section, it can be used for practical purposes such as nuclear reactor monitoring. So here's a little more detail in the standard model. Here's a way of writing the differential recoil cross-section here, where the GV and the GI are the standard model weak parameters. The GV is the vector coupling, where this neutron term is strongly dominant. The weak charge of the proton is very small, so it's really scattering off neutrons very much. There's also a small axial contribution. These here, Z's and N's, are the numbers of unpaired spins in a nucleus. The number of unpaired spins is typically much smaller than the number of nucleons in a nucleus, so the axial coupling is typically a small contribution. And if the spin is 0, it's 0. I can zoom in on this term in the differential cross-section. This is the nuclear form factor. Actually, this is where if you have precise measurements, you can actually get some information about nuclear physics. But in fact, we already know quite a bit about that. This is the Fourier transform of the spatial distribution of the nucleons in the nucleus. And it has typically quite small uncertainty. And on sevens rates that we're going to be talking about, it's less than a 5%, maybe a couple percent uncertainty. So it's the kind of thing where if you get very precise, you can probe it. But in the short term, it's the experimental uncertainties are larger. And this is just a demonstration of that. This is a fluxed average cross-section. This is the for a stopped pion flux, which I'm going to talk about as a function of neutron number. This is the n squared dependence that you expect. The black line is if you have a form factor of 1, so the nucleus looks exactly like a point to the neutrino, so there's no substructure from the point of view of the neutrino. There is some size, finite size of the nucleus, and that's gives you a suppression in the cross-section here for sevens. And that is the green line here. And the width of this line in that plot is the size of the uncertainty. It's about a 3% uncertainty. So it's really a very small uncertainty. And I've chosen some isotopes there, not randomly, we'll come to that. And so the idea for testing beyond the standard model of physics is that a deviation from the expectation can show you something new. And in particular, a deviation from the n squared dependence can be a pointer to new physics or deviation in other aspects. And zooming in a little bit on that, I think you're going to hear more about this kind of thing from Carlo in the next talk. One example of a way you get a deviation is just a simple excess or deficit. This is the kind of thing that a new heavy mediator would give you, just a scaling. And there's a kind of a whole subfield of looking for beyond the standard model in neutrino physics, where you can parameterize new interactions by these epsilons, which are just plonk them in the Lagrangian. If they're non-unity, then there's a new interaction of standard model size if they're of the size unity. This would give you an overall scaling. Here's an example. If you've got an epsilon EU and ED, this will give you either a suppression if the parameters are in this region, assuming all the others are 0, or an excess in the sevens rate. They can accidentally add up to match the standard model rate. And so if you measure the standard model rate or something consistent with it, you can exclude a region on that plane, but you can't completely get rid of all the possibilities. This is another topic I think Carlo is probably going to talk about more later, but you can also get a distortion of the recoil spectrum as a signature of beyond the standard model physics. If you have a light mediator, that will give you a shape of the recoil spectrum that doesn't match the standard model, for example. You can look for an anomalous magnetic moment, which gives you a specific kind of distortion that goes as approximately 1 over T at low recoil energies. There was a lot of excitement about some possibility for neutrino electron scatterings of this nature from the recent xenon experiment. There's also a possibility to look for sterile oscillations, which will give you a true disappearance with a baseline dependent recoil energy distortion. Okay, so I will move on to sevens as a background for signatures of new physics. And this is also some famous things here. There's what's called the neutrino floor. This is a parameter space for dark matter direct searches. Direct detection searches, where the parameter space is cross-section and mass of the dark matter particle, and the experiments will either find a spot on the plane or exclude a region above one of these lines here. And when the detectors get sensitive enough, they actually become sensitive to neutrinos from natural sources, such as the sun or the atmosphere. And what this line represents is the parameters at which, if your detector is sensitive to WIMPs of those parameters, then it is also sensitive to a similar signal from a natural neutrino. And therefore, those natural neutrinos will blind the detector, they will dominate the rate. And that's what's known as the neutrino floor. And it's kind of difficulty for getting below this for WIMP direct detection experiments. I'm going to mention this only very briefly. Sevens is also a background for accelerator produced dark matter. There's actually the same detectors that look for sevens can look for dark matter produced in an accelerator. For example, if you get a new mediators that will then decay into particles that can create recoils, you can search for that on accelerator. Actually, there's new results coming on this soon. And you can, and here it's the natural neutrinos that form the background for that. I'll say something very briefly about signal for astrophysics, although this is something that is dear to my heart. But I'll say something about solar neutrinos. You can actually see supernova neutrino bursts, but I will just mention that you can also see neutrinos from the sun. Just as it's a background in large dark matter detectors, it's also a signal. And the Xenon 1-ton experiment has actually put a limit on sevens from neutrinos from the sun. And eventually these experiments will hit the neutrino floor, and I just have to point out that sometimes there's very interesting things to see on that floor. Okay, so how do you actually measure this? I haven't talked about that yet. How do you do it? The only experimental signal is that little tiny recoil. The neutrino bumps the nucleus, and you somehow have to couple the energy of that recoil into something that you can digitize and measure. And in fact, the field has developed tremendously over the past few decades, actually with WIMP detection in mind, but those same detectors can be used for recoils. And I've stolen this from a dark matter talk that there's different strategies. You can couple heat or phonons into something digitizable. You can drift charge and collect it, or you can see light. And those are strategies. You can also use a combination of these. Just a point on the thresholds of these detectors, you need very low energy thresholds to see these tiny recoils. The maximum recoil energy goes as the square of the neutrino energy over the mass of the nucleus. This is an example for an argon target as a function of neutrino energy here. This is the maximum recoil energy you get here, and this is kV. So this is 1 kV, this is 100 kV. And if you just look at different fluxes of neutrinos that you might look at, these are artificial fluxes. This is neutrinos from pion decay at rest that go up to 50 MeV. Reactor fluxes only go up to around 8 MeV, even though they're actually very large. Fluxes that come from neutrino sources are below 1 MeV, so they're tiny. And so if you look what kind of threshold you would need to see these different fluxes, you can see that detectors that have, say, a few keV threshold, excuse me, are basically okay for stopped pion neutrinos. But if you want to see reactor neutrinos, you need very low thresholds around below keV or so. And if you want to see sources, you need even lower thresholds. So really novel technology. It's really, and backgrounds are going to be very difficult. This is just the same plot on the left. And just to illustrate this point, again, comparing reactor and stopped pion fluxes, this plot on the right is for the same flux, which is maybe a bit unfair because you can get very large reactor fluxes. But for the same flux, if you take a 3 MeV neutrino, typical of a reactor flux, compared to 30 MeV, this is the differential spectrum you would expect of recoil energies. And you can see that for the stopped pion flux, not only do you get higher recoil energies, you also get more of them because the actual total cross-section scales as the square of the neutrino energy. And so you might think, well, why not keep going higher in energy? But the problem is that if you get too high, you no longer satisfy the coherence condition. You start to get large momentum transfers dominating, and you're scattering off nucleons instead of nuclei. The effective de Broglie wavelength of the neutrino is very small, and you have just other interactions on nucleons dominating. So it's kind of a sweet spot to be around a few tens of MeV. And it turns out that we're lucky that we can actually make neutrinos in this range. These are neutrinos from pion decay at rest, or stopped pion neutrinos. And this is what you get when you slam a proton into a target. It creates pions. These, if they stop, then they decay at rest, and you get this two-body decay. You get a 30 MeV nu mu, so it's a specific flavor, specific energy. The muon then will subsequently decay at rest in a three-body decay, whose shape is determined by the weak interaction, and the time scale is well known. It's 2.2 microseconds. And so this is a very clean, well-understood spectrum. This spectrum has been used over the years for other neutrino experiments. This is just a figure of merit comparison of different proton sources that have been used to make stopped pion neutrinos. And you want more power. The more power you have, the more neutrinos you have. So you want to be on the right-hand side of this plot here. And it's a benefit to have the beam pulsed sharply, because when you have a sharp pulsing, you know when your neutrinos are coming, and you can measure the backgrounds off the pulse. That's used for lots of beam experiments. And what you get is if you have a high duty factor, you get a strong background rejection factor. You want to be in the upper right. And I'm going to zoom in on, so these are different kinds of sources that have been used, and some of them are in the future. I'm going to talk about the spallation neutron source, which is was used for the first measurement of sevens. So spallation neutron source it's at Oak Ridge National Lab in Tennessee. Proton beam energies are around a GeV. The power is regularly up to 1.4 megawatts, high power source. This was built to make neutrons. It's just random good luck that it makes fantastic neutrinos. It's 400 nanosecond pulses at 60 hertz. This is what the time structure looks like. So you get a prompt muon neutrino in time with the proton pulse, and then you get a delayed muon decay set of neutrinos on a 2.2 microsecond time scale. So this is very well known, and this happens 1/60 hertz apart, and so you get a very nice background rejection factor, comparable to being underground. This is the spectrum. This is on a log scale. The one I showed you, there is a little bit of stuff that is at higher energy beyond the 50 MeV from, for example, decay in flight, that because the SNS actually has a very large, dense target, almost every single proton or every single pion that is created immediately comes to a halt and then decays at rest. And so there's not much, it's very, very clean. Coherent is the collaboration that exploits this source. It's a small by high energy physics standard collaboration, about 90 people. And this is the list of sevens detector technologies that have been deployed, are deployed now, and are being deployed. So there's a cesium iodide detector that is now completed, that was deployed about 20 meters away from the source, 14.5 kilograms. There's an argon detector, 24 kilograms, currently running, and then 2 detectors, germanium and sodium iodide, that are under deployment now, of different scales from a couple tens of kilograms, and the sodium iodide will be 3-ton scale. There's a 185 kilogram prototype now deployed. So here's where we are. This is the proton beam. Here's the mercury target of the SNS. The neutrinos emerge isotropically from that. And there's a hallway. This is also fabulous good luck. We call it Neutrino Alley, which is along the proton beam, and where we can sit and be irradiated by neutrinos. We don't have to do anything with the beam. We just sit there and wait for the neutrinos. And this is where the detectors are aligned. This is what it looks like looking down Neutrino Alley. This is the first measurement with a 14.5 kilogram cesium iodide detector. This was 2017. It was published in Science. This is the energy, or this is proportional to the recoil energy, photoelectrons in from the scintillator, which is gives you the momentum transfer distribution. This axis here is the arrival time. This is a projection here on the right, which is basically the recoil energy distribution with the efficiency folded in, and the different colors of green show you the different contributions for the different flavors of neutrinos, which is well known. So that was the first measurement. The second measurement was early last year, and this was in argon. So there's another detector, which is a single phase argon detector. It's 24 kilograms of argon viewed by 2 PNTs with wavelength shifter. To shift the scintillation light from the argon, so it's using only scintillation. This is in the corner of Neutrino Alley and has been running for several years. And here is the first result from that. These are 3 distributions. This is time, this is energy. This is maybe the one that's most interesting to look at. This is also a pulse shape discrimination parameter that we use to select nuclear recoil-like events. And you can see here, there's a recoil spectral excess. There are more neutrons in that corner than in the center part where the cesium iodide was, but it's still tractable to understand that background. Neutrons are kind of the worst background because they also make recoils. And this is a new thing. This is earlier this year. This is the full data set analysis for the cesium iodide data, about twice the first result, with much improved detector response understanding and improved analysis. And this here on the left is the energy, recoil energy distribution. The red is the sevens, or the orangey is the sevens. On the right is the time distribution. And you can see that the neutrons are really a quite small contribution. And so this is now the status of the coherent results shown on this neutron number plot. And this is the cesium iodide result here. And now the error bars are getting squished down. Here's the argon result. So they're both consistent with the standard model. Nothing creepy there. The little tiny bit high, but still within 1 sigma on the argon side, and a tiny bit low, but still within 1 sigma on the cesium iodide side. So nothing really to point to beyond the standard model. And this is just an example of one of those simple non-standard interaction plots where it's actually significant improvement in allowed parameters for assuming all the other ones are 0. The one on the left is for the first cesium iodide result, and in orange for argon, and the one on the right is the new cesium iodide result, and we're working on a combined analysis. Okay, and so here's the future for coherent. Cesium iodide is decommissioned, has been for a while. Germanium is now in progress. It's funded. We have the detectors in hand and are testing them. Liquid argon is, we want to expand it. It's still running the smaller detector. And sodium iodide, we have the resources in hand to expand to about 3 tons. And there's also heavy water flux normalization. Heavy water has a well-known cross-section, so we should be able to reduce our largest uncertainty, which is the flux, using the heavy water. And we're also very excited about possible upgrades. So this is a plot showing the 2 target stations. There's a second target station which will be constructed within the next decade. This is the first one. So this is where the protons come in. The protons also go here. Some of them go here. And what this plot shows is it's a contour plot of neutrino flux surrounding these 2 different target station upgrades, which will approximately double the current power that we have. And so this is very, very exciting. Okay, so now let me say something about reactors. And so there's many technologies and detectors. This is not quite a comprehensive table, but there's a lot of different experiments that are going after sevens. There's only 2 of them using plan decay at rest that I know of in advanced stages. The other one is called CCM. I'll say a little tiny bit about that. And then there's this whole array of detectors that are going after the very challenging prospect of looking at reactor neutrinos, where the recoil energies are really, really tiny. But some of them are very exciting and interesting technologies. I'll say a little tiny bit about a coherent Captain Mills, which is another stopped pion experiment that is underway at Los Alamos, where they actually have a single, quite large 10-ton argon single-phase detector, and are planning a second one. And here actually the focus is on sterile neutrinos and dark matter search. For the reactors, the fluxes can be huge, but as I mentioned, the recoil energies are really tiny, and I'm just going to pull out a few of them. There's Konus in Germany, which has presented so far a limit. These are very challenging for background from a steady state source and such low energies, but has made very good progress with germanium. Connie is silicon-based CCDs. They have also put out a limit. They're looking for little tiny blips in a CCC, thick CCD detectors. They have actually a very small detector, 47 grams, and are planning on increasing that. And there's new exciting electronic technology for that. There's also Red 100. This is in Russia at Kalinin, and is deploying now 100 kilogram xenon, which is dual phase. So that's like the dark matter dual phase detectors, and they've demonstrated low thresholds. And I think I'm almost out of time, so I just want to summarize the sevens results. And so this is the flux average cross-section for stopped pion neutrinos. So this is approximately 30 MeV neutrinos, and these are the coherent targets that we're going after with the 2 measurements on it. So we've got these 2 measurements from coherent. We've also got limits from xenon that I showed. We've got that solar limit from xenon here. So this arrow represents the limit on the flux average cross-section. Solar neutrinos are lower energy, so the flux average cross-section is lower. And then for reactor neutrinos, we also have limits. We have a limit from Connie and a limit here from Konus. That's a lower cross-section yet, and is even more challenging, but I'm looking forward to more results soon. Okay, so I will stop there. So here's the summary, basically takeaway messages. 7 has this large cross-section, but tiny recoils. It goes as the square of the number of neutrons in the nucleus. It's now become accessible thanks to new low threshold technology, and also the extra oomph of the stopped pion source has enabled first measurements. This first one's by coherent in argon and cesium. We now have more data. Even that is enough to put on meaningful bounds. And we've got more in the works. Multiple targets and upgrades and better source. And there's also very exciting prospects for new 7's experiments going after reactor neutrinos, very long list. I haven't listed them all. And I think Yuri Efremenko will give a more information on some of these next Wednesday. So stay tuned for that, and also for Carlo's talk next.
Thank you very much for this excellent talk, Kate. All right, so let me check whether there are questions. I think I've seen a hand. Yeah, please, Carlo. Were you asking questions?
Yes.
Yeah,
thank you, Kate, for the very nice talk. I wanted to ask you about the cesium iodide possibility to make new experiments with cesium iodide, because you said that the coherent one has been decommissioned. And it will be interesting to have more measurement with cesium, because one can measure with 7's also the weak mixing angle and connect the 7's measurement to the atomic parity violation measurement with cesium with the same nucleus. So do you know if there is more experiment with cesium?
Actually, quite possibly we have, and I probably should have put it in that table since it's kind of getting close to on mass shell. We actually have a working group that is looking into cryogenic scintillators, and the most likely candidate of which is cesium iodide. And so if you have the right doping and you have the low temperature, you can actually get about twice the light out. And in fact, we do have some proposal. We actually have an active R&D program for that detector. That's Jinglu at South Dakota. And if this is funded, then we will be adding a cryogenic cesium iodide. I think he's also looking at sodium iodide, but I think cesium iodide is the most promising of those. So yeah, so actually that's good information. If cesium iodide is the preferred for physics reach, then that would influence the choice, I think.
Okay, thank you. Can I make another question about, I think you have a plan of a detector in which you measure the neutrino flux with charge current interactions, because this is a source of uncertainty in coherent.
Yes.
So how is going on that?
Oh, that's going well. We actually have pretty much secured the funding for the first module of that. We want to do 2 modules, adding up to a good fraction of 2 tons. So the first module is about 700 kilograms. We have heavy water for that. Actually, we got that from UCI. That's now in hand at Oak Ridge. The PMTs are in hand. We're working on the rest of it. And so that we're actually hoping to deploy that by the end of the year. That's going to be challenging, but that's, I think probably Yuri, in his talk next Wednesday, he's the leader of that group and he will be likely saying more about that. But yeah, so it's about 700 kilograms of heavy water, which should enable us to, so the flux uncertainty is now about 10%. It's now the dominant uncertainty. And the cross-section uncertainty for heavy water is 1 or 2%. So in principle, we could get down to something like that. In the short term, I think 5% is reasonable to aim for, and we're hoping in the longer term to get to a few percent. And we have to worry a bit because the beam does change, so we have to, it's not a huge change, but at some level we're chasing the changes in the beam configuration to nail down those uncertainties.
Thank you.
Thank you. I think time is up. So thank you very much, Kate, again, for this excellent presentation. And let's move on then to the next speaker, that indeed is Carlo Giunti, theoretical overview on coherent elastic and neutrino nuclear scattering.
Okay, can you see my slides? And can you hear me?
Yes, both.
Very good. So okay. So thank you for to the organizers to invite me to give this theoretical talk on the overview of coherent elastic neutrino nucleus scattering. So as Kate explained, this process is called sevens. So I will call it that way from now on. This is a neutral current interaction of a neutrino with a nucleus in which the nucleus recoils without any internal change of state. In the standard model, this is done to the exchange of the Z boson, and the cross-section is the same for all the different flavored neutrinos. This process is very difficult to detect, as Kate explained, because one needs to detect the energy, a nucleus which has a very low nuclear recoil energy, which is smaller than about 10 keV. So it was observed by the coherent experiment about 43 years later after the prediction of this process in 1974. And last year, the coherent experiment measured also this process with another detector, which is the liquid argon detector that was described by Kate. So let us look at the cross-section to understand what is the physical contribution to this process. So the cross-section in the standard model is given by this expression, and one can see that it depends on the square of the weak charge of the nucleus. So the weak charge of the nucleus has a contribution from the neutrons in the nucleus and from the protons in the nucleus. Now, due to a numerical coincidence, the mixing angle, twice the mixing angle is about 1/2. So in the case of the proton contribution, just due to a numerical coincidence, there is a almost perfect cancellations, and the proton contribution is subdominal. The main contribution is due to the neutrons, which is not suppressed. So in practice, the cross-section of sevens is proportional to the square of the neutron number of the nucleus. So this is due to the coherence of the process, so that is proportional to the square of the neutron number, because the incoherent cross-section will be proportional to the sum of the cross-sections over the all the neutrons in the nucleus. So it will be proportional only to the number of the neutrons. So there is an enhancement of the coherent cross-section with respect to the coherent cross-section given by the neutron number, which can be rather large for heavy nuclei which have a number of neutrons of the order of 100. Here you can notice that in the weak charge, we must take into account also the form factors of the nuclear of the distributions in the nucleus of neutrons and protons. And these form factors take into account of the possible loss of the coherence when this product is larger than 1. So one has a coherence only when this product is smaller than 1. And this is illustrated schematically here. So when the neutrino interacts with the nucleus, it exchanges a Z boson. And the Z boson, if it has a large wavelength, then it cannot distinguish the structure of the nucleus, and then the nucleus is recoiled in a coherent way as a whole without any change of state. And since the wavelength is inversely proportional to the momentum transfer, then we get this condition that the product of the momentum transfer times the radius of the nucleus is must be less than 1 in order to have coherence. Now, in the coherent cesium iodine experiment, the scatter is not completely coherent. And this one can see by considering the energy recoil measured in this experiment, which is connected to the momentum transfer through this relation. And one can see that the product of these two quantities is between 0.5 and 2. So we are just in a range which superimpose the coherent part, which is this part, and the incoherent part, which is this part. And this can be seen here in this plot that shows the prediction of the standard model in the case of the full coherence, which is given by this dash dotted histogram, and you can see that it cannot fill the data. In order to fill the data, one must consider the form factors which describe a partial coherency in the interaction. Here, this is also shown in this plot that was shown also by Kate, in which the measurement of cesium iodine incoherent is smaller, the cross-section is smaller than the one that is given by the solid line, which will be correspond to a full coherency. And this plot shows also the dependency as a function of the square of the Newton number of the cross-section. Now, the partial coherency is a rather interesting quantity that give information on the structure of the nucleus. And because the form factor is the Fourier transform or the distribution of the nucleus. So this is the equation. And the measurable parameter is the radius of the nuclear neutron distribution, which is a parameter of the distribution that is written here. Now, this is interesting because it is very difficult to measure the radius of the neutron distribution in the nucleus. Contrary to the proton distribution, which can be measured by looking at the charge density of the nucleus or in the nucleus. And in fact, the proton distribution in the nuclei for all nuclei has been measured with rather high precision using electroweak probes, electromagnetic probes, in particular with electron nucleus elastic scattering and with muonic atom spectroscopy. In order to measure the neutron distribution in the nucleus, one can use hadronic scattering, but the interpretation of these experiments is very difficult and model dependent because it depends on the nuclear model of the nucleus. Instead, interaction with neutral current wake interactions are independent on the model of the nucleus, but they are more difficult. And in fact, the radius of the neutron distribution in the nucleus was measured only once for the lead nuclei in this PREX experiment using parity violating electron scattering. I mean, it was measured by neutral current weak interactions. And the value is given here. So for the lead, it is about 5.8 Fermi. And this measurement shows that the radius of the neutron distribution is larger than the radius of the proton distribution, which is about 5.5 Fermi. And this corresponds to the existence of the so-called neutron scheme that is shown here. So for heavy nuclei which have an excess of neutron, then it is expected that the surface of the nucleus is more populated by the neutrons, and one has a radius which is larger for the neutron distribution than from the proton distribution. So using the coherent cesium iodide data of sevens, then we, for the first time, we measured the radius of the neutron distribution in cesium iodide using neutrino scattering. And this led to a rather large value that you can see here, about 5.5 Fermi, but with large uncertainties. But the best fit indicate a value which is larger than the value of the proton radius. So it indicates a sizable neutron skin, which is a rather interesting information. More recently, we used the new 2020 coherent CSI data, and we obtained practically the same value with smaller uncertainties. So the existence of neutron skin is a very important, interesting thing for nuclear physics, but also for astrophysics, because the fact that the radius of the neutrons is larger, it means that there is a larger pressure of neutrons in the nucleus, and so this is something that should be explained by nuclear models, and it has important implication for astrophysics because it implies a larger size of neutron stars, and this is connected also with measurements of gravitational waves which are emitted in the merging of neutron stars, which depend on the size of the neutron stars. So this is a very useful information. Now let me go to information that we can get from CEVES on the neutrino properties. So in general, the coherent interaction with the nucleus of neutrino can occur in the standard model through the exchange of the Z. But when we go beyond the standard model, then we can have electromagnetic interaction, so exchange of a photon, which generate the coherent recoil of the nucleus, and then also other mediators like vector type mediators that are typically called Z prime or sometimes dark bosons, and also scalar mediators. As you can see here, here I did not write a BSM for electromagnetic interaction because we will see that even in the standard model, radiative correction generate electromagnetic interactions which contribute to the CEVES. And here you note also that I put here a different flavor beta because in this process we cannot measure the flavor of the final neutrino, so we sum over all the possible flavors, and if there are interactions which are flavor changes, then flavor changing this interaction contribute to the process. An important thing about the coherent experiment is that this coherent experiment used a source of neutrinos given by stopped pions, and this produces neutrinos with different flavors from mu and electron neutrinos. So this is very good because we can distinguish the interaction beyond the standard model that can be different for muon and electron neutrinos. And this is done because it can be done because the muon and electron neutrinos have a different spectral, so the energy spectrum is different, and also they arrive at a different time. So this allows to distinguish the different interaction of the electron and muon neutrinos. So now I will have time only to speak about electromagnetic interactions. And electromagnetic interactions are can be written in terms of an effective Hamiltonian, in which we get the interaction of the neutrinos with connected with a photon is given by this effective electromagnetic vertex. And on the basis of general properties like Lorentz invariance, Gauge invariance, this vertex function depends only on four quantities which are written here. And these quantities in reality are form factors, but we are considering a very low momentum transfer, so we can consider this form factor close to zero. And in this case, this term corresponds to the charge, this to the anapole, this to the magnetic moment, and this to the electric moment. As you can see here, this two moments, then they conserve helicity in the limit of ultra-relativistic neutrinos, and this flip helicity. And this is important because they will contribute in a different way to the 7 cross-section. Other important properties are that these quantities are real. For Majorana neutrinos, then one can have only transition moments. And in the case of ultra-relativistic neutrinos, here, this gamma 5 practically is equal to a -1. So the charge and anapole contribute in the same way, and the magnetic and electric moments contribute in the same way. So the first property to be studied is the neutrino charge radius, because even in the standard model, this charge radius exists, and it is given by radiative correction. So in the standard model, one can calculate these loops, and these loops contribute to the interaction of neutrinos with the photon. And in particular, when we must develop the form factor in a series, and the first term at q square equals 0 exactly, then this is 0 because the neutrino in the standard model is neutral, and the first term in the series can be interpreted just as a charge radius. So let me emphasize that this is not related to neutrino masses, and this is the standard model for massless neutrinos. So this is the original standard model of Glashow-Weinberger-Salam. And in the standard model, then one can calculate these radiative corrections, and this was done by the group of Bernabeu and collaborators, and it has these values. So here we speak about the charge radius, but in the terminology, in reality is the square of the charge radius, which is of the order of 10 to the minus 33 centimeter square. There are many some experimental bounds on the charge radius, which were obtained in reactor experiments and accelerator experiments. And as you can see here, the bounds are of the order of 10 to the minus 32. So they are not far from the standard model prediction. That is only about 1 order of magnitude smaller. So there is good hope that in the future, this will be the first electromagnetic interaction that will be detected for the neutrinos. In the sevens, the charge radius radii of the neutrino contribute in a rather complicated way, as you can see here. So here we need to distinguish the diagonal charge radii from the off-diagonal charge radii. And this is because both of them conserve the helicity. So the diagonal charge radii, since they have the same final momentum, final flavor state of the normal neutral current interaction, they contribute coherently to the normal neutral current interaction. And on the other hand, the off-diagonal charge radii, then they contribute incoherently. So they contribute in a different way. And this different type of contribution allow us to distinguish this different charge radii. In the fit of the coherent data, we obtain the results which are shown here. So this is the allowed region. The green region is the region which was obtained by the combination of the data of the coherent experiment, cesium iodine and argon. And you can see that the region is rather large, so it is some tens of, the scale is some tens of 10 to the minus 22 centimeters. So this bound, for the moment, they are not competitive with the bounds obtained from reactor experiments, and which constrain these quantities here within this small square. but we hope that a new seventh experiment will improve this measurement and maybe become competitive. So we must remember that the seventh measurement of the coherent is just the first one, and this is the field is just at its beginning. So in the future, it will be maybe an important player in the determination, high precision determination of this charge array. Using this formula that I showed in the previous slide, we obtained for the first time information on the off-diagonal charge radii, and this is given here. And here I must remember you that in the original Lagrangian, the charge radii are defined in the mass basis. So in these experiments, we measure some effective charge radii, which are a combination of the charge radii in the mass basis according to the neutrino mixing parameters. It is interesting that also the millicharges of neutrinos can be probed in sevens, and people mostly believe that the neutrinos are neutral particles, but in some theories beyond the standard model, they can have very small millicharges. And as you can see from these formulas, then the millicharges of the neutrinos, they contribute in the same way, in the similar way as the charge radius, but they have a different Q² dependence. So the results are different. And in particular, this is a list of bounds on the neutrino millicharges. As you can see here, the strongest bounds apply to the electron, to the millicharge of the electron neutrinos, which has been obtained from the nuclear reactors, and a very strong one from the neutrality of matter. From the muon, for the millicharge of the muon neutrino, the bound is less constraining, and the limits that we obtain from the coherent sevens data are competitive with this bound, and in particular, we obtain some information on the for the first time some information on the transition charge charge from nu mu to nu tau. And this is shown, I mean, the result of the data, of the analysis of the data are shown in this plot. So this plot shows the allowed region for the diagonal charges, and this for the off-diagonal charges. And then I will finish with the discussion of the neutrino magnetic and electric moments. So these are quantities which are predicted beyond the standard model, and they are connected with the mass of the neutrinos. Essentially because the same diagrams which contribute to the mass of the neutrino, if one add to them a photon line, then they contribute to the charge, to the magnetic moments. And these are elicity flipping quantities, so they, as we will see, they contribute in a different way in the seventh cross-section. The prediction of the simplest extension of the standard model is that for Dirac neutrinos, then the magnetic moments is very small, so like 10 to the minus 19 Bohr magnitude for the diagonal one. For the off-diagonal, they are even more suppressed by the JINR mechanism. Also, Majorana neutrinos can have a transition magnetic moment, but these are severely suppressed by the JINR mechanism. The traditional way to look at the magnetic moment is through with laboratory experiment is to look at the scattering of neutrinos with electrons, and using the fact that the cross-section due to the magnetic interaction increases is inversely proportional to the recoil energy of the electron. And so it increases when you go to look at electron with very low recoil energy. And instead, the weak cross-section remains constant. So by looking at an excess at the low recoil energy of the electron, it is possible to put bounds on the magnetic moment. And these bounds have been put, the strongest one are those obtained with reactor neutrinos, and the stronger one is from the JINR experiment, is 2.9 times 10 to the minus 11 Bohr magnetons. Also, accelerator experiment give bound on the magnetic moment, and especially this accelerator experiment can be used to get bound on the magnetic moment of the muon neutrinos. But as you can see, there is a gap of about 8 orders of magnitude between these bounds and the predictions of the standard, of the simplest extension of the standard model with Dirac massive neutrinos. So if some value will be found near this bound in the future, then it will mean that it will be an indication of some non-minimal standard model extension. In the case of sevens, the magnetic moment contribute incoherently to the.
Okay, sorry to interrupt you. We are really now at the limit. Do you have many more slides?
No. I have just 2 slides. So
okay,
I'm going to finish. Thank you. As you can see here, the magnetic moment contributes incoherently, so we cannot distinguish the diagonal magnetic moment, and we get information only on some collective effective value of the magnetic moment, which take into account also the electric moment. And this is the result of the fit of the coherent data. And unfortunately, the bound on the electron neutrino magnetic moment is not competitive with the reactor data, but the bound on the muon neutrino magnetic moment is just not far from the bound which is obtained from the LSND experiment. So there is hope that in the future, sevens can play an important role in the determination of this magnetic moment. So since I knew that there will be no time for the summary, I just conclude with this nice figure made by Eligio Lisi some years ago, which shows that sevens is some magic process that will allow already allows, and in the future will allow to obtain very interesting information on nuclear physics and neutrino physics and also astrophysics. Thank you.
Thank you. Thank you very much for this very, very intense talk. Is there any questions? Are there any questions?
I have one question.
Yeah, please.
When you spoke about the off-diagonal magnetic moments of Dirac neutrinos, you told that they are suppressed by the JINR mechanism. But you referred to the minimal extension of the minimally extended standard model. What happens if you consider other extensions of the standard model where the off-diagonal, where the magnetic moments of Dirac neutrinos are predicted?
Well,
does JINR suppression works in this case?
I think it is very difficult to get even some values which is not suppressed. Now I really don't know about the transition magnetic moment, but in general the contribution of the magnetic moment is proportional to the neutrino masses. So it may be that in some models, then it is possible to get some value which is not so strongly suppressed for the transitions. I think there are some models. One has to arrange the these models involve new particles, so one has to arrange the new particles in order to have larger values.
Thank you.
Thank you. We do have another question, I guess, Yuri, and then I guess we should move on to the break. Yuri, please.
Yes, thank you. Carla, thank you for very nice overview. I have a question. Could you comment on possibility of inelastic coherent scattering? The same coherent scattering, but nuclear left in excited state. There are some publications. What do you think about that?
This is a question that I also was thinking about, but it seems to me rather difficult. So the incoherent scattering, so for example, if we have some incoherent scattering in which the recoil nucleus is some excited state, then this will emit decay into the ground state. So it will be necessary that the experiment can see this decay. So to measure an additional signal due to this transition to the ground state. And also from the theoretical point of view, then here we need to have a nuclear model to describe this transition. So everything is very, very complicated. So as far as I know, there is Naumov and collaborators, they discussed this possibility, but I don't know if it can be applied.
You see, it's very attractive from the point of view of experiment, because instead of single signal, tiny nuclear recoil, you have de-excitation as well. So a detector can deal with the two signals which suppress background significantly. So if process like that does exist, it's very attractive to detect it experimentally.
Yeah. This seems to me good, but you experimentalists must tell us if you can do these measurements.
Yeah, I think with germanium detectors, which supposed to be deployed in coherent experiment this year or next year, we can try to look for this process as well.
Very nice. Thank you.
Okay, I can't see any other hands, and I'd like to thank. Yes, please. Let's thank the speaker again, and also all the people who participated in the discussion. Thank you. Now to Alexander.
Yeah, well, thank you very much for the speakers and for Francesca. So we shall start both sessions, A and B, at 15:40. Okay? Thank you.
Thank you.
Okay, hello everyone. Can someone confirm that you hear me?
Hello, yes.
Yes, hello.
Oh, it's 3:40 now, sorry. And we should begin afternoon session. So the first speaker is Hussein Ahmad, who will present test of standard model by means of epsilon 3s decays with Babar. So I would like to ask you to keep on time. You have 15 minutes, including discussion. So we need to have 2 to 3 minutes for discussion. So I will remind you at minute 12 that you have 1 minute left. So you can start sharing and start when you're ready.
So I have to go to the, I didn't use the Zoom before.
We have also organizers that can help you if needed.
Yes, there is a button down, a green button with a demonstration of the screen or translation of the screen, green button.
Yeah.
Okay.
It's share screen, and then you press that one, and then you just pick your slides and go to full screen.
But I cannot see my slide when I use the share button.
You should have, when you click on the share screen, you should see everything that is open on your laptop.
Yeah, so that is the desktop. I can see whiteboard and Microsoft PowerPoint.
Drive your PPT. I don't know where you have your slides.
At first, you should go to Zoom, and in Zoom, you should press the green button. Share the screen.
Yeah, Konstantin, he did it, but he cannot find his slides now on the screen.
Okay, I can translate your slides and
yes,
I will open it in 1 minute. Okay.
Okay, we see the slides. So Hussein, when you're ready, you can just start and I will start timing.
Yes,
I see my slide. Do you guys hear me and see the slides?
Yes, we hear you and see the slides.
All right. So hello, everyone. My name is Hussein Ahmed, and I'm calling from Nova Scotia, Canada, from Cinefax. So today I'm going to present the Babar result for Lepton University and the Charles Lepton flavor violation by using the epsilon 3s decays. So if we go to the page number 2, someone needs to change the page for me. Yeah, okay. So these measurements are basically the test of the standard model. For example, the Lepton University and the Charles Lepton flavor violation. And these are also the search for the phenomena beyond the standard model. So the Lepton University, based on the branching fraction ratio measurements using the epsilon 3s decays to tau pairs and epsilon 3s decays to muon pairs, is already published in PRL. And the Charles Lepton flavor violation based on the epsilon 3s decays to E plus minus and mu minus plus is in the final stage for submitting to the PRL. On page 3, so in the motivation for the Lepton University, so according to the standard model, the lepton pairs, coupling of the lepton pairs from gauge boson is independent of the lepton flavor. In other words, if we measure the lepton pairs coming from the epsilon resonance and make the ratio of the branching fraction, then it should give us the unity result. So any deviation from the unity is just a violation of the standard model prediction, and it's indication for the new physics. On the other hand, the leptonic decay of the epsilon resonance, for example, if you see this small cartoon in the bottom, is very important to study about the beyond standard model scenario. For example, next to minimum supersymmetric standard model, which predicts a hot CP odd Higgs, which is denoted as A0. So the Babar has very significant study in this analysis. For example, the A0 decays to lepton pairs, A0 decays to invisible or the hadrons, etc. On page 4, please change the slide. So charge-lepton favor violation, on the other hand, is a clear sign of the new physics, because we already learned about the quark mixing from the CP violation and the neutrino mixing from the neutrino mass measurements. So these discoveries support the charge-lepton favor violation in high rate, but in the standard model, this charge-lepton favor violation is heavily suppressed due to the small neutrino mass. Page 5. So this is the Babar detector and its productivity. And Babar is an international collaboration of electron-positron collider at Stanford Linear Accelerator Laboratory, having 600 people working for last more than 20 years. And we almost produced 600 journal papers and more than 1,000 presentation or the talks in scientific community. So the Babar detector is explained somewhere very details in the paper, or you can have the reference in the paper. But to make the short, we are looking for the charged particles track by using the, for example, the 5-layer silicon bar detector and 40 layers drip chamber, which is mounted in 1.5 Tesla superconducting magnet. We do have the EMC, or the electromagnetic calorimeter, for identification of the electron and muon and the reconstruction energy. We do have a ring imaging serencom detector, also known as the DIRC, which is responsible for identification of the hadronic particles. And then we have the instrumented flux return for muon studies. So basically, Babar work on the epsilon 4s resonance, which is almost exclusively decays in BB bar, and Babar recorded almost like 500 million BB bar event in its lifetime. But between the December 2007 to April 2008, Babar also recorded data for epsilon 3s and epsilon 2s. So you can see that we have almost like 30 inverse 1 epsilon 3s data, which is the sum of the on and off peak, and which is almost like the 20 times more data than CLEO. And so for epsilon 2s, we have 15 inverse data, 15 inverse 1 data, which is almost like 12 times the CLEO. So meaning that the Babar is an excellent resource to study about the epsilon NS resonances, especially n equals 2 or 3. Let's go to the page number 6. And so these are the analysis mode that I mentioned. We are looking for the branching fraction measurements for lepton universality, and looking for the electron and muon track from epsilon 3s for the charge lepton favor violation. In both cases, we use the epsilon 3s data as the signal event. And since these are having the continuum scenario, so we use the epsilon 4s run 6 data with heavy luminosity as modeling the continuum backgrounds. And we also use the off resonance data, for example, epsilon 4s and epsilon 3s off resonance data for study about the discrepancy between the Monte Carlo and data. Let's go to the page number 7. So let's start with the lepton universality analysis. So what we do is we, to study about the Monte Carlo, we use the Monte Carlo event generator. For example, KKMC is used for the tau tau and the mu mu pairs, and BH wide for the Babar, and event gen for generic epsilon 3s decay and so on. We use the KKMC with the initial state radiation is turned off for the signal event, and G4 for the detector acceptance. By the way, see these all the Monte Carlo event generator are used for the lepton flavor violation paper as well. Okay, so for the lepton universality, the event selection started as we have to have two oppositely charged track, one in each hemisphere, and then we go for the dimuon invariant mass and the energy reconstructed from the tau plus tau minus tracks. And these selections, due to the time, I'm not going into details. So based on these selections, our Monte Carlo study shows that for the dimuon, we have the 99.9% purity samples, and whereas 98.9% for the tau pairs. Page number 8. So what we did is for the analysis in lepton universality, we used the off-resonance data to study about or to correct the data in Monte Carlo differences. And then we go for the continuum modeling. So one can see that epsilon 3s decays to mu pairs, and E plus E minus decays to mu pairs continuum decay is modeled by the fact that the epsilon 3s resonance is very narrow, which is suppressed the initial state radiation. And this result, when we plot both of the histogram overlay each other, we can see in the tail region that about 23% of the event continuum event are staying in below 0.98, whereas only 7% epsilon 3s resonance event are in the same space. So by this way, we can model our continuum, and then we can use this template in our continuum background study. Let's go to the page number 9. So what we are doing is we are looking for two variables. One is called the dimuon invariant mass, which is scaled to the center of mass energy. And then we are looking for the reconstructed tau pair energy, which is also scaled to the center of mass energy. And then we go for the cascade decay, because epsilon 3s can decay to the epsilon 2s and epsilon 1s and so on. Okay, so one can see that based on our maximum likelihood fit, we can distinguish the cascade decays in muon cases very clearly, whereas for the tau pairs, these cascade decays are almost invisible. So let's go to the page number 10. And we are looking for the branching fraction ratio, which is basically coming from the fitting to our variables to dimuon invariant mass scaled to the center of mass, and the energy reconstruction of the tau pairs scaled to the center of mass. And then we fit, we use the fitting and then get the parameters. The parameters are, for example, the number of events coming from epsilon 3s to mu pairs, and then the ratio of the decays, for example, tau tau to mu mu and so on. So in the left hand side, you can see the dimuon invariant mass scale to the center of mass peak. A is depending on full data or the all events, and B is excluding the continuum, and C is just the enlarged form of the B. And in the right hand side, you can see the energy reconstruction or the reconstruct energy for the tau tau scaled to the center of mass energy. And based on the systematic, we calculate the all sources, and this is giving us the 1.4% of the total uncertainty. Page number 11. So based on our fitting result and also data MC correction and also the efficiency ratios, our final result for the branching fraction ratio, epsilon 3s goes to tau pairs to epsilon 3s goes to mu pairs is 0.966 plus minus 0.016 in total uncertainties, and which is almost like 6 times more precise measurement than only measurements have in CLIO, which is reported in this paper. And this final ratio is also in 2 sigma of the standard model values, which is 0.9948, which is reported in this paper. Page number 12. So in this case, one can see that the output particle is not mu pairs, output particle is not tau pairs or the electron pairs. Rather, output particles is electron and muon. They are the different flavor in lepton. So this is a kind of a forbidden the standard model. So what we can do reordering the incoming and outgoing particles, and you can see that the reordering Feynman diagram can looks like here, which is studied by the Neutrino and his team. So if we compare this reordering Feynman diagram with our very known muon decay, then we can get some the ratio of the decay widths, which is giving us the branching fraction ratios, branching fraction. And this branching fraction based on the known values, for example, MW or epsilon 3s mass, or W decays to electron neutrino, and then the epsilon 3s decays to E plus E minus, which is given in the particle data group. So based on this calculation, we can have some indirect measurements, but our measurements from Babar data is several order sensitive than these indirect measurements. So there are some other measurements happen, epsilon 3s decays to E tau or mu tau, and from the CLIO, this is the mu tau results are reported in this table, but epsilon 3s decays to E mu is the first measurements recorded by this Babar result, Babar data. Page number 13. So on the selection mode, what we did is we go in two stages. Number one stage is called the free selection, and then number two is called the tighter selection. So in the free selection, or the initial stage of the selection, we are looking for the E mu going back to back, and then the momentum of the track is very close to the beam energy. And since electron and muon are back to back, they should be having the angle between these two tracks should be greater than 179 degree. And the main sources of the background in this case are coming from the tau pairs, muon pairs, and electron pairs, because in electron pairs, the one electron can be fake as muon. In muon pairs, one muon can fake as electron, and so on. So we have to have kinematic skirt and also the PID selection. So that is what we see that in the tighter PID selection we applied, and also use the kinematics criteria. In the right hand side, you can see that the electron and lepton plane. So the event requires to have a circle from at peak at 1, 1, and their radius should be less than 0.01 according to our study, which is given in the bottom plot. So based on these selections and the invariant mass on page number 14. So you can see that the free selection invariant mass measurements for data, black one is the data and the MCs, and in the right one is the after all the selections applied. So from the right hand picture, we have the number of candidate, which is n candidate. We have the background candidate. We have the signal efficiency, and we have the total number of epsilon 3s event. So based on this calculation, our result is 1 plus minus 1.4 statistical plus minus 0.8 times 10 to the power minus 7. So since there is no significant signal, so we set an upper limit at 90% confidence level, which is 3.6 times 10 to the power minus 7, based on this paper given here. Okay, so since this is the new measurements, we can also put some energy scale constraint, and which is given in the backup slides. If you are interested, you can see that. And then finally, the paper is almost in the final stage to submit to the PRL. And on page number 15, this is the summary that Babar has made a significant contribution in this testing the standard model scenario by using the lepton universality, which has this 6 times more precise result than only previous measurement by CLIO, and result is already published. And for the second paper, we do not have significant evidence for the Charles-Lepton favor violation in epsilon 3s to E plus minus mu minus plus, but we set some new energy scale for the new physics, which is given in the paper and also in the backup slides, if you're interested. Thank you very much.
Thank you. So, okay, I see a question from Alexei. So Alexei, go on.
Yes, hi. I'm just wondering. So you have this lepton flare violating bounds for EMU. Would it be possible? Would it be easy to get similar bounds for the radiative lepton flare violating transitions like EMU gamma?
I don't know, but so far Babar has the lepton flavor violation studies in the mu tau, and Clio has also the mu tau, but I don't know that these new things are going to be happening in Babar, because Babar is going to over very soon. So we have to look for the more data which might be possible in future if BAL2 can take this epsilon 3s or epsilon 2s data in future.
Okay, I mean, radiative decays probe slightly different constants in the effective Lagrangian compared to what you guys do.
Yeah.
Thank you.
Okay, do we have other questions? I don't see any hands raised, so I would like to thank you, Hussein. And now the next speaker is Igor Altsibayev from St. Petersburg with overview of recent ALICE results in particle correlations and fluctuations. So Igor, when you're ready, you can start.
Yes, do you see my slides? Hello?
Yes, we see your slides and we can hear you.
That's perfect. So let me start. And yes, let me firstly introduce, of course, the ALICE detector, because my talk is the first one at this conference about ALICE. So ALICE is one of the 4 big experiments at LHC, as you all know, of course, and we have a very good tracking at mid rapidity. And what is crucial for us and a unique feature of ALICE, we have very good particle identification at mid rapidity, mainly thanks to the time projection chamber and to other detectors, and among them maybe time of flight is the most important after TPC. We also have 4 detectors for centrality determination and triggering and 0-degree calorimeters. And in round 1 and round 2 of the LHC, we collected all possible data which was delivered by the collider. So PP, PLED, LED, and xenon-xenon collisions at all energies. And we have analyzed and continue analyzing all these data, of course. And since my talk is about correlations and fluctuations, I just put here some recent papers which were put on archive or published, but only from this year, because otherwise this list will be even longer. And you see by colors topics of these papers: flow, correlations, event-by-event fluctuations, femtoscopy. And of course, it's not possible to cover even half of these papers today because of the very short time of the talk. And I will highlight only some of them, plus some recent preliminary results released for big conferences during this year. And let me start with the first chapter about flow. Just a quick reminder that after the nuclei collision, we have a system which possesses some special anisotropy, which then transforms into the momentum anisotropy of the final state. And we register these particles with their momenta and see this anisotropy. In particular, if we decompose this anisotropy in the azimuthal plane, in the transverse plane to the collision, we will get Fourier coefficients, which are usually called flow coefficients, Vn. And the main one, of course, is the elliptic flow, because it simply reflects the almond-shaped geometry of the interaction region at the beginning of the collision. And the second important coefficient is the triangular flow, which is denoted with 3. And on the next slide, I will show the first part of the results, namely, in 2017, we had a very short but very productive run of xenon-xenon collisions at LHC. And here I show a bread and butter measurement of ALICE, namely elliptic flow, B2, as a function of PT. Why bread and butter? Because, of course, ALICE is very good in PID, and we should deliver this kind of information. So at low transverse momentum, up to 2 GeV over C, we see the famous effect, which is called mass ordering, which means that for light particles like pions, we have big V2 values already at low PT, while heavier particles acquire big V2 values later. So we see kind of a blue shift to the right, which is due to the interplay between elliptic flow and quick radial expansion of the medium. So blue shift, kind of. While at higher PT, above 3 GeV over C, we see another effect, which is called usually baryon and meson grouping. For example, protons and lambdas are grouped together at high V2, while pions and kaons are at lower values. This could be due to quark coalescence mechanism, but this is still under debate. Is it so? And maybe other mechanisms are playing a role here. On the right-hand side, you see the triangular flow, and also for this coefficient, you see mass ordering at low PT. And of course, it is interesting to compare these results with lead-lead collisions, and it turns out that the values are very similar to lead-lead. And we can also compare with models. For example, this IP Glasma is an initial state model plus hydrodynamics from the music, and the final state is scattering from YAR-QMD. And you see that at low PT, this mass ordering, this blue shift is well reproduced in this model. And the parameters, by the way, are the same as were used for lead-lead collisions. You can see this paper for more details. Let me go to more exotic, let's say, observable, namely correlations between different flow amplitudes in lead collisions. So correlations between two different amplitudes were studied before, several years ago. But what about three different coefficients? For instance, V2, V3, and V5. We can subtract all low order contributions, all lower order correlations, and we are left only with the genuine correlation function, which is called cumulant. We can normalize it to average values and see the behavior. Is it non-zero? Is it non-trivial? And on the left-hand side, you see an example from this paper put on arXiv and accepted by PRL for the correlations between V2, V3, and V5 as a function of centrality. And you see the positive values, which is already non-trivial. On the right-hand side, you see another correlation. Again, we take only two harmonics. So in the first case, we have three harmonics. Now we have only two, but with a higher moment. So V2 in the power of 6 and V3 squared. And for this kind of observable, we also see non-trivial behavior, in this case, negative values. And of course, why it is essential, we want to compare with our models, which implement all existing knowledge about the collisions. So we compare with initial state models plus response of the medium. And we see that this kind of data gives us strong constraints on initial conditions and evolution of the QGP, especially on the so-called nonlinear response of the expanding medium to the initial conditions. So this is well accepted by the theoreticians, let's say. And let me continue to the next slide. So lambda polarization. Several years ago, the so-called global lambda polarization has been measured, which is due to orbital momentum of the whole system, orbital angular momentum. But now we study something different. What if some polarization exists along the beam collision axis Z? Indeed, if we go to the transverse plane and see at the evolving medium, we will see that some vorticity of the medium can take place. And for example, due to elliptic flow, a kind of a quadruple pattern of this vorticity can be seen. And if we couple this azimuthal pattern of the vorticity, and this pattern, this vorticity can be transformed to the polarization of particles. So quadruple pattern, polarization of particles like lambda. And if we couple this measured polarization with the phase of the azimuthal angle with respect to the second order event plane, we will see that values are again non-trivial, they are non-zero, they are positive. And we compare this with previous measurements by star, and more or less same results are obtained. And as a function of centrality. And if you go to the function of PT, we will see that slight deviation between star and Eris exists, but in principle, results are very similar. The more polarization along beam axis develops at higher PT. And the only model, which is nearly qualitative model, is a blast wave model, which is able to describe this kind of data. So this is a blast wave model of the expanding medium, which is tuned to V2, to V3, to spectra, and this captures this behavior very well, while the more sophisticated thermal models actually fail to reproduce this behavior. They are not shown here, but you can take a look in the paper itself and see that very sophisticated models by Karpenko and company and also others, they actually struggle from these results. So I highlighted flow, and let me continue with another peculiar measurement. What about V2 of jet particles in PLED and lead collisions? So we can take correlation function, two-particle correlation function, couple it with the information about V2 of the high PT particles using forward detectors, and using some template fitting, extract finally the V2 of jet particles in these collisions. And on the plot, which is very busy, you can see the following. This is a V2 as a function of PT, including V2 of all particles inclusive is shown in black for lead collisions and in magenta for PLED. And you see also here on the same plot V2 of jet particles, which is much lower than inclusive PT, inclusive V2, but nevertheless it's non-zero. You see values which are higher than 0. And also these values are in correspondence with V2 of high PT particles from lead collisions and even V2 of jets themselves, which is already a very unexpected, let's say, and peculiar result, because in lead, okay, we know that there is a jet quenching, but what about PLED? Is it the first indication of jet quenching in PLED, or it is simply due to some final state scatterings? We don't know, and these results are just preliminary, and we are investigating, and more details can be found in the EPS talk of the recent conference. I continue with the next slide, where I show another spectacular result, two particle angular correlations between Xi hadron and other hadrons, sorry, Xi baryon and other hadrons in PP collisions. So for example, for Xi proton correlations, you see correlation distribution as usual as a function of rapidity difference and azimuthal angle difference, and you see some kind of peak at small separations for opposite sign particles. But if we take both Xi and proton to be of the same sign, we see a depletion, so lack of number of pairs at small angular separation, which was seen for other baryon pairs also in this paper, for example. And this result is striking, and it actually challenges a lot different hadronization models. For instance, well-known model of Lundstring breaking implemented in PFA event generator with a standard configuration where there is a break of the string into quark, sorry, d-quark and anti-d-quark pair. Also modifications with string junctions, with color ropes, which overlap with each other. And also EPOS model with core plus corona, where core is a hydrodynamics plus corona is strings. This model is also failing to describe our data. The next slide is about the same, but just projections on delta phi. So difference in azimuthal angles for Xi pion, Xi kaon, Xi proton, Xi lambda, and Xi finally. Even Xi correlations have been measured. This slide is very busy, but the main idea is to compare black points with the models. So you see the PFA with different tunings and EPOS, they all fail to describe data. And by the way, by solid, let's say, black points, you see for baryon-baryon correlations, this depletion, which I mentioned before. So no model can capture this depletion at small separation angles between baryon-baryon pairs, in this case, Xi plus some other baryon. So Lundstring breaking to the quarks is challenged, and in EPOS we need local charge conservation implemented correctly if we want EPOS to describe this kind of data. Finally, let me finish with femtoscopy. So in femtoscopy we measure correlations between particles in terms of as a function of the relative momentum, and we can decompose this correlation as the integral of the product between emission source function, which depends on position, radius of the source, and the wave function. So we can study, if we know the source, we can study the interaction potential or vice versa. And let me focus only on PP data, because we have a huge number of papers which study different pairs of particles in high multiplicity PP collisions in ARIES. And just only to highlight a couple of them. The first one is a recent result for P lambda interaction in high multiplicity PP collision. You see that the correlation is positive at low K star, at low relative momenta. So it is already a result, but it was known. What is more important and interesting is the opening of the coupled channel at around 300 MeV over C. This is because lambda and sigma 0, they are of very similar mass and quark content is the same, but isospin is different. And we can start to feel this coupled channel at this particular difference in relative momentum. Why it is important? Because it put additional constraints, of course, on models, in particular on models which are based on chiral effective field theory. And this is essential also, of course, to study possible existence of lambda hyperons in the core of neutron stars and so on. So astrophysics is also very important. And just to flash here, another result is the first measurement ever about proton-phi interaction. So our statistics allow us to see that there is an attractive interaction between proton and phi at small k star. And if we fit it with the Rudnitsky-Boschitz model, we will see that this interaction is mostly due to elastic processes. We see that imaginary part of the scattering length vanishes. That means that inelastic process is at least very small. So elastic interaction should dominate. And finally, of course, I cannot cover everything, so I just flashed several results. And I just want to say that we continue to analyze data from run 1 and run 2, and more exciting results from already registered data will be available. And meanwhile, we are preparing to run 3, where acceptance of phase detector will be increased, statistics will be increased as well. So more interesting observables can be measured in run 3. And last but not the least, some feasibility studies have been done also for possible oxygen and proton-oxygen runs, which will be possibly at LHC in several years. You can take a look at this paper. Thanks a lot for your attention.
Okay, thank you. Are there any questions? Okay, I don't see any, but can you, I have one then. Can you clear a difference between new 2, new 3, and new 5? I mean, you talked about 2 and 3, but you didn't mention 5 in your introduction.
Ah, you mean Fourier harmonics, the fifth harmonics. It's simply just the fifth coefficient in front of the sign. And maybe I can just expand a bit that V2 and V3, they are very closely related to the geometry of the collision, namely to the shape of the interaction region, plus fluctuations in the nucleon positions, while V5 also is very sensitive to the so-called nonlinear response of the medium. So if we have quark-gluon plasma, which evolves somehow, it actually gets, so for V5, we get contributions from lower order harmonics, lower order special anisotropies. That's why it's very important how these low order harmonics contribute to the high order momentum anisotropic coefficients, because it is very sensitive to the shear viscosity of QGP and so on. So how all these special anisotropic coefficients start to influence each other at higher Vn values, higher n values of the coefficients. So you see my point, yes? So we start to probe QGP properties more precisely with higher harmonics.
Okay, thank you. I don't see any hands raised, so thank you again. And the next speaker is Paolo Gandini from Milan, who will talk about spectroscopy at LHCb. So,
hello, can you hear me?
We can hear you, but I don't see your slides yet.
Okay, I am now sharing my slides. Now?
Yes, please go.
Okay, so can I tell me when I can start?
Yes, you can start.
Okay, so thank you very much for having me here. Of course, it would be much better to be in person, but I would really like to show this online as well from Milano. So this talk is about spectroscopy at LHCb. That is a kind of a hot topic. And as an outline, okay, this is the LHCb detector. This is the first talk about this, but I'm not gonna go into the detail of how the detector is made. And as this is a very short talk, I will only cover just a very, very very short set of recent results, okay? And the LHCb experiment is an extraordinary regime for spectroscopy for both conventional standard model states and what we call exotic. And LHCb again offers excellent tracking PID, which is a unique, like a very important feature for spectroscopy, and also a high trigger efficiency. And plus we benefit from the high cross-section at LHC and the energy. This is the shopping list of the few analyses I will cover. As you see, they're very recent, I mean a few weeks old. Plus some actually are already being shown these days at conferences, but there is no paper yet on the archive and it will be posted soon. Okay, the first, I cannot start without talking about the observation of this new TCC plus state. The paper is in preparation, and this has been presented for the first time at TPS just last week, the link. And this means that the double heavy spectroscopy is now effect at the LHCb physics program, which is a striking thing to be noted. And also just charmed state with double charm content, in this case are actually D0 mesons, but they are the same type, with the same charge in the final state. And it manifests itself as a very narrow peak just above the threshold. Okay, and as you can see here as a preview, it's kind of strikingly high compared to the level of background. And there is a lot of hype generated with a lot of nice articles also published for the outreach. And here, just an overview. The TCC should have new quark content of CC, U bar, D bar. And charged double charm state, as I was saying before, is manifestly exotic. And it manifests, we see it in narrow peak in the D0, D0 pi plus meson mass spectrum. Remember that the D star plus goes to 100% D0 pi plus. And the new state is just below actually the threshold, the D star plus D0 mass. Okay. And the sample, as you can see, is extremely pure. There was a kind of a considerable involvement in selecting the two mass windows. Then one can do like an analysis subtracting fake D background using a 2D fit to the two invariant masses plus of the pion. And of course, one can check the opposite side sample where there is obviously no evidence of any somehow of this kind of enhancement. And we measure actually a yield of more than 100 events in here, and the mass window is very skewed. Actually, there is a lot of details in the paper about how to shape this signal PDF, and these are the measurements that are extracted from the data set. And this observation of a double charm tetraquark candidate, let's call it like this, nicely complement actually some previous studies on states with double heavy quark content. That's why I said it's now effect. And for instance, just last year, like exactly last year, 1 year ago, LHCb announced that the possible discovery actually was more an evidence of a 4-charm tetraquark state in double J psi, as you can see here. And also, I remind you that since 2017, we have excellent observations in several channels, actually different of Psi CC++, which is the first double heavy baryon observed with, as you can see, let's say thousands of events of signal. Okay, and just to complete, there are also new searches that are ongoing on other final states, and but in the other searches involving BC states and the omega CC, we didn't find any significant sample, and therefore we put upper limits on the production cross-section on the relevant mass window. This is essentially good for the upgrade phase. This is another very interesting result concerning spectroscopy. And again, this is brand new and it has been posted on the archive last week. So it's 1 week old, the result. And this sits on other type of analysis involving pentaquark searches. So this, before we were talking about tetra, this time it's pentaquark. This is LHCb, of course, has investigated many modes in the past involving J psi proton system, but in baryons, so lambda b. There are also evidence of states in J psi lambda, which is the equivalent, but with strangeness. And this analysis relies on the amplitude analysis of flavor untagged B sub S D0 into J psi PP bar. Okay, the decay has been observed and reported in 2019. The link is on the slide. And now it's time to do the amplitude analysis. And with a sample of something shy of 800 signal events. And if you see the final state, this is really, really interesting because of the symmetry of the Dulles plot and the fact that you have a proton and an antiproton in the final state. Here you can see the B0 peak and also the B sub S peak with pretty much as super high purity that makes easier the analysis, the Dalitz plot. So next slide, as I was saying, this is the final state. It's very interesting because you can exploit the different projection. For instance, you have JSI proton where you look for pentaquarks. Okay, then of course you have JSI antiproton, and you should be kind of symmetric, so you can use only one amplitude, or at least the amplitude should be symmetric. Okay, the Dalitz plot. And then you can look at PP bar, where you could have gluon like contribution from these global type of states, and you can add amplitudes for this. And the results is that we find evidence for new structure in JSI proton and of course in the JSI antiproton systems, while there is no significant contribution of anything like global type that can go in PP bar. And these are this Dalitz spot, the projection with the light, with the nice axis, and also here are the quantities extracted from the pentaquark amplitude. So this is to finish that there is a lot of things that can be done in this, and now we are also using mesons, which is kind of nice. And slide number 8 instead, I move back to something that is more like normal standard model. Sorry for the repetition. And with the observation of 2 new excited states, because we can do exotic, but it's also important to fill up the missing states of the standard model. And for instance, we can use the huge abundant sample of lambda B, which is saved on disk, for instance, to look for higher up resonances. And this has been done in the past, and this time we are opening up with states with K-pi, for instance. And if you see here, the number of yields we have that we use are huge. We're talking about millions of events. And you can see that in lambda B K-pi, you see 2 very nice peaks, kind of relevant, especially if you consider the wrong sign sample, which is on the right in there where nothing is seen. And if you go to the next slide, you see that here it's a prompt reduction. The states are consistent with theoretical prediction of the 1D excited doublets, the first time we observe this type of events, and also one can do a projection and see where the intermediate resonance pattern. And of course you see that if you do the projection, the first peak goes into sigma B as intermediate state, and the other in with the star. That confirms a bit of the ranking of the excitability doublets, and these are the experimental. And just to finish off, a few kind of remarks of other conventional spectroscopy that is recent. This has been posted quite recent as well, and this is the new observation of omega B new final mode in XIC K-pi again. And this low mode is considered the first time we consider it, and is the first observation. And also we use this to look for the XICK final states where we know we have excited omega C baryons, and we confirm and measure the production rate for this. And also for these final states, since the Q-value is lower, we can also have for free a precise mass measurement of the omega B, which is always welcome because there are no much yield here. And also it's nice to note that here we have the first observation of a mode which actually has a higher yield compared to the control sample. And omega B's are kind of like rare objects because the cross section is quite low. So now we are, exploring modes, and we're building up yield of also other studies that can be done. And as you can see here, one can project the Dalitz plot to see intermediate resonance. And here you have on the right, you see 4 of them. And actually, it's nice to compare with the inclusive observation. We actually observed the 5 of them. One is missing at the top because of the lack of statistics, and in the paper there are, of course, the relevant numbers and expectations, and also an upper limit of missing resonance. To conclude, this is a plot that is circulating, and are the hadrons discovered by LC. And these are mostly done by our experiment, but also CMS has a very fair share in this. So it means that also other experiments, not only us, can do nice spectroscopy as expected, of course. And we're now building up in this table, which is created by our colleagues, Patrick Koppenburg. And we are now at the number of 62 new hadrons discovered or at LSC. And just to know that this summer we have 3 hadrons more added to the list. So this plot is growing extremely fast, so 62 states in 10 years, let's say. And this is also the time, so you can see that also the improvement is pretty much costed. And so to conclude, this was a very short talk on the latest result. As you see, latest like 2 weeks, 1 week. And all the results are exploiting our very large data set using RAM 1 and RAM 2. And of course, more research is ongoing. And plus, you should remember that we are upgrading. So this is now, this is the situation, but of course, we expect to improve this. And we expect also a bright future ahead, both for exotic and conventional, as soon as we get new data from the upgrade.
Okay, thank you, Paolo. Do we have any questions on this talk? Okay, I don't see any hands raised, but then I can ask on your slide number 7.
Yes. Here.
Okay, so if I look on the left side plot, so the yellow should be where the peaks are, but basically, how can you correlate this plot with the 2 plots on the right?
Well, this is the Dalitz plot, okay, with the bins chosen for the analysis. Okay, so these are just the number of events in the bins. Then here, these are the projection you get from the fit with the components superimposed. But these are just projection of the amplitude analysis of the full system. So it's kind of difficult to extract information for a kind of 2D plot because it's very skewed. In here, you see bumps, let's say, but what gives you the evidence is actually the fact that you cannot fit the sample without including an amplitude. So that's why you see this. So this doesn't fit if you don't include a pentaquark state.
Okay, thank you. Any other comment or question? I don't see any hands raised, so I would like to thank you, Paolo, again.
Thank you.
We can move on. So the next speaker is Rongkun Wang from Harvard with measurements of multi-boson production, including vector boson fusion and scattering at Atlas. I will start timing you.
Finito, Pichi.
Can you?
Sorry,
no,
I will mute.
Slides are very small, so can you?
Can you hear me?
Yes, I can hear you, but your slides are very small, only in the middle of my screen.
Sorry. Let me.
Your whole desktop is very small.
Good.
Okay.
How about now?
Now it's great. So you can start whenever you're ready.
Okay, so I'm gonna talk about the measurements of multi-boson productions, including vector boson fusions and vector boson scattering at the Atlas. So why are we interested in multi-boson physics? We are interested in mostly the electroweak productions, and because it's a powerful tool to probe the standard model mechanisms. And this includes vector boson scattering and fusions that directly probes the gauge boson self-interactions, and that is related to non-abelian structure of the electroweak interactions. And in the bottom of the spectrum of the cross-section of those standard processes, you can also see we are doing analysis. We are going lower and lower in the cross-sections, and that provides us discovery opportunities because those processes are not seen before. So here are the outline of my talk. I'm gonna go through 4 analysis, 3 VBS processes, includes electroweak ZZ plus JJ analysis, and then Z gamma JJ fiducial cross-section measurements where Z decays to 2 leptons, and then the search for Z to nu plus gamma JJ, and then the observation of tri-W process alone. So the observation of electroweak ZZ-JJ is a very rare process with a fiducial cross-section of around 1 femtobar, and you can see on the right is the example of Feynman diagrams. And the Higgs processes are included, and that prevents the unitarity violation at the TeV scales. And it is also sensitive to triple gauge coupling and quadric gauge coupling vertices. So in this analysis, 2 decay channels are studied, including ZZ to 4 lepton decays and ZZ to 2 lepton 2 neutrinos. And the VBF topologies are utilized. So we apply rather large delta of the rapidity of the two tagging jets, and then require the dijet mass to be bigger than a certain number. Here's the GEV. So the QCD control regions are reverting the cuts above to give a constraint of the QCD production of ZZJJ. And then the BDT is trained to distinguish between electroweak and the QCD ZZJJ using a total of 12 variables and largely benefiting from the jet-related ones. And they include, for example, MJJ and delta rapidity JJ and PT of the jets. And also the rest includes the kinematic variable of the Z themselves. And here are the example of the data versus Monte Carlo post-feed. So you can see that they have generally well agreements in the control region in the left plot, and then 4 lepton signal region in the middle, and the LL nu signal region on the right. And we carry out simultaneous feed on both the electroweak and QCD component in all the regions on the BDT scores, and derive a electroweak signal strength of 1.35 plus minus 0.34 with a significance that is derived as 5.5 sigma, where the expected is 4.3. And the QCD signal strength is given as 0.96. And the next analysis is Z to LL plus gamma JJ. It also probes the non-standard model neutral quadric gauge couplings. Its VBF, similarly, the VBF topology is 2 tagging jets have a large rapidity gap. And here the jet cuts are optimized to be delta YJ bigger than 1. And the main QCD background is estimated from the Monte Carlo, while the Z plus jets background is estimated from the data-driven method. And those are the major backgrounds. The centrality of the LL gamma system is defined relative to the tagging jets as this formula, and the signal distributions are largely have this zeta value smaller than 0.4, so they are defined as the signal regions, and then bigger than 0.4 is the control regions to constrain the QCD. And again, simultaneously, we do a feed in the signal region and control regions on the MJJ distributions, and floating the electroweak components and QCD components differently in the signal region and the control regions. And then we derive a electroweak fiducial cross-sections of 4.49 compared to the prediction of 4.73. And worth mentioning that this is an observation of well over 10 sigma, as you can see in the left bottom plot. That's quite significant at high MJJ regions. another cross sections, including the QCD inside, is derived, where the cross section is given to be 20.6 femtobar, and that's also quite close to the prediction. And the next analysis is Z2 nu gamma JJ, and the signature would be 2 jet 1 gamma and 2 nu, where also we have a large separation of the tagging jets and with large dijet invariant mass. So this analysis is observed with a 5.2 significance. We apply a delta phi JJ cuts to suppress multi-jets events, and also define a similar centrality of bigger than 0.4 to extract our signals. So there are many different control regions in this analysis that are used to constrain the to constrain the QCD Z gamma and W gamma background during the feed. And so the measured signal strength is given to be 1.03 plus minus 0.25. And here's the plot of the photon energy. As you can see, the comparison of the data background that shows our modeling is relatively well. And this analysis also sets a limit on the invisible Higgs decay, as you can see, just replace the Z with the Higgs. And then I will move on to the triboson processes. This is one of the rarest standard model processes that is sensitive also to triple gauge coupling and also quadri gauge couplings. Besides the radiated 3 bosons from the quarks, also the off-shell WH productions, where Higgs decays to WW, is included as a signal. But this one will have 1W as an off-shell of the mass shell. And in total of 2 channels are used in this analysis. One is tri-W decays to 2 lepton plus 2 jets, where the 2 lepton are required to be same sign the lepton, same sign. And furthermore, channels are separated based on the lepton flavors E, mu, and mu. And there's also a 3 lepton channel where there will be 2 lepton with the same sign and 1 lepton with the opposite sign. To suppress the Z backgrounds, we require no same flavor opposite sign lepton pairs. And this is the in the signal regions, we use dilepton MLL and missing ET to suppress the Z plus jets. And then we train separate BDT in the 2 lepton and 3 lepton channels. And the variables include, just as an example, MJJ, PT of the jet and jet multiplicity, and dilepton mass, PT of the leptons, and also the missing ET component, since we have neutrinos in our final state. And the main background is the WZ that is constrained by same flavor opposite sign control regions during the simultaneous feed with the signal. And you can see that in the right plot, there are 3 bins on the rightmost is the control region bins that is quite pure in the WZ, so that gives us a good constraint. And then there are some data-driven backgrounds, including non-prompt backgrounds, gamma conversion from V gamma, and the charge fleets backgrounds. They are separately estimated in their own dedicated control regions and then convert back to the signal regions. And the other standard model backgrounds are given by the column. So here I'm showing you the after feed result of the 2 lepton channels. The left plot is the dijet invariant mass, and the right plot is the BDT. You see some separations between the signal and the backgrounds. And here is the 3 lepton channels post-feed results. The leftmost plot is tri-lepton mass, and the middle plot is the missing ET significance. And the rightmost plot is the BDT output. Here you see an even larger separation between our signal in the yellow and the rest of the backgrounds. So the signal strength is measured to be 1.66 plus minus 0.228, where the other normalization factors are the WZ, signal strength separated by the jet multiplicity. And in total, we observe a significance of 8.2 sigma with a 5.4 expected significance. And we also extrapolate this to production cross-section measurements of 850 femtobarn. So in this table, you can see the breakdown of significance. And the 2 lepton give us more significance sensitivity than the 3 lepton channel. So in summary, on Atlas, the VBS electroweak DDJ process is observed with the significance of 5.5 sigma, and where the expected is 4.3. And the fiducial cross-section of Z gamma JJ Z to 2L process is measured to have a cross-section with 4.49. And the Z nu gamma JJ is observed for the first time with a 5.2 significance, and the tri-W process is observed also for the first time with 8.2 significance. Thank you for your attention.
Okay, thank you, Ronkun. So do we have a question from the audience here? Okay, I don't see any hands raised. So if you can go back to your slide number 4.
Okay.
So here you sum up all the processes as a signal process, right? All this, and there is no destructive interference or something like that, I assume.
No, they should be modeled inside the Monte Carlo. I don't think there's interference effect.
And another question is, you mentioned on Z to nu gamma plus 2 jets limits on invisible Higgs decays. Do you have any plot or number of how that compares to the total limits on invisible Higgs decay?
Yeah, I don't have the plots on top of my head, but
it should be much smaller than from other searches. I just wanted to see if you have anything to compare to. Okay, I don't have any other questions, so I would like to thank you again, Ronkun. And then we move on to Sergey Petrushenko from MSU that will tell us about heavy ion physics at CMS. So, Sergey, when you're ready.
Hello, can you hear me?
Yes, we can hear you. If you can go. Okay, now you're in full screen, so you can start whenever you want.
Okay, so you can see my slide. Okay, thank you very much. I will have a talk about heavy ion physics at CMS. CMS is a very nice heavy ion experiment. We have a very good tracker, wide range calorimeters, electromagnetic and hadronic. And also very, very good muon chambers that together with magnetic field close to 4 Tesla give us possibility to investigate heavy ion collisions. All started almost more than 10 years ago. In our CMS control room, we get the first collisions, and since this very interesting point, we have more than 100 published or submitted heavy ion physics CMS paper, and together with some preliminary results, which already are very interesting. But of course, during my very small presentation, I can't give you any detail about all this paper. So I try to concentrate on the result of the last 2 years since the last Lomonosov conference, where we were already presented the results of heavy ion physics. If you say about CMS heavy results, we can separate it somehow to the 3 points. It's about global pictures of heavy ion collision, about multiplicity, energy flow, hard probes, or hard objects like jet, diamonds, etc. And also some a kind of exotic things like heavy ion effect in proton-proton collisions, interesting things in proton-lead and xenon-xenon collisions. And CMS collected many data on all of such kind of collisions. And we have many things to present to you. If you say about charged particle multiplicity and transverse energy density, we can see that our latest results show for us a good power law dependencies for energy dependence in collision for charged particle multiplicity and transverse energy density. When we say about the flow, just from the very few days of the collisions, we already see in our CMS control room, in our monitor, Mandel shapes events which give us calorimeter sign of the view in azimuthal plane of the collision, and we can see it in very easily things that we have non-central collisions when non-symmetric volume of the coagulant plasma or something like this give us such pictures. Of course, I hope you know about the ridge effect. CMS was first to find this ridge effect in proton-proton collision, and we say that some heavy ion pictures proton is already ion, and we see a picture close to the C and the Riggs collisions for heavy ion collisions. We also find it in proton-proton collisions, then we find it in lead-lead collision and also in proton-lead collisions. From one of the very latest things here, interesting things that if you have a look in ultra-peripheral proton-lead collisions, we find this that also a correlation with gamma proton interactions within such a kind of collisions, and the single particle flow coefficient V2 is larger for gamma proton enhanced events that for minimum bias collisions. We also see a flow for charm and beauty, but what's about if we try to see open and hidden charm, we see this dependence of V2 versus VT, but almost no significant flow for open beauty for non-prone D0. Another things, we try to measure epsilon V2 in proton-proton collision, and in contrast to GPSI methods, we can't see any azimuthal anisotropy for epsilon methods. Another interesting result is about mixed height ordered anisotropic flow in lead-lead. We find all of them and this almost similar dependency, PT dependencies, but we see that the viscous hydrodynamics doesn't provide a very simultaneous description of it, and this anyway need to be understood later. Xenon-xenon collisions, we can see that this is a kind of the bridge between proton-proton and lead-lead collisions within central of the periodical system of the elements. And we also have result here, for example, V2 for xenon-xenon collision in comparison with lead-lead give us interesting things that an magneton of V2 coefficients for xenon-xenon is larger than those found in lead-lead collisions for the most central events. Maybe this because of the larger fluctuation of the component in lighter collision systems. Another things, we try to see some hydrodynamical models and try to have a look, compare it with the results, and see that if we try to use non-spherical xenon shape of the nuclei, we see a better comparison with the result if we think that xenon will be an ideal sphere. What's about hard probes? There is many kind of optic checked here that we can test quark gluon plasma. The main factor here is array. With that we compare something measured in light-light collisions and then divided to proton-proton reference with some and then scattering to scale it. Very interesting results. I very much like this picture about upsound suppression in light-light collisions. CMS can observe a very nice and real and sequential suppression of all upsilon family. And we don't find any sign of the third component of this family, even in the very, very much statistic in light-light collisions. If we have a look on this in proton-light collision, we also see suppression of upsilon, but not so much. We see all members of the family, but with some suppression. And in these slides, we see the comparison of it. We see a very good ordinate of binding energy. Of course, the largest suppression is for light-light events when, as I said, we can't see any sign of the third component. But we see also the good suppression for proton-light collisions if compared with proton-proton. This is we have published first evidence of these strange particles in proton-proton collisions. Of course, we don't, for the moment, we don't know what is these particles and how it look like, but we was first who find this particle in lead-lead collision and hope these results help to understand the nature of this particle. Another interesting result about measuring in comparison with B0 and B plus mesons. B0 mesons is observed with good statistical significance for the first time in nuclear collisions. And we get some comparison with B0s. We don't see no significant PT dependencies of B0, B2 ratio. And model prediction is reasonably agree with data. This you can see the first search for top using lead-lead collision, and we find it, and the measured cross section of it with in two different channels in a good expectation from QCD predictions. We get some result and publish on it, and we have close to 4 standard deviation for both two methods with the significance of this measurement. Jet quenching, I think you know what is this. Proton-proton, we have two jets in almost the same in different direction opposite to each one. But in proton, in lead-lead collision, sometimes we see that we see one jet, but small jet or no jet on the opposite side. And CMS together with Atlas was the first who measured this is in LHC energies, and with this demonstration of this jet quenching. Very new result here. We try to do jet radius scan when we get when we use the same method with cone, but with different radius of it, and we see some development, some dependencies of this measurements in comparison for with standard 0 to 5 cone. And from my point of view, the very interesting thing here is that our PyCon generators, this was developed in our laboratory, have a good agreement with the data, and I hope it will be a very good demonstration that this PyCon generator works very fine. Okay, that's about summary. We have many interesting heavy-end results with CMS for different systems, and we hope that later in round 3 and round 4, with upgraded CMS detector, we provide more exciting opportunity. Please stay tuned. And in the very end of my talk, I would like to show a few pictures from my and my wife and daughter's telephones. We was very happy to be 2 years ago in the auditorium, central auditorium physics department, which we spent so many times when was There was a student with me and my wife, and was very happy to show it to our daughter. It's very hard now to present this talk from home, not from the real auditorium, not to see you face and face, but I hope that next time in 2 years, I will see you in Moscow and in physics departments. Thank you very much.
Okay, thank you, Sergey, for this nice talk and to present us with a lot of results. So I see one hand raised. So Mikhail, please go and ask a question.
Thank you very much, Sergey, for interesting report. But could you say some shortly about the searching for quark-gluon plasma?
Ah, we see it. Already, you know, this is a big discussion. What is quark-gluon plasma? There is so many interpretation of it during many theoreticians. For example, some people think that at RIX we already have a quark-gluon plasma. I think we have something like quark-gluon plasma. At least results with hard probes show us absolutely well about upsilon suppressions, gypsy suppressions, of course, jet quenching. We already see it. And what we have for the soft physics with all the Ricci effect, when we see as that the proton is the same as the lead collisions with all this Ricci effect, etc., etc. So I think we can find a kind of quark-gluon plasma, but what is this? How it's look like? It's a question for the future, for the next energy, next systems, something like this.
Okay, thank you. Thank you.
Okay, are there any other questions from the audience? I have actually a few. When you were talking about open charm and beauty, what do you mean by that? That was on slide 10.
Okay, wait a little bit. Okay, this is what we have for gypsy, for prompt and non-prompt gypsy and D-zeros, and how it compare with models, and how it looks in different generator, how they try to describe us. And we too measured for these kind of particles.
Okay, but what is the difference between open charm and hidden charm? One is coming from which and the other from which particle?
Okay, if you can see from the picture, open charm, this is from D-zeros. Hidden charm, this is from gypsy.
Okay, thanks. And then it's really nice to see that you see a top quark production in heavy iron.
Yes, yes. Yeah, really
but I actually have one question related to that. How do you tag on B-jets in heavy ions? Are you using only soft muons, or are you using more sophisticated taggers?
Well, I can't give you such details of this analysis. I think that they use some prediction of the theory comparison with the data and using a full simulation of the detector and looks and use some prediction for it.
I will check. I will check.
I think from generator, some generator like PFA, something like this.
Okay.
Because of course this is just a question of how much we believe that this is a big jet, but there's some prediction for it based on the theories.
Okay. Okay. Thank you very much. Since we don't have any other question, we can go on to the next speaker. That's Natasha Vukashinovich from Vincha. That will now we move on to the future colliders. She will tell us about CP violation and Higgs production in ZZ. Okay, Natasha, I think that we see. No, Sergey, we still see your desktop. If you can stop.
Okay, so sorry, I tried.
Yeah, just you should have a stop sharing button on top. Okay, Natasha, I think that now you can share your screen. You see my slide now? Yes, but please go to the full screen. Okay. And start. Is now better? Yes, and start when you feel ready. Okay, thank you. So I have a great pleasure to give a talk on CP violation in ZZ Fusion at 1TV IRC on behalf of the IRD collaboration. Differently from other speakers that are showing more or less final results, I'll present current state of the analysis at Future Collider that is exploring CP violation in Higgs vector boson vertex. This kind of study is new and rare. So firstly, I'll talk about the strategy for exploring CP violation in Higgs sector. Then I'll discuss method of the CPV mixing angle measurement. Experimentally observed size of the CP violation is not supported by the formalism. New sources of the CP violation beyond the standard model are necessary. Some of the new sources may be introduced in an extended Higgs sector, where Higgs boson could be a mixture of a scalar and pseudoscalar state. So far, there are very few results of CPV mixing angle. IRC result at 250 GeV is the most promising in the Higgs to tau-tau decay. For more details about this analysis, see Daniel James' talk. Staged IRC physics program offers possibilities for CPV study also in Higgs vector boson vertices. As all of you know, the International Linear Collider is a high luminosity linear electron positron machine that will run at different energy stages from 250 GeV up to 1 TeV. Beams will be polarized. IRC is aimed as a Higgs factory, and it offers precision studies in the Higgs sector. A few words about IRD detector. Silicon pixel vertex and gaseous tracking detectors enable excellent check momentum resolution. Also, high granularity calorimeters enable jet energy resolution below 3.5% for high energy jets, and also with particle flow approach that is key feature in reconstruction of particles. All detector performances are tuned in accordance to the IRC physics program. As is already mentioned, standard model like Higgs boson could be a mixture of scalar and pseudoscalar states, where psi presents CPV mixing angle. There are numerous Higgs production processes that can be exploited at linear machines at various center of mass energies, such as Higgs Strahlung, WW fusion, and ZZ fusion. In order to probe Higgs vector boson vertex, both Higgs production and Higgs decays can be studied, as is shown in the upper plots. CP violating term is added to Lagrangian. It is presented in red. Due to the relatively high statistics available in one-inverse autobahns at 1 TeV, suppressed CPV effect can also be studied in vector boson fusion. Information on spin orientations of vector boson states is contained in the angle phi between the production planes. Angle phi is actually angle between unit vectors orthogonal to those planes. Unit vectors could be in the same or in the opposite hemisphere. In our case, or in ZZ fusion, unit vectors have the same direction. So angle phi can be retrieved through the Arcus cosine function in a way presented in this formula.
Sign plus or minus retain natural domain of arcus cosine function. In our case, sign is plus. While parameter A defines how positron plane is rotating with respect to the electron plane, direction of Z boson in electron plane regulates the notion of direction by the right-hand rule. Here we can see 5 distributions at the generator level in case of ZZ fusion and Higgs to WW decays. These distributions are got as a cross-check of this reference. We can see that 5 distributions are correctly reproduced at the generator level for both Higgs production and decay vertices. All distributions are obtained for pure scalar state. Now we come to the method of the psi measurement. We consider 2 decay channels, Higgs to Babar and Higgs to WW fully hadronic. In these channels, we cover most of the Higgs width and also avoid high cross-section E to E gamma background that is presented in plausible reconstruction. Firstly, we select ZZ fusion in our sample that is mixed with Higgs strahlung. This is done using the cut on the lepton invariant mass. Then we isolate 2 electrons, reconstruct angle phi, and employ MEA in suppression of signal from background. Next step is fit of psi directly from phi distributions, and the statistical uncertainty of the measurement will be derived from repeated pseudo experiments. So ZZ fusion is the channel process. About half of the full statistics is available in the tracker because electrons are scattered forward. However, 1 TeV is the optimal energy for this study because at higher energy stage, more electrons are scattered forward, while at 500 GeV cross-section for ZZ fusion is smaller than at 1 TeV. All samples are normalized to polarization -80 plus 30% with factor that is obtained in the way presented here. Goal of the pre-selection is to find electron spectators from ZZ fusion and reduction of high cross-section backgrounds. Requirements that are applied for electron isolation are cut on track energy, then cuts on transfers and logging to the null input parameters, cut on the ratio of energy deposited in calorimeters, and polynomial cut that actually optimizes cone energy versus track energy of electron candidate. In this table, we can see for signal and relevant background processes cross-sections, input number of events, output number of events after pre-selection, and appropriate pre-selection efficiencies. We can see that for signal pre-selection efficiency is about 80%, while for background it is per-mil level. Current signal statistics is small. Background samples with stars are actually considered with ideal BTAG performance. Background statistics after pre-selection is 2.5 times larger than signal. And in these plots, we can see 5 distributions after pre-selection for signal and background. Important thing here is that background is CPV insensitive, so it would not influence our measurement. MVA is trained with 14 sensitive variables. In these plots, we can see the most sensitive variables. BDT efficiency is about 70%, and background to signal ratio is reversed in favor to signal. Of course, this is just preliminary results because in this analysis, only quarter of the available signal statistics is analyzed. Here we have step plot after the NVA and phi distributions for signal and sound background. As we can see, shapes are maintained, but yet we can see large fluctuations in case of signal. However, we plan to increase signal statistics in order to improve our measurement. This brings me to conclusion. Only few results of the CPV Higgs mixing angle are available from the future projects, primarily in the Higgs fermionic decays, but there are also possibilities to probe CPV in other Higgs channels. 1TeV-IC offers optimal statistics to probe CPV also in Higgs vector boson vertices. A sensitive angle phi between Higgs production planes is reconstructed in ZZ fusion with expected behavior for psi equal 0. Result will be further improved since only quarter of available signal statistics is used. On the other hand, background phi distribution is CPV insensitive. It is effectively suppressed with the stage event selection. And of course, further improvements are on the way. Thank you for the attention.
Okay, thank you for this nice presentation. So are there any questions from the audience? Okay, I don't see any hands raised, so maybe I can ask one question. So here you say on this last slide, you say that background distribution is insensitive, but then in slide 17, you have this phi distribution, but it is difficult to see that you can actually distinguish that much between signal and background. I mean, you do see some separation, but is it because of lack of statistics or?
Actually, yes, that is because of the small statistics, and of course we haven't made final decision do we perform MVA or not, because we suppressed background very well and already at the pre-selection level. So we'll consider will we directly fit background after the pre-selection, and of course signal statistics we will improve.
Yeah, you can also maybe try to consider some two-dimensional distribution of phi in one dimension and MVA output in the other. So maybe you can see some better separation there.
Mm-hmm.
Okay. Anyway, I don't have any further questions. I don't see any hands raised. So Natasha, thank you again for presenting this.
Thank you very much.
And the next speaker is Amara Ahmad from CERN that will tell us about Atlas-style calorimeter performance and upgrades toward higher luminosity. So I see your slides. They're still not in full screen.
Okay.
Okay, now they are. So as soon as you're ready, you can start.
Okay, thank you so much. So I am Amara Ahmad, and I will give a general talk about the Atlas-style calorimeter performance and its upgrade towards the high luminosity LHC. So as it is a very wide topic, so I will try to summarize it as much as possible. Okay, so So a little about the Atlas style calorimeter, which is the central hadronic calorimeter of the Atlas experiment, and it is composed of the layers of steel, which act as the absorber medium, and the layers of scintillators, which act as an active medium. And the tile is divided into 4 longitudinal sections, as you can see here, 2 on the central and 2 extended barrels. And the main basic principle of the tile gal is to measure the light which is produced by the charged particles into the plastic scintillators. And its main purpose is to perform the precise measurements of hadrons, jets, and missing transverse energy. And it also provides a signal to level 1 calorimeter trigger. So about the TileCal readout, it's organized into 4 partitions. 2 is located in the long barrel region and 2 in the extended barrel region. And here you can see the module, a single module of the TileCal, in which the scintillating tile is read out by the 2 wavelength shifting fibers, and these 2 fibers go along the side of each module and grouped into geometrical cells constituting these 3 layers of cells, which are the A layer and the BC layer and the D layers. So, and each of these cell is read out by 2 photomultiplier tubes, and which constitute up to 10,000 PMTs in the whole detector. So about the calibration system in the TileCal, to monitor the behavior of all the detector components, we have a dedicated calibration system at each level of the signal reconstruction. So, and the reconstructed energy of the TileCal channel is given by this equation, where these C factors are the characteristics of the detector, like C1 is the characteristic of the scintillator and the cell, C2 is the characteristics of the PMT, C3 is the characteristics of amplifier, and C4 is the AC counts per volt. And we calibrate all of these factors through our 4 dedicated calibration system, which are cesium, laser, charge injection, and minimum bias system. So I will talk about these systems in the following slides. Cesium system. So in cesium system, we have a movable cesium radioactive source which passes through the body of the calorimeter a few times a year, and it calibrates the entire optical chain, including the scintillators, fibers, and the PMTs. And the precision of the cesium calibration in a typical cell is about 0.3%. On the right side, you see the plot. In which you see the response of the cesium in all the layers of the TileCal deviation from the expected cesium response during the entire run-to period. And in the red points, you can see that these are the cells of the A layer, which are the most exposed cell to the beam because they are the nearest to the interaction point. So they drifted much larger as compared to the cells reading the cells of the BC and the D layers. So in charge injection system, we inject a known charge into the ADC and measures the electronic response. And this charge injection system calibrates the response of the ADCs, digital gains, and linearities in the dedicated runs, which we take 2 times a week. And in this figure, you see the detector wide the charge injection constants average over all the high gain ADCs. And the precision of charge injection system is about 0.7%. Then we have a laser system in which we send the laser light pulses of 532 nanometers to the PMTs in the dedicated runs. Also, we send these pulses during the collisions, which calibrate the timing, and also we can study the PMT nonlinearity. And here on the right side, you can see the evolution of the mean relative response of the 3 layers of the detector as a function of time during the entire run 2, as seen by the laser system. And here we have the mean gain variation as a function of eta and radius of the PMTs, covering the entire 2018 proton collision period. So in these figures, you can see these E cells and the A cells, they have the largest downdrift, again, because they have the highest energy deposits. They are nearest to the interaction points. And this here, you can see these in the red points. So the minimum bias system measures the response of the minimum bias events and also measures the integrated PMT signal over the large time. And it also monitors the full optical chain like the cesium system. And additionally, it also measures the instantaneous luminosity in the tile-cal and provide us with the luminosity coefficient. So in this plot, we see the response variation of A13 cell, which is the highest exposed cell to the beam, to the minimum bias shown in the green points, and the laser system shown in the blue points with respect to D6 cell, which is which we consider as a stable cell during 2017 data taking. And then we also perform combined calibrations in which we compare the cell response of cesium or minimum bias events with the laser measurements. And this calibration allow us to isolate the relative response of the scintillators and fibers. And we can also interpret the differences between these comparison. And we can interpret it as scintillator aging due to the radiation damage. And then for the time calibration, we calculated using the jets from the PP collisions and monitored during the physics data. And for the precise time calibration is very important for the reconstruction of the cell energy. And here we see the mean cell time in the jet events as a function of cell energy for the entire run 2, and we see that the mean cell time decreases gradually with the increase in the deposited cell energy. So about the noise in tile-cal cell, we have noise contributed by two types of contributions. One is the pileup contribution, which occurs due to the multiple interactions between the bunch crossing events. And then we have electronic noise, which in tile-cal is usually below 20 megaelectron volts, and we calibrate it regularly with when there is no signal in the detector. And here we see the tile-cal noise dependence with the average number of interactions per bunch crossing, and this orange and this maroon points you see for the E3 and A13 cell, which shows the highest largest noise because of the highest exposure. Then we have some performance studies in the tile-cal which validate and verifies our calibration systems. So the tile-cal energy response, we can probe it using the single hadrons and jets. The ratio of the calorimeter energy to the momentum of single hadrons can be used to evaluate the uniformity and linearity during the data taking. And here you see that the calorimeter response to single isolated charge hadrons characterized by the ratio E or B as a function of momentum with the data and the simulation, and which agrees quite agrees with each other. And then we have the isolated muons from the cosmic rays, which we use to study the intercalibration of the tile cells, and it verifies the measured energy at the electromagnetic scale. And for this study, we have around 0.5% non-uniformity in the eta and less than 1% in the phi response to cosmic muons. Then, so this is the LHC schedule given for the upgrade and the before. So we are now around here, and during the past LH2 phase 1 upgrade, which is still ongoing, we have already replaced the crack scintillators and trigger scintillators, and the detector electronics is already done. So for the upgrade, the plan of the LHC is to increase the instantaneous luminosity by a factor of 7.5, which will give us 4,000 inverse pentabond of data set and up to 200 collisions per crossing. So to withhold such high luminosity and radiation, the tile-cal must be upgraded. So the plans of the TileCal is to replace the full electronic, both on and off detector. And there is also a modular mechanic change in which we replace one super drawer with the 4 mini drawers, and then 10% of the PMTs will be replaced, and new high voltage and low voltage power supplies will be installed, and also the data and power redundancy will be increased to improve the system stability. And so as I already told that we have to replace all the electronics on and off detectors. So this is the current readout of the electronics, and this will be the new for the phase 2 upgrade, and it provide us with a higher trigger rate, and we will have extended data pipelines, and then it should withstand high radiation level, improve reliability and robustness, and then we also have the increased bandwidth. So for this upgrade, we have a lot of development in the front end electronics, in which the PMT box shaping is already done, and the digitization of the main board and also the communication on the daughter board is also done. For the phase 2 upgrade electronics, it should withstand the high luminosity environment and high radiation, and it should also provide us with the low latency and high frequency, and also we will have the fully digital input for the Atlas trigger system. This is a figure. This is a picture of a mini drawer which we will replace. Instead of one super drawer, we will put 4 mini drawers in the TileCal, and each mini drawer will host up to 12 channels by means of 12 PMTs, which turn the light pulses to the electrical signals, and then 12 front-end boards to shape the PMT signals, and a main board which sample and digitize the gains of the PMT signals and also give control to the Phoenix. And then a daughter board is also located inside the mini drawer. And so about the test beam measurements, so during the span of 2015 to 2018, we had 7 different test beam campaigns in which the TileCal modules were equipped with the previous legacy system electronics and also the new electronics, which we will upgrade. And and they were studied together, and overall we see a good performance and agreement between the legacy and the new electronics in terms of the energy calibrations, and also in terms of signal to noise ratio, we saw an improvement of about a factor of 2. And also we studied the response of the data to Monte Carlo to each Hadron type using this test beams, and we found the results compatible with the previous measurements. So here you can see the data to Monte Carlo response with the electrons and muons and hadrons, and all of these results validate our new electronics performances, and it review and improve the detector calibration procedure. So to summarize, the tile calorimeter is an important part of the Atlas detector, and in TileCal, at each step of signal production, we have dedicated calibration systems, and the stability of the absolute energy scale at cell level was maintained to be better than 1% during run 2, and during this ongoing shutdown, we already replaced the cracked scintillators, and the TileCal electronics maintenance has been performed. And for the phase 2 upgrade, all TileCal on and off detector electronics will be replaced, and for which the R&D is already done, and the initial test demonstrates good performance, and then the readout resolution and sensitivity is improved, and many components of this electronics and mechanics is already entered the pre-production or production level. Thank you so much for your attention.
Okay, thank you. Do we have any question here? Okay, since we're running a bit late, I will just ask one question. You mentioned that for calibration with cesium moves around. So did I understand well, it is actually inside the detector during the run and it moves around
so we have a hydraulic system in which we put the cesium through these source tubes into the module, each module, and then it moves around the whole detector body. So it's not already there. We have to.
Okay, and this is it done during some special runs or?
Yes, so it is done during special runs when we have no beam in the detector and during technical stops, and it's just a few times a year. So we have very few, you can see from here. In 2015 we have more, and then as we gradually here, so we have less cesium scans here.
Okay, I can see. Okay, thank you, Amara. I don't see any other hands raised, so we can now move on to the next speaker. That's Tatiana Karavicheva from JINR RAS. She will talk about ALICE upgrade overview for run 3 and run 4 at CERN. So Tatiana, okay, your screen is okay now. Now your screen is nice. If you can also go to the full screen. Okay, it is nice now.
Do you hear me now?
Yes. So please start and I will start timing. Okay, now we don't hear. I don't hear you now.
Okay. First, I would like to say good afternoon for everybody. In my presentation, I would like to focus on the ALICE upgrade overview for run 3 and run 4 at CERN LHC. So I would like to briefly remind you that ALICE is one of the experiments at LHC and dedicated to heavy ion physics. And we would like to study detailed characterization of strongly interaction quark-gluon plasma. And we are designed ALICE in order to carry out comprehensive studies of hadrons, electrons, muon, heavy flux, photons, and jet produced in heavy ion collisions. And during run 1 and run 2, we have a tracking and particle identification over large kinematic range with a high vertex reconstruction. We also have a good central barrel detector, what was presented by Igor in a previous presentation. We have a muon spectrometer forward and also forward detector for trigger centrality, luminosity, and for reaction plane. And during run 1 and run 2, we receive large number of results based on the full analysis of this data. We are working during approximately 10 years and measured with a different system, start from proton-proton up to lead and with a different energy. And okay. It's not change. Okay. And during the ongoing launch shutdown 2 at LHC, ALICE is undergoing a major upgrade. And you can see on the right part of my slides that now we are in launch shutdown. And we expect that start from 2022, we will start a new run number 2 during 3 years, and after launch shutdown 3, it will be a next run for starting from 2027. And our ALICE physics goal driving the upgrade requirement is measurement the flow mesons and baryon laws to the very low PT. This is to study mechanism of quark-medium interaction. We would like to study charmonium states to study the confinement and medium temperature. And also we would like to measure high precision light and hyperlight nucleus jet. And for this task, we need minimum bias and the high rate data taken. And we decided to take data without dedicated trigger. And so our requirement for data taking, it means that we would like to have an untriggered data sample. This is, for example, for around 3 around 4, like 13 inverse non-Barn for lead collision with interaction rate approximately 50 kilohertz. And we will start round 3 with the proton-proton data with interaction rate approximately 500 kilohertz. And then we expect that interaction rate will be increasing up to 1 megahertz. And we expect that during these runs, we will collect a factor of 50 or 100 more minimum bias data compared to our previous run 2 or run 1. And for make upgrade, we of course need the first to improve the tracking efficiency and momentum resolution at low PT. For this task, we need to increase tracking granularity, reduce material thickness, minimize the distance to PT for our tracking system, and also we think about synchronous data processing. So we are prepared for the upgrade of our online and our offline system. So the upgrade involves a completely replacement our inner tracker system and installed a new muon forward tracker system. This was detected using the same smooth pixel and MOPS maps technology. We also would like to change to our readout chamber for TPC using the new GEM technology. Also, we will install a new fast interaction trigger detector, what we would like to use for centrality when plane luminosity interaction rate. And also, the key feature of the upgrade of other detector is to go to the continuous readout for all other detector. And for this task, of course, we need to install a new online processing forum for synchronous reconstruction. And really, we are looking what we installed for run-through. We installed really 3 new detectors, as I said, ITS, MFT, and fast trigger detector. It's but really it's 3 dependent. But anyway, this old detector will be share the same support structure and installed at point 2. And I would like to start with our tracking system. Now we in May we finished installation of this detector, and this detector is ready for standalone and also for our cosmic data taking. And it's a nice detector with 13 billion pixels for after upgrade. And so what is the main motivation and goal to install our new tracking system? This, of course, because we would like to improve vertex and tracking precision, and also to make faster readout, because we would like to study rare processes. So in run 1 and run 2, our ITS system included 3 different type of technology. So we're using pixel, drift, and strip detector. But in run 3, we installed the new detector with inner and outer barrel with this new technology. We increased the number of layers. We made the inner part of our tracker system more close to beam pipe. We decrease the material budget, so special for inner barrel, it's 0.35% of radiation length. And of course, we have a better space resolution and maximum rate, and it's possible to work with a leaded collision approximately near 100 kilohertz and for proton, it's higher than 1 megahertz. What I would like to say that the core of the upgrade of the Alice silicon tracker is the new Alpine sensor. And this is a small monolithic active pixel sensor. This is special development for upgrade of our ATS and also for MFT detector. And the presence of full small circuitry within the active area eliminated the need to external electronic to be bonded to the chip. So now in the pixel we have amplification, shaping, discriminator. We have a high efficiency, like 90%. It's possible to working with maximum rate per pixel. It's for square centimeter. It's 100 megahertz. And what is important also that we have excellent noise performance. It means that we have less than 10 up to -8 fake hits per pixel per events. And this is a technology. You can see that acoustics cross-section of our Alpine chips, and it's possible to make more information about this from this nuclear particle physics paper. And if we are what we expect as a performance from ITS in run 2, so we think we receive improvement tracking efficiency compared to the previous ITS. So it's possible to see that with the PT start from 200 MeV, its efficiency like 90%, and we improved pointing resolution approximately three times. And this is example that it is possible using this new ITS to measure baryon-meson ratio for charm and beauty. And this is gives Alice possibility also to measure lambda B for first time in Alice as like example. So as the result, I would like to say that with new ITS, we will provide the high accuracy of secondary vertex determination. We impact parameter resolution will be better by a factor of 2. It is possible to low PT registration starting from 50 MeV to possible to measure charm and beauty mesons down to the zero PT. And this is important also that we increase our readout from 1 kilohertz from the previous hour runs to 50 kilohertz. And the next, our new detector is a muon forward detector. Is also installed in December 2000. It came, and the main objective for the muon forward tracker is to edit vertices capacities for the Alice muon spectrometer, because in run 2 we have a muon spectrometer, but really the position of this spectrometer is far from interaction point, and between interaction point and spectrometer we have absorber. And now in run 3 we install between the interaction point absorber new forward tracker, and this is added precise vertex capabilities to edit tracking at forward rapidity. So it means that now we have a new high resolution silicon tracking, and technology what we are using to create such detector based on the Alpine chip, it's like our ITS detector, and we receive a high pointing accuracy. So we have matching muon tracks with MFT tracks, and we have possibility to separate charm beauty via secondary vertex reconstruction. And on the right, you can see the photo before our installation. This is a to detect MFT, and also next our fit detector. And this is also a like examples of using the new MFT. We will increase possibility to measure G-psi and psi prime, and it gives for us possibility to improve signal to background factor 5 or 6. And last, our new detector, what we installed. This is a fast interaction trigger. This is installed in June 2021. And after that, it is possible to say that Alice is fit for run 3 after last new sub-detector installation. And this is a fast interaction trigger detector. It's a 3 detector with a different technologies. This is a scintillator and the Cherenkov detector, but they have a common functionalities that we would like to use this detector for luminosity monitoring. Is give for us a possibility online to determine vertex, to prepare the minimum bias and centrality selection, reject beam gas events, to prepare Veta for ultra-peripheral collision. But it's also important that we would like to use this detector for particle identification, and we are measured the collision time. And I would like to say that for level collision, we expect that a resolution of such detector will be approximately 7 picosecond. This is the fastest detector in ALICE. We also make some update of TPC, but not chamber, but we made the changing on only readout chamber. The main goal of this upgrade to make possibility to working with the high rate, approximately 50 kilohertz, as we have planned to working with a lead collision. In round 1 and round 2, we're using another technology. We use the multi-wire proportional chamber, and this is give for us to working only a few kilohertz. And now we make another solution. We adopt a solution using a new 4-gem stack. This is a combined gem foil with different size of hole pitch, and using this optimization of high voltage and gain, it is possible to working also with which will provide us ion backflow suppression up to less than 1%. And special for this detector was also development special chips for electronics using amplifier, shaper, and prepared for continuous readout, and also the front end card, which gives possibility to take data at approximately 5 megahertz. And of course, working as other detector with continuous readout. Some words about our online offline system.
Anna, you already passed your time, so if you can.
Okay, I will probably I skip some slides about our online and offline processing. So I would like to show only what our plans for run 4. For run 4, we really would like to upgrade our ITS and to install our focal detector. Then if you're looking, this is what we would like to do in ITS. So we would like to decrease material budget for ITS and for focal. And so you can see that using this upgrade, it is possible to improvement point in resolution by factor of 2 for all momentum, and also increasing the tracking efficiency for low PT particle and extension our PT. And last detector, what we would like to install, this is a focal calorimeter. This is included to detect electromagnetic and hadronic calorimeter. And what I would like to mention, that what is the main challenge to install this calorimeter, that it is possible to separate gamma and pi zero at high energy. And for example, 2 photon separation from pi zero decay approximately 2 millimeters. And because we would like to use the same MAPS technology, it is possible using MAPS layer providing position resolution to resolve overlapping shower. Then I would like to say that major Alice upgrade for run 3 is on track. So we upgrade our detector readout architecture and computing, also our online-offline system. We installed a new detector. So we're increasing tracking and vertex performance using this new detector, new fast interaction, and we are also start to prepare our new detector for run 4. This is ITS and the focal. And you can see on the right picture that many people have possibility now during long shutdown to visit Alice and to look our upgrade. So thank you for your attention and thank you for some delays with my presentation. Yeah.
Thank you, Tatiana. Since we went a bit over time, are there any questions? Okay, I don't see any hands raised, so we will move on to the next speaker, Dmitry Budnikov from Russian Federal Nuclear Center in Sarov. We'll talk about RFNC. Okay, I'm sorry, I cannot spell out work at CERN for the new spectrometer for Alice. So Dmitry, can you please share your slides? Okay, and then yes, we can see them, we can hear you. So as soon as you're ready, please start.
Okay, may I start? Okay. Good evening, colleagues. Let me present you a report, our report, Russian Federal Nuclear Center of NIEV's contribution to the construction of the fourth spectrometer. We will tell about design, mechanical design, cooling system, and temperature control. Okay, let's go. General information. Since 1996, our institute has been working on the construction and modernization of the force detector. Our institute is responsible for the mechanical design and assembly of a force detector, development of a cooling system, and automated system for the temperature control, monitoring, and stabilization. I would like to say that we are working with a worldwide collaboration from many countries, Norway, USA, Japan, Poland, Czech Republic, etc. It's a very successful cooperation for our spectrometer. In this slide, you can see general mechanical parameters of the force detector. In general, the force detector is a complex cooled system with a total sensitive surface area of approximately 8.7 square meters. We plan the force detector will have 5 full-scale module that including 17,000 and 1920 measuring channels cooled to a temperature of minus 25 degrees with stabilization in the range of plus minus 0.1 degrees. You see that the total weight detector will be about 25 tons. In general, the crystals are divided into 5 identical arrays. Each array is structurally combined into a module. Within one module, all crystals lie in the same plane. You see the overall dimensions of this on this slide. The modules are arranged along the arc of a circle with a radius of 4 4,600 millimeters, so that the arc of a circle is tangent to the surface of the crystals in the center of each module, and the center of the circle coincides with the interaction point of a colliding beams of the Alice experiment. Here you can see the main mechanical parts of the force spectrometer. Now we have 4 modules in the detector, not 5 as we plan. The total sensitive crystal surface area of approximately 6 square meter. This is the main unit, assembling unit of our detector, so called strip units. It consists from 16 crystals made from lead tungstate material. Here you see the process of module installation into the L3 magnet. One of the module number 1 has half of the crystals matrix. The total crystals quantity now is 12,544 crystals. Okay, this is a fourth module. Fourth module consists of 3,584 single detection channel, which forming a matrix of 64 per 55 crystals. Here you can see the overall dimensions of the module, and in this is a fourth module in his vertical position. This is a single registration channel, which is made as I said from lead tungstate crystals. Showers which occur in crystals under the action of high energy photons are converted into scintillation like radiation recorded by an avalanche APD photodiode, which photodiode, you see this is a photodiode, which is glued to the end of the crystals, with an optically transparent glue. The electrical signal from the APD photodiode are amplified by a charge-sensitive preamplifier. This is a crystals which are ready to be assembling. And what I would like to say that please pay attention that the density of crystals material is 8.28 gram per cube centimeter. It's a bit more than the density of steel, and the weight of one crystal is 0.7 kilogram. It's a heavy assembling unit, and the crystal for the force detector was produced by the stock company. Severnye Kristally Apatit in Russia. This is a crystal matrix. This is a front view of crystals matrix seen from the interaction point And what is important, the thickness of glue seal between the crystals and the surface of a photodiode is not more 0.25 millimeters. The presence of the air bubbles inside the seal is not allowed. Here you can see a step-by-step for the process of assembling the strip unit. 16 crystals are packed mechanically into groups of 2×8, referred as I told, strip units. The weight of each strip units is approximately 12 kilograms. You can imagine what is the assembling unit, how difficult to work with this heavy unit. Here you can see an example of the mechanical calculations of the main module frame. The results of mechanical calculations of a glass cloth base, laminate body, and cooling panels with T-section at their horizontal position. What I would like to say that the primary aim is to exclude any deformations that lead to the contacts between nearest crystals, in order to exclude any damaged crystals, because the materials of the crystals is very fragile. And the short preliminary summary for the force mechanical design. The mechanical design of a detector is very stable over more than 10 years of operation. The mechanical design of a module provides all conditions to reach a temperature of -25 degrees for the crystal matrix. In future, we plan to divide the module into two parts, named cold part with crystals and warm one with electronics, to have a possibility to service the electronics at any time. For example, when there is no beam. This is a finish of my report for the mechanical design, and I would like to give a word to my colleague Sergei Filchagin. She reports about the force cooling system and the system for temperature control, monitoring, and thermal stabilization. Thank you very much.
So we have got some physical factors that affect the efficiency of work the force detector. They are force light yield and APD gain strongly depend on the temperature. So we have to avoid water in front and electronics zone in warm volume. We have to remove heat from electronics. Therefore, to achieve 1% energy resolution, high precision temperature measurement in matrix required, and high cooling stability is required. For force requirements, temperature of operation is -25, and temperature stability is 0.1 degrees centigrade. To satisfy these requirements, the cooling system has been developed. This slide shows a scheme of a detector cooling system. The detector is located in the L3 magnet in the LS experiment. The cooling system consists of cooling unit and pumping unit, and a heat exchanger between them. A control system has been developed to measure the temperature and humidity in the detector, as well as to control the temperature of the detector. To measure the temperature, nickel 100 temperature sensors are mounted between the crystals. They have a thickness less than 100 micrometers to not enlarge gaps between them. We use 128 temperature sensors and 20 humidity sensors. Software has been developed to control the cooling system. The interface of control cooling system software is shown here. It should be noted that there was not any fail of cooling system due to software for 8 years of operation. A few words about results of cooling system operation. From 2015 to 2070s, the system worked for more than 900 days. Let's take a closer look at the result of the work for 2070s. It is the last year of run 2. The system worked 242 days for cooling from March 30th to November 27th. This is the temperature distribution of the module 2. The module temperature was about minus 24 degrees, and sigma is 0.05 degrees centigrade. 2 temperature peaks were detected only in the first module. The appearance of the 2 peaks is associated with the disconnection, a part of electronics in the volume of the module. This is the temperature distribution before disconnection, part of electronics, front-end electronics. The module temperature was minus 25.35. And we can see the second peak of the temperature distribution after the disconnection part of electronics. So our conclusions. The uninterrupted operation of the cooling system is provided in run 2. The temperature of all of modules satisfy force requirements. The cooling power is about 45% of max. Thank you for your attention.
Okay, thank you both. So I only announced the meeting because I was only told about one speaker. Anyway, are there any questions from the audience? I have one. What force is standing for? What does it mean? Can you hear me? So,
sorry, please repeat the question.
Yeah, what does FOS stand for? PHOS. What does it stand for?
PH for photon spectrometer. Yes, FOS, photon spectrometer.
Ah, photon spectrometer. Okay, thank
FOS, PHOS spectrometer.
you. Okay, thank you.
Mm-hmm.
Any other questions? I don't see any hands raised. If not, thank you very much. So we move to our
Thank you.
speaker, Maria Arsentiva, that will tell us about advanced accelerator concepts for future accelerators. So, Maria, can you share your slides?
Do you hear me?
Yes, yes. Can you share your slides, or you need the
Yes,
organizer
of
to share
course.
them?
So,
okay, just go to the full screen.
Yes.
Fine now. So please start.
Okay, so my name is Maria Arsentьева, and I work at Butker Institute of Nuclear Physics, Novosibirsk. My topic is on the edge of the conference area, so the presentation will be quite short, and I'll give you a brief review of the most promising accelerator concepts that can potentially advance the high energy physics to the new level. Among them, I'll mention plasma weak field acceleration, acceleration in the electric structures, and also high gradient metallic accelerating structures. So, first of all, I would like to draw your attention to the so-called Livingston curve. It shows the progress in increasing the collider energy depending on the year. The important thing here is that every progress step was made after the appearance of a certain technology. The last technology that significantly advanced physics was superfluid cryogenics at LHC. Of course, besides, the accelerator size is also a crucial parameter. But what can we do next? Colliders can't be infinitely increased, so what are other ways to increase the beam energy? It seems that there is need in new technologies and concepts, since existing facilities have different limitations, namely maximum accelerating field due to breakdown, magnetic field limitation, and finally the cost. So what are the main candidates to increase the beam energy? I'll mention some of them. First way is to use high gradient metallic structures. And actually this is the option that is proposed to be used at compact linear collider at CERN. So here there is a problem of the breakdown limit. The second option is acceleration in the electric structure. I'll say some words about how does it work and about the characteristic accelerating gradient. And the third way is to use plasma weak field accelerations. And about these three options. Plasma weak field accelerations can be used due to absence of the classical breakdown limit. Because if we excite plasma by the charged particle beam or by the laser pulse, the second or the witness beam may be accelerated in the longitudinal wave in the high amplitude electric field, and there is no classical breakdown limit like in metallic structure. Also, a field amplitude here depends not only on the excitation source parameters, but also on the plasma density. Characteristic numbers are the following. With the electron driver beam, the accelerating gradient of about 150 GeV per meter was obtained at Stanford. With the proton beam, the gradient of 200 MeV per meter was obtained, and with laser pulse, the gradient of 300 GeV per meter was obtained. But I have to note that the main disadvantage here is the accelerated beam quality. It's too poor. So the next option is to use the electric structure. Roughly speaking, these structures are very similar to the plasma weak field experiments. The breakdown limit is also very high due to the dielectric presence. The structures may also be fed both by a driver beam or a power source. Also, decreasing the dielectric structure's transverse size, one can increase more the breakdown limit. And
experiments with these structures show obtaining a gradient of about 1.3 GeV per meter. This experiment was also held at Stanford. And the structure was fed by an electron beam. But the challenge here is similar to this of the plasma wave field acceleration. The quality of the accelerating beam is too poor. It has large angles and an enormous emittance. At this state, the accelerated beam can't be used at colliders. And the third option I would like to mention is high gradient metallic accelerating structure. They are also called millimeter structures due to the wavelength. The size is not mentioned here, but at the right figure, for example, the cell size is 1 millimeter by 2 millimeter. And a slight advantage of this structure over plasma wave field acceleration and dielectric accelerating structure is that the accelerator beam quality may be higher. It is possible since there are no instability influence on the accelerated beam like there is in plasma or dielectric. Such structure are now being developed in several laboratories worldwide at Stanford and at the Frascati Institute. And at Stanford, for example, the accelerating gradient of 300 MeV per meter was achieved. And this is about 10 times higher than conventional structure gradient. So this is a very good perspective for future accelerator because the length could be reduced by 10 times. Besides, over the past few years, high gradient metallic structures are being developed at our Butker Institute at Novosibirsk. And I'll say some words about my work. Since we had not had any experience in this area, we developed and manufactured first prototype of the structure just for test of our manufacture technology. During this process, we have realized main challenge of these structures. At figures, you may see what is the structure size. They are much smaller compared to conventional structures. Again, this is necessary to increase the operating frequency and to have a higher breakdown limit. And actually, the structure size is the main challenge, and we have to keep extremely low tolerances. In developing next prototype, this is our present study, we take into account this peculiarity. Saying about the accelerating gradient we can achieve, I should note that this does depend on the power source for the structure excitation, while this is still in question for us and we have several options. So a brief conclusion. I would like to note that conventional accelerating techniques that are used at existing facilities are close to their limit. There is a need in novel accelerator techniques. Plasma wave field acceleration or dielectric accelerating structure have their main challenge in the low quality of the accelerator beam. Its emittance is enormous, and of course, such a beam is so far not suitable to be used at colliders. And the third option is to use high gradient metallic accelerator structure. But of course, here we have the main challenge in the fabrication tolerances. We have to keep them. But this is the question that can be decided. So we work with this option. So, of course, all of these advanced accelerator concepts have their pros and cons, but for sure, all of them still are very interesting to be developed. So that's all. Thank you.
Okay, thank you. And are there any questions from the audience? So I don't see any hands raised, and well, I don't know that much about accelerator technologies, but can you maybe tell us what you have done, what you have shown in the last few slides, how that compares with some other technologies investigated elsewhere?
Of course. So I'll begin with this slide. It presents the works of other laboratories. For example, on the right, you can see the structure that is being developed at Stanford. And the operating frequency is about 140 gigahertz. And the size is very small of the cell, 1 millimeter by 2 millimeter. And the difference with our structure, this slide, is that here we have standing wave structure, and at Stanford they have traveling wave structure. And the main difference is in calculations and how to calculate the energy that the witness beam can achieve in the excited structure. And also there are some manufacturing difference, because we have a different way to manufacture these structures, and that's all. And with this slide, I just wanted to show what are our challenge. For example, at the figure on the down right, you can see that the quality of the surface is not quite good. And now we developed another way to manufacture the cavities. And I hope we will not have such problems on the surface.
Okay, thank you. So are there any other comments or questions? Okay, I don't see any hands raised. So this was the last talk at this session. So I would like to thank everyone that stayed until the end and join other sessions as well. And then I don't know if organizers want to comment on anything else.
I would like to thank for all the speakers and Lydia Zhivkovich for on behalf of the Lomonosov conference team. Thank you very much. Tomorrow the sessions will start at 8:30. Thank you very much.
Thank you. Bye.
Okay, Lydia, thank you very much for covering of this session.
You're welcome.
Bye.
Bye.